My name is Kenneth Armstrong. I would like to thank you for viewing this VTC course on the Red Hat Certified System Administrator exam. I have been an avid open source enthusiast for years and have had the pleasure of working with Linux systems in a variety of environments. Some of those environments include internet service providers, multinational companies, local government agencies, and the U.S. military. I have been employed in various capacities of the information technology career field, but I find that teaching others how to use and administer the Linux operating system the most rewarding. I am currently a Red Hat certified engineer, and I also hold a few other information technology certifications. I am a firm believer in staying up to date with technology, as this career field changes rapidly. It doesn't hurt to be well versed in open source software, as the open source movement is a leader in many areas of the information technology industry. Again, I want to thank you for taking the time and learning with us in this video course. Make sure that you practice the skills taught in this series, and I wish you luck on the exam. Many Linux system administrators perform the vast majority of their tasks at the command line. A lot of technicians would agree that it is faster to complete administrative duties from within the shell environment. Although you could administer a Red Hat Enterprise Linux system entirely with graphical tools, the RHCSA exam expects that you know how to work from the command line, and your ability to pass the exam could depend on it. Practically every Linux desktop environment includes a way to access a shell. GNOME has terminal, just as KDE has console, spelled with a K. To access the terminal from the default GNOME environment of Red Hat Enterprise Linux, go to Applications, System Tools, and Terminal. We can even drag the menu item of the terminal to the panel so that we can get to it easier in the future. The shell environment itself is Bash, the born-again shell, which is a reference to Stephen Bourne, the creator of the original shell environment for the Unix operating system. There are multiple shell environments available to Linux, such as the Korn shell and the C shell. The default for Red Hat Enterprise Linux is the Bash shell. With Terminal, we can open up multiple tabs to run various commands concurrently. We can also edit the profile to change the colors of the environment. While in the desktop environment, we can access the different terminals known as the virtual consoles or TTY console, which is short for teletype, by pressing Ctrl, Alt, and F1 through F6. Just log in with your username and password. We will use root for our example here. While in the virtual console itself, we can just press Alt and an F number to access another terminal. For instance, Alt and F5 will bring us to another terminal. Alt and F4 brings us back to the one we were just at. Again, you can do this by pressing the Alt key and F1 through F6 to jump between the different terminals. We will display a text file so we can show you how to scroll up and down the screen itself while in a terminal. To do this, just press the Shift key and the Page Up key to scroll up, Shift key and Page Down key to scroll down. This is helpful in case you run a command where the output scrolls across the screen. To return back to a desktop environment, just press the Ctrl, Alt, and F7 key. And here we are back in our desktop environment. Part of the beauty of Linux is that nearly everything that is configured on the system is in human-readable script files. This case is no different for how the Bash environment is constructed. Here is a breakdown of how a login shell, which is a shell that is started when a user logs in, works. When a login shell is started, the etc profile script is ran. This script sets up the user's environment variables such as the user's path, host name, history size, and others. The etc profile script will also run the scripts found in etc profile.d. Next, the bash_profile script in the user's home directory is run. This script modifies some environment variables that are stored in the etc profile script. Next, the bash_profile script calls the bash_rc script in the user's home directory. This script sets local variables such as the ps1 variable, which dictates how the command prompt appears. A non-login shell, which is started by scripts, graphical terminals such as this one, and shells started by other bash shells utilize the same scripts, just in a different order. The first script that gets run for a non-login shell is the bash rc script in the user's home directory, the one we were just looking at. This script in turn calls the etc bash rc script, and this script calls the scripts in etc profile.d. Look these scripts over so that you will have a better understanding of how the shell environment is created. We have been adding users and groups to our system, but where is all this information stored? We will start with the etc passwd file. The etc passwd file is the database file that contains all of the users on our system. These include our system accounts that run various services, the root account, and all regular user accounts. The etc passwd file is broken up into different fields, each one separated by a colon. The first is the username field for the account. The second field is for the password. Notice the X in the field? That doesn't mean the password is an X. It just means that the password is encrypted and stored in a different file that we will look at in a moment. The next field is the user ID, and then the group ID. The next field is our comment field. Remember when we used the -C option of user add and user mod to enter the full name for a user? This is where that name gets stored. The next field is for the user's home directory. And the final field is for the default login shell for the user. The next file we will look at is the etc shadow file. The shadow file is where all of the password information for an account is stored. Only the root user can read the shadow file. Just like the etc passwd file, this file contains fields that are separated by colons. The first field is for the account's username. The second field is for the account's password. If you notice, some accounts have long strings of characters. This long stretch of text is the encrypted password. On some of these other accounts, we see exclamation marks in the password fields. This indicates that there is no password for this account. The next field is for the number of days since January 1st, 1970, also known as Unix time, that the password was last changed. The next field indicates the minimum password age expressed in a number of days before a user can change the password again. A 0 means that there is no minimum password age. The next field is for the number of days after which a user will need to change their password. If this time has passed by, the user can still log in with this password. They will just need to change it when they do log in. If you will notice, the number in this field is quite high, which sets the maximum password age well into the future. The next field is for the password warning period. This is for the number of days prior to a password's expiration. If there is nothing in this field, then there is no warning period. The following field is for the password inactivity period. This is the maximum number of days that a password could still be accepted by the system after it has expired. An empty field means that there is not an inactivity period in place. The next field is the account's expiration date, again shown as the number of days since January 1st, 1970. If this time has elapsed, a user will not be able to log into the system whether their password is valid or not. An empty field means that the account never expires. The next file that we will look at is the etc group file. This file contains fewer fields. The first field is for the group name. The next field is for the group password, also stored in a separate file that we will look at shortly. The next field is for the group ID, and the final field lists all of the members of this group. The final file that we will look at is the etc gshadow file. Just like the etc shadow file, only root can view this file. The first field is for the group name. The next field is for the encrypted password for the group, should one exist. The next field is for a comma-separated list of group administrators. And the final field is for the comma-separated list of users that belong to the group. To view the man pages for each of these files, you can do the following. Just replace shadow with the name of the file that you wish to look up, such as group, passwd, or gshadow. One of the most essential tasks for the Red Hat Enterprise Linux System Administrator is the ability to add and remove user accounts to systems. We will first demonstrate how this is done with the command line, then with the graphical tools. To create a new user on the system, we use the user add command. Here is the basic usage of the command. Just type in user add and the username for the account that we wish to create. By default, every new regular user that is set up on a RHEL system gets a home directory. So let's take a look at our /home directory. And here we can see that our gfreeman account has been created. Now, to delete a user account, we use the userdel command. Now, let's take another look at our home directory. Well, we still have a home directory for gfreeman. Why is that? By default, the userdel command does not remove the home directory. There's also something else that doesn't remove, but we shall see that momentarily. This is useful in cases where a user's manager or some other individual may still need access to the deleted user's files. Let's remove the home directory for gfreeman. And his home directory has now been removed. Now, let's say that gfreeman was hired back. We will add his account to the system again, and we will also include the user's full name to the command by using the -c or comment option. It looks like his mailbox file already exists. Well, why is that? Remember the userdel command by itself where it doesn't delete everything? Not only does it not delete the home directory, but it also does not delete the user's mailbox that was created earlier. Let's do another ls on our home directory to make sure the account was created. And now we have the gfreeman account again. Well, let's say that gfreeman has left the company again, and we want to remove his account including his home directory and his default mailbox since he wasn't here long enough to create any new files. We can do this with the following. The -r option is what removes the user's home directory and his mailbox. And we can see that gfreeman is now gone from the system. Now we have a new employee that is starting, who is a C programmer and prefers the C shell over the default bash shell. To change a user's default login shell during account creation, we use the -s option. We can even add a new user that has a home directory in a location of our choosing. Say we have an accounting department that all members should have their home directory in the accounting folder. Let's go ahead and create this accounting folder. Now we add our first member of accounting with their home directory under the accounting folder. And there's Barney Lee's home directory. We can also modify a user that is currently configured on the system with the usermod command. The usermod command takes many of the same options as the useradd command. Let's say that we want to edit Vance's account so that she has her full name when she logs into the graphical environment. Just as we would use the -c option to enter the user's full name when we create the account, we can use the -c option on the account that is already on the system. Usermod -c and the user's full name. And here we can see Alex Vance now has her full name at the graphical login, along with Barney Lee and Kenny Armstrong. New users can be created with the System Config Users graphical utility. This is accessed from System, Administration, Users and Groups. We add a new user by clicking on the Add User button. Here we can specify the username, their full name, just like the -C option, their default login shell, and if their home directory is going to be in a different location. We will go over passwords in a later video. Let's enter in a new user now. And we just click the OK button. We didn't enter a password, but that's okay. We will fix one up later. Now we have our new user. Notice that the user IDs for non-system and non-root accounts begin at 500. This is a default that is set up by Red Hat Enterprise Linux so that user accounts and system account IDs do not get mixed up. We can also delete a user account from here. Let's go ahead and delete the Bill Wallace account. Just highlight the account and click on the delete button. We also want to make sure that we want to delete his home directory and his mail spool. Another method to mount a remote networked file share is to use the AutoFS service. The benefit of using the AutoFS service is that the share is unmounted after a period of time and automatically mounted when the user needs to access the resource. The main configuration file for the AutoFS service is located at etc auto.master. Let's take a look at this file. We can use this file to configure mappings to other files that contain specific mountings that we wish to use. For instance, the top of the file points to a file named etc auto.misc that will mount a resource for the /misc directory. So let's take a look at that file. In this file, we can see some examples of locations and devices that can be automatically mounted when the user accesses them. If we look at the entry for CD here, we can see that a directory called /misc/cd will be mounted with the ISO 9660 file system, read-only, and other mount options. And the device used is /dev/cd-rom. When a user wants to navigate to the /misc/cd directory, the AutoFS service will bring this mount online and it will be active for a period of time, and after the user leaves that directory, the location will be unmounted, therefore saving system resources. Below this, we can see some further examples on setting up AutoFS mount options. Let's try a very simple example where we use the AutoMounter service to mount our remote NFS share. We have removed the NFS mount from our system and from our /etc/fs tab file, so the AutoFS service is the only thing we will use right now to mount the NFS share. The first thing we will do is add an entry to our /etc/auto.misc file for the NFS mount. Just like the examples above, we are creating an entry for NFS, which the AutoFS service will use to create our /misc/nfs directory when the share is accessed. Then we are specifying the NFS file system type. Next we are using the INTR mount option, which is short for interrupt, on the NFS share. What that means is that if for some reason the NFS server is not reachable, then our system won't hang when trying to access it. Finally, we are giving the share location just like we did when we manually mounted the share in our previous video. Once we make our changes, we will need to restart the AutoFS service. Next, let's do an ls on our /misc directory. We don't see the /misc/nfs directory because we haven't accessed it yet. Once we change into that directory, the AutoFS service will mount the share for us. and we are now in the /misc/nfs directory, courtesy of the AutoFS service. Now we will leave the /misc/nfs directory. By default, after 10 minutes, the /misc/nfs directory will no longer exist as long as nobody accesses it. We can also create a separate configuration file to create an AutoFS mount point by following the format of the auto.misc file. First, we will need to modify the etc auto.master file to point a new directory to our AutoFS mount point. We will create this line at the bottom of the file. This line is telling the AutoMounter that the /remote directory will be created from the contents of the auto.remote file. Now we will create the auto.remote file, which will hold the directives needed to create our mount points. We are using the same directives as before, but this time we will end up with a /remote/nfs directory. Again, we will need to restart the AutoFS service. Now, if we do an ls on the root directory, we can see that we have a /remote directory now. Now, do an ls on /remote. And we see nothing there. But if we navigate to our /remote/nfs directory, we will be able to enter the directory. Take a look at the man pages for AutoFS and AutoMount to find more detail on the AutoMounter service. The RHCSA exam assumes that you are already familiar with basic Linux shell commands. However, we are going to review the more common commands that you will need to know. The first command that we will look at is ls, which is short for list, as we will be listing a directory's contents. Here we are performing the ls command on the root user's home directory. Now, if we wanted to list the file sizes and who owned what files and directories, you can do what's called a long listing, ls-l. Here we can view the file's permissions, the user ownership, and the group that owns it, and the file size. An ls-lh will show us the same information, but with the file size in human readable format. 1.0 kilobytes for this anaconda-ks.cfg file, and 40 kilobytes for our install.log file. To view all files and folders, including those that are hidden within our home directory, we can do an ls-a. Note here that we have our bash_history file and our bash_logout file, both preceded by a dot, which indicates that they are hidden from normal view, along with these directories that are also hidden from normal view. The next command that we will look at is cd, which is short for change directory. To change directory to a particular folder, you just type in cd space and a directory that you wish to change to. Notice how the prompt changes to the directory that you are currently in. To move up one directory, you can do cd ... If you'll notice, you are now back at the root directory. cd space tilde will bring you back to the root user's home directory. To also view which directory that you are in, you can use the print working directory command, pwd, and it will give you the full file system path as to your current location. Now we will move on to creating directories. This is done with the make dir command. We will create a testing directory in the root user's home directory. Now if we perform an ls, you can see that we now have our testing directory. We can also make a parent directory and subdirectories beneath the directory with the -p option. Let's do an ls on our testing directory. Notice that we have the first directory showing up here that we just created with the make dir-p command, test1, which is right underneath our testing directory. And if we do an ls on testing test1, we also see our final directory of test1b. To remove a directory, we will use rmdir, which is short for remove directory. The remove directory command will only work on directories and subdirectories that do not contain any files. Here is an example of removing a directory that is nested beneath other directories. Now this command will only remove the test1b directory, even though we specified the full path, because it is only going to default to the last directory specified. See how the test1 folder is now empty? We can also remove a full directory tree, provided that there is no content within the directories, with the rmdir-p command. And now we do an ls on the root user's home directory, and we can see that the testing directory has been removed, along with the test1 directory that was beneath the testing directory. The cp command copies files and folders from one location to another. We will copy the etc host file to a subdirectory that we have within the root user's home directory called example. And there is our host file. To remove files and directories that contain files, we use the rm command. Rm by itself will prompt you before it removes anything. To not get a prompt before a remove action takes place, use the -f switch. Only do this if you are sure you want to remove something, as the action is not reversible and there is the potential for damage to the operating system if this is performed on a non-protected system file. Let's remove the host file that we had just copied over to our example directory. We already have our rm command here, so let's just specify the directory and the file. Notice that it is prompting us to make sure that we want to do this. We just type in y for yes, and we will now perform an ls on our example directory, and notice that it is now empty. Continuing on from our last video where we were working with basic command line commands, we will now remove a directory that has a file beneath it. To do this, we will use the -r, the recursive switch, for the rm or remove command. In order to do this, we have copied our etc host file back into our example directory. So in order to remove the example directory and the host file at the same time, we will use the rm-r command on the example directory. Now notice that we are going to get prompted by the rm command to make sure that we want to do this. It's just extra protection to make sure that we do not delete any files and folders that we do not wish to remove. So we just type in y for yes. Yes, we wish to remove the file example/host, and yes, we do wish to remove the directory example. Perform an ls on the root user's home directory, and the example file and the host file beneath it are now gone. The move or mv command moves files and directories to other locations. Let's move the kickstart file from the root user's home directory to the desktop folder. And just like the cp command, we are moving something to somewhere. Now if we perform an ls on the root user's home directory, the anaconda-ks.cfg file is no longer there. However, if we perform an ls on the desktop folder, That is where our anaconda-ks.cfg file is at. The move command is often used to rename files as well. We are basically moving an original file name into something else. For example, let's go into our desktop folder and let's work with our Anaconda file here. Let's rename it by moving the original anaconda-ks.cfg file to anaconda-ks.cfg_backup. Now if we perform an ls, we will see that the backup file exists but not the original. The reason for this is we have actually just renamed our original file by moving it from its old file name to a new file name. The less command is used to read the contents of a file. Let's take a look at our Etsy profile script with less. We can scroll up and down in less by using the up and down arrow keys. We can also skip pages with the page up and page down keys. Another way to scroll through the file in less is by using the J key to scroll down and the K key to scroll up. Pressing Q will quit less and bring us back to our terminal. As an RHCSA candidate, you should already be familiar with performing a basic installation of Red Hat Enterprise Linux. The only method of system installation that the RHCSA exam covers is the Kickstart installation, which we will cover in a later video. However, just as a refresher, we are going to step through a basic installation of Red Hat Enterprise Linux using the installation DVD. After you boot your system using the DVD, just highlight Install or Upgrade an existing system and press Enter. On this screen, you are asked if you wish to check your installation media just to be sure that you do not have a corrupt installation disk. You can press the OK button to continue on and check the installation media, or if you have already verified your media, you can highlight Skip and press Enter for that. We've already verified this disk, so we're going to skip the disk check. When the first screen comes up, just click Next. Choose a language that you wish to use for the installation process, click Next, and choose the type of keyboard that you have. Since this is a very basic system, we're going to stick with basic storage devices, which is generally reserved for those that have a local hard drive. Click Next, and here we get a warning stating that the installer has found a disk that could possibly have data on it. This disk doesn't, as it is a brand new blank disk, so we're going to click on Yes to discard any data so it can continue on and install to this disk. Now we are prompted to enter in a host name for this server. We're going to use rel6 test. Now on the bottom left, there is a button to configure the network. Let's go ahead and click on it. And we will choose our system ETH0 device. Click the Edit button. And we want this device to be connected automatically, so click the check mark box for that. And check the IPv4 settings. And right now it is set to automatic or DHCP. We will leave it at that as we do not wish to assign this system a static IP. Click Apply, then Close, and now we wait for the Network Manager service to start the device for ETH0. Then click the Next button. You are prompted to choose the time zone that you are currently installing your system in, and we are on the East Coast, so we will use the default of America, New York, and click Next. On this screen, we are asked to enter in a root password. Once you type in your password, click the Next button. On this screen, you are asked the different types of installation method that you would like to use. The two main ones that you would work with would be the top two, either use all free space or replace any existing Linux systems. We do not have any existing Linux installations on here, so we will go ahead and choose the option for Use All Space. Let's go ahead and click on the Review and Modify Partitioning layout. When we click Next, this is going to give us an overview of what our disk will look like during the installation. Click Next. And here we are shown the overview of our installation disk layout. We are getting a root partition of about 7 gigs and a swap partition of about 2 gigs. Below that, we see that we have a separate partition for boot of 500 megs. By default, our system is going to install using LVM, or Logical Volume Management. Do not worry, as we will cover LVM in greater depth in later videos. Go ahead and click the Next button, and we receive a warning that the following disk will be formatted, which is quite fine. It's a brand new disk, and there's nothing to lose on here. So click the Format button, and again we are reminded that all of our changes are about to be written to disk, destroying any data that is on there. Go ahead and write changes to disk, and the file systems get created. Next, we are asked to install the bootloader to a particular location. We only have one disk, so we do want the bootloader to go to dev SDA, and we can also put in a bootloader password. We're going to leave this empty for right now, as we will show you how to do that in a later video. And here we are shown what our default boot menu will look like after the system boots up, and we'll leave this the same here. Click Next. And this is the screen that we can use to determine what type of installation we are going to set up. Let's go ahead and choose a desktop for now, as we will be modifying our software installations throughout the video series. We go ahead and click the Next button. And now our system will be installed. And now that the installation has completed, we can press the Reboot button to restart our system. After the system restarts, we are presented with what is known as the first boot screen. This is where we perform our final configuration steps to complete our RHEL installation. Click the Forward button. Click Forward to agree to the license agreement. And this is where we get asked to set up our software updates. Since we are going to use a local network and we're not going to connect to RHN or the Red Hat network, we're going to click on No, I prefer to register at a later time. Click Forward, and we are presented with a window asking us to verify if we do not wish to connect to RHN at this time. Click on No thanks, I'll connect later. And we get a message stating that our system is not set up for software updates. This is our training environment, so that's okay. Click Forward. And here we create our regular user. Then click the Forward button. And we're going to leave it at system time, as we will set up NTP later. Click Forward. And since this is a basic system and we do not have a whole lot of RAM on it, we're going to get a warning stating that we cannot do a kdump configuration. That's fine for training. Click OK. And click Finish. And we are now presented with the login screen. And that's all there is to it for a basic RHEL installation. Now, we are going to go over the basics of file and folder permissions. Basic file permissions allow or deny a user to read and write files. Directory permissions allow a user to list a directory's contents. They can create new directories or files within it, or we can even set permissions to deny a user to do any of these things to a directory. There are two different ways with which we work with file and folder permissions. The first is with the symbolic format, which is how we view files and folder permissions when we use the ls command. We can also modify file and folder permissions in the octal or numerical format. Linux permissions are broken down into three different categories. The first that we have is read, using the letter R. Next we have write, using the letter W, and then finally execute, which uses the letter X. All permissions are preceded by a special character. A dash just represents a regular file. If we see a D, that represents a directory. If we have a lowercase l, that means it is a symbolic link, which is basically a shortcut. Linux permissions are grouped in this particular order. First we have the owner on the far left, and then the middle set of permissions is for the group, and finally to the far right we have the world permissions, also known as other. If we look below at our example, where we did an ls-l to get a long listing of a directory, we can see our permissions here. Our dash, just like we said before, is a regular file. These three represent the owner permissions. Our next group of three is our group permissions. And then our final group of three is the other or the world permissions. Same thing with the directory, as represented by the D in the front. the owner permissions for that directory, the group permissions for that directory, and then finally, the far right, the other or the world permissions for that directory. Each permission bit has an octal value associated with it. The read permission is equal to 4, the write permission is equal to 2, and the execute permission is equal to 1. No permission, represented by a dash, equals 0. So a file with this particular set of permissions is equal to 755. And the way we get that is we have read, write, and execute, which is 4, plus 2, plus 1, which equals 7, and then read, which is 4, and a dash, 0, and execute, which is 1, so we have 4 plus 1 is 5, and again 4 plus 1 equals 5. 7, 5, 5. Each file is owned by a user and a group. The user ownership is listed first, then the group ownership is listed. In our example, we have a file, .text, that is owned by the user A. Vance. And a file .text is owned by the researchers group. Next, we are going to start working with basic permissions. Let's take a look at some files and folders in our root user's home directory. Using the long listing, we can see all of the file and folder permissions for everything in the root user's home directory. Take a look at the permissions for the vim-test.txt file. As we can see here, there is a dash in front, indicating that it is a regular file, that the root user, which is the owner, has both read and write permissions, the group has read permissions, and the world has read permissions. Let's modify the permissions on this file to grant the A. Vance user the ability to modify it. First, we will copy the file to A. Vance's home directory, since she won't have access to the /root directory. And we will double check the permissions of the file. We see that the owner of the file is root, so A. Vance will not be able to change the permissions on the file so that she could write to it. Only root will be able to do so, since root is the owner. The tool that we use to modify file and folder permissions is chmod, or the change mode command. We can modify a file's permissions either using symbols or by numbers with the chmod command. We will start with the symbols. We run the chmod command, specifying O for other, and we are adding the write permission to the vim test file. Then we log in as A. Vance, and we verify that we can read the file. And since A. Vance has write permissions to the file, we will modify the file from the A. Vance account. Back in the root account, we wish to take away the ability for A. Vance to write to this file. We can do this using the chmod command and by changing the octal value of the permissions on the file. Let's modify the permissions so that only root can read and write to this file. We can see that only root has read and write access to the file. If you remember from the previous video, 600 is equal to read and write and no permissions for the group or for the other users, which is what we have here. Just read and write for the owner, no permissions for the group, and no permissions for others. Let's try and read the file from the A. Vance account. And we are denied access. You might be wondering, where do the default permissions come from on a RHEL system? These default permissions come from the umask, or User File Creation Mode Mask value. You can view your default umask value with the umask command. Here we see that our umask value is set to 0022. Bash gets this value from the /etc/profile script. Umask works like this. A file has a default set of permissions of 666. We take our umask value and subtract that from 666 to get our user default file permissions of 644. Let's try this. Here we are just creating an empty file. Now let's take a look at the permissions of that file. And we can see that the file's permissions are set to 644, or read-write, read-read. The same principle applies to a directory. A directory's base permissions are 777. So by subtracting our umask value from that of 022, we end up with 755. See the difference between the file and directory permissions? And that is where the default file and folder permissions come from. We have discussed the basic permissions for files and directories, so now let's move on to ownership. Let's take a look at the contents of Avance's home directory. We can see that all of the directories in here belong to the user Avance and also to the Avance group, as denoted in our permissions. But at the bottom, we have the vim-test file that is owned by the root user and the root group. So how can Avance have ownership over this file? Since the file is owned by root, only root can change the ownership of it. For that matter, root can take ownership of any file on the system and grant it to other users. Let's give this file to Avance by using the chown or change ownership command. We have now changed the ownership of the file so that the Avance user now owns it. However, the root group still retains ownership. The chown command only changes the user owner if a group isn't specified. To change both the user and the group ownership of the file, we use chown like this. We use a colon to denote that we wish to change the user first, then the group ownership of a file. We can also change group ownership with the chgroup command. Let's change the group ownership of the vim-test file to the research group. We can also change ownership on directories with the chown command. Let's create a directory for Avance and copy over a file from the root user's home directory into the new directory under Avance's home directory. According to the permissions, Avance can read the contents of the directory, but she will not be able to create new files in the directory, delete the directory, or rename it since she is not the owner. Let's give Avance ownership of the directory. Now, Avance has ownership of the notes directory, and she can create files in there. We will log in now as Avance and create a file in the directory. We can see that Avance has ownership of the file she just created in there, but not the one copied over by root earlier. We could just run chown on that one file, but another way would be to run chown recursively on the whole directory. This is what root should have done earlier when ownership of the directory was granted to Avance. Here is how we can use chown to grant ownership of a directory and all files underneath it. We can now see that Avance is the owner of the directory as well as all the files underneath it. We are going to switch gears and discuss another type of file attribute known as the immutable bit. We can use the immutable bit to make a file read-only so that no user, not even the root user, can modify or delete the file. This is done with the change attribute command. To change the immutable bit on the vim-test file in Avance's home directory so that no one can edit or delete it, we use the +I option on the file. To view the file's attributes, we run the ls-attribute command. Let's see our new attribute on the vim-test file. Notice the I here? That I indicates that this file has the immutable bit set. Let's try and delete the file. See, even as the root user, we cannot delete the file. To remove the immutable bit, we use the -I option. Once again, let's take a look at the file's attributes. And the immutable bit is gone. Now we should be able to delete the file. And the file is now gone. The immutable bit can be quite handy if you wish to protect a file from accidental deletion. Look at section 1 of the change attribute command to learn more about the different types of attributes that can be applied to files. In this video, we are going to discuss some basic troubleshooting techniques that you can use while working with Red Hat Enterprise Linux systems. There are multiple theories on troubleshooting and numerous books and websites on the topic. These are the steps that I use. The first thing you should do is try to gather as much information as possible. Find out what the user was doing when the error occurred. Next, determine what the error is. Ask the question, what seems to be the problem? Try to find out what was the last thing that changed on the system. Was there any new software or hardware installed? Did someone modify a configuration file? Next, research a solution to the problem. Look around for a solution on the internet, ask about one on mailing list, or you can check with your support representatives. Next, test the solution that you have decided on. If it works, then make your change permanent and note the resolution and any necessary documentation. If your resolution did not solve the problem, then repeat the above steps. If the problem that you are encountering does not have an obvious fix, you should make sure to check your system's logs. The first log file you should review is the var log messages file. This will contain information on your services, such as an error message or notifications from other processes whenever a change occurs. The next log you should consult is the var log audit.log file. Use your SE Alert or AU Report utilities to parse this log, as these tools will often provide a fix for the issue, or at the very least, they will point you in the right direction for a resolution. Another log file that you should check is the var log secure file. In case you believe that another user has escalated their privileges and caused some damage to your system, you can look in this file and correlate the time that the user logged in as root to the time that the damage occurred to help determine what happened. And finally, if the issue pertains to a particular service such as a web or FTP server, look in the var log directory for the log files that pertain to these services. If your system is not operating at full performance, for example, graphical windows take a while to open up or web page requests take longer than usual to respond from your web server, check to see what processes are running on the system and how much CPU time they are taking up. If you are in the graphical desktop environment, then you could use the GNOME System Monitor application. This utility will show you what processes are running, how much CPU time they are taking, and it will also graph your overall CPU usage. If you are not in the desktop environment, or you are unable to open the GNOME System Monitor, then you could use the top utility from a terminal. Here, you can see your top processes that are utilizing a lot of CPU resources, as well as other pertinent information. You could also use the ps command to see if you have a process that is hung up. If you have a process that is taking up way too many resources, you could try and use the renice command to change its processor priority. If it doesn't look like a process's CPU usage is slowing your system down, check your disk space and memory usage. You may have an application that needs a certain amount of disk space to write temporary files, and there isn't enough room to store them. You could check to see how much space you have left on a particular file system with the df-h command. This command will output how much free space you have left over in human-readable format. You could also find out how much disk space is in use within a particular directory by using the du-h command. This command will output your disk space usage in human-readable format, which is helpful in determining which directory you could clean up the most data from. As for your RAM usage, run the free command. This command will tell you how much RAM you have used and what is available, as well as how much swap space you have available. If you don't have enough physical RAM but some extra hard drive space, then you could create more swap space and add it to your total. That may not be the best solution for long-term performance, but it could get you by in a pinch until you get some more RAM cards installed on your system. If a piece of hardware does not seem to be operating correctly and you have verified that you have it connected and powered on, run the following commands to see if the system's kernel has detected it. If you have a new hard disk that you installed, run the fdisk-l command to make sure it is detected by your system. If you installed a new internal PCI card, such as a network card, run the lspci command to see if the PCI bus detects it. If not, make sure that the card is properly seated in the PCI slot. If it requires external power from the motherboard, make sure that you have the power connected. The same goes for USB devices. Run the lsusb command to verify that the system sees your device. You can also run the DMI decode command to check your BIOS version. It could be possible that you may need to upgrade your system's BIOS to enable new features. If you are having issues with a particular service, for instance perhaps it is not running or it won't seem to start properly, use the following commands to verify its configuration. First, run the checkconfig --list command to make sure that it is set up to start at boot time. Run the service, then the name of the service, and then status command to verify that the service is running. If the service won't start, or you get errors when you try and start it, double-check the service's configuration file. Make sure that you have everything configured properly, and make sure any security context and permissions on the configuration file are set properly. Some services, such as HTTPD, will have an option that will let you check the configuration file syntax, such as the service HTTPD config test command that you can use for the Apache web server. In our next few videos, we will be looking at some scenarios where we do some troubleshooting on network connections and working with the rescue environment that comes on the installation disk. There are a lot of text editors available for Linux. The first two that we will discuss are cat and nano. Cat is short for concatenate, which means that we can join multiple files into one, or we can concatenate the output of our terminal into a new file. We can also use cat to display the contents of a file in the terminal. To create a new file at the command line with cat, we do the following. We start cat, telling it that we will be typing input at the terminal until we hit EOF, or end of file, which tells cat that we are finished. This next bit tells cat that we are going to be dumping the contents of what we type at the command line into a file called test.txt. This is also an example of output redirection, which we will discuss further in a later video. For now, just understand that what we type at the command line with cat will be saved in a file called test.txt. And now we can start inputting our text. Type in EOF for our end of file, and we're brought back to the terminal. Now we run ls to see that we have a new test.txt file in our home directory. And here it is. Let's use cat to display the file's contents. Notice that we are back at the command prompt. Cat is not a program like less that will let us scroll through multiple pages of content. Cat just displays the contents of the file to the console and exits. Cat provides a quick way to create new text files and read their contents. To combine files into a new single file, we can run cat, and we will use our install.log.syslog file and our test.txt file into a file called new file. See how the second file, test.txt, was added to the bottom of the first file? Nano is an easy-to-use text editor that is similar to the edit text editor from DOS. To start Nano with an empty file, just type Nano at the command prompt. Once in Nano, we can type in some text. Then press Ctrl-O to save or write out the file. Here at the bottom is asking us for a name for the file. And we press Enter. Now we have a new file saved. As you can see at the bottom, some of the more common tasks that you would perform with Nano are displayed for your reference. To exit Nano, just press Ctrl-X. And we're back at the terminal. We can even open a file with Nano by specifying its name at the command line. And we can navigate around Nano by using the arrow keys. We can even replace text in the file. Press Ctrl-W to find a certain word, then press Ctrl-R to invoke the replacement option. So let's search for the word hello. Then press Enter and input a word that we wish to replace our search term with. Press Enter, and as soon as Nano finds an instance of our search term, it will prompt us to replace it. We can press Y to replace just this instance or A to replace all. To cut a line of text, use the arrow keys to navigate to the intended line and press Ctrl-K. To undo the cut operation, press Ctrl-U. To get further help with the Nano text editor, press Ctrl-G. The instructions at the bottom of the window will instruct you on how to navigate the help file. Press Ctrl-X to exit. As you can see, Nano is an easy-to-use text editor. Now we are going to discuss process priorities. Changing a process's priority is doing nothing more than devoting more or fewer CPU cycles to a process. This could be useful on a web server where you want to devote more of the processor's time to the web server daemon so that it could answer requests for web pages quicker. On the other hand, you could have a process that is using up more CPU resources that you would like dedicated to other tasks, so you throttle back that process's CPU usage. When we modify a process's CPU usage, we are changing its nice value. Nice values range from -20 to 19, with -20 being the highest nice value and 19 being the lowest nice value. The higher the number, the less CPU time a process gets. The default value that a process gets when it starts is 0, which is right around the middle of the nice scale. To start a process with a specific nice level, we use the nice command. Let's say that we wanted to start the FTP service with a higher priority than normal. We could do so with the following command. With this command, we are starting our FTP service with a nice value of -10, which grants the FTP service more CPU cycles than it would have with the default nice value of 0. We can verify that we have started our process with a higher nice value by checking the output of our ps command. The first number is the PID, or process identifier. Next, we are looking for the nice level and the name of the command that corresponds to this process. And we have confirmed that the VSFTP daemon is running with a nice value of -10. We can also take the PID number and use it to change the nice level again, while the process is already running. To change the nice value of a process already started, we use the renice command. Let's use the renice command to decrease the nice value of our VSFTPD process. With this command, we are specifying that we want the priority of our FTP service to have a nice level of -5. We can also use the top command to change and view nice levels. We could run top by itself, or we can pass only the PID of the process we wish to monitor. And here we see only the details of our VSFTPD service. The NI right here is referring to the process's nice level, and we can see that it is -5. We can easily change the nice value of the running VSFTPD process while in top. To do this, press the R key to renice a process, then enter the PID of the process, then the renice value we wish the process to have. Immediately, the new nice value is applied and we have instant feedback of that nice value. As root, we can change the nice level for any process on the system. Regular users can only change the nice level for processes they own. Changing a nice value on a process is probably not something that you will have to do very often, but it is useful if you have single function systems where you would want that function to have a little bit more performance. CIFS, or Common Internet File System, is the default network file and folder sharing protocol used and developed by Microsoft. On Linux systems, we have the Samba software suite that allows a Linux system to share files, folders, and printers with Microsoft Windows systems. There are a lot of things you can do with a Samba install on a Linux system to make it integrate more easily into Microsoft Windows environment, but the RHCSA exam only expects the candidate to be able to mount and unmount CIFS shares. We will be working with the SMB client utility. SMB client is a program that we use to access CIFS shares on remote systems. To see what shares are available on a specific server, run the SMB client command with the -L option. The -U option specifies the username that has rights to the CIFS share. The -L option lists the available shares at the server specified either by IP or hostname. Then we enter in the user's password, and we have now listed our Samba shares. Let's work with the share named Samba. To log into the remote CIFS share, run the following. When accessing a remote Samba share, use 2 // followed by the IP or the hostname of the server that hosts the share, then a single / followed by the shared name. This is known as a UNC, or Universal Naming Convention path, that Windows systems use for accessing CIFS shares. Again, enter in your password, and you are now logged into the share. Once you do get logged into the share, you can run normal directory commands to see what is available. You can also even run the equivalent Windows commands. We can use standard FTP commands to download and upload files. First, let's run the LCD command to change to our local home directory on our client system. Now, let's use the get command to retrieve the readthis.txt file. And now we have a copy of the readthis file in our local home directory. We will upload a file to the Samba Share with the put command. And we can verify that we uploaded the file. To log out of the share, run the quit command. We can mount a CIF share with the mount command. Here is the syntax for this. First, we will need to switch to root. We are specifying CIFs for the file system type, and we are using a mount option for the username. Take a look at the man page for mount.cifs to see the different types of options you can use. We are mounting the share to our /mount/samba directory that we had already created earlier. And now we should be able to access our Samba share as if it were a local directory. I want to quickly show you that you can also access a Samba share from the desktop. Go up to Places, and then connect to Server. We can change the service type to Windows Share, and enter in our information. And then click the Connect button. Enter in the password, then click Connect. And here we can see we now have access to our remote Samba share. We can transfer files back and forth just by dragging and dropping them into this window. And that is how you access a Samba share. We have reached the end of this training series. In this series, we covered all of the exam objectives for the Red Hat Certified System Administrator exam as outlined by Red Hat, located at the URL below. We based the content of this training off of what is taught in the RH-134 course as taught by Red Hat. You can go to the link below to take a pre-assessment questionnaire to see if you are ready to take the exam, or if you need more time to study. The material taught in this course will help you on your way to the RHCE exam, as you will need to know what was covered here as well as what is expected of an RHCE. In this course, we covered how to use essential Linux tools, such as using the command line, managing user accounts on a system, modifying file and folder permissions, and reading system documentation such as the man and info pages. We also covered how to modify text files at the command line with tools such as Vim and Nano, working with regular expressions to search for text within files, and archiving files and folders with the tar and gzip commands. We demonstrated various ways of starting and stopping our systems, and we learned how to boot a system into a different run level. Next, we discussed what the single user mode is for, and how to use it to change the root password, and how to lock the single user mode down. We also covered the various tools that we can use to manage the system's processes, such as top and the ps command, and how to start and stop services. We then went on to discuss the importance of managing and monitoring system log files. We also worked with virtual machines. We demonstrated how to administer them from the command line and how to create new ones with the Virt Manager utility. We also showed you how to administer various network services, such as setting up system connectivity and installing various network services, such as a web server and an FTP server. We also worked on various types of basic storage management, such as creating new partitions and file systems and configuring these devices to be available at boot time. We also showed you how to set up an encrypted partition and make it prompt a user for a password at boot time. We then moved on to working with LVM by showing you how to create new LVM volumes and the different methods available on increasing and decreasing their size. Next, we worked with network file systems such as NFS, the AutoMounter or AutoFS system, and how to mount CIFS shares. We demonstrated the various ways to install system software and how to properly update the Linux kernel. We installed a system using the Kickstart method and used a network installation source. And one of the more important topics we discussed was how to manage and configure ST Linux on your system. And we also showed you how to modify the kernel runtime parameters. The VTC RHCSA course that you just completed was roughly 8 hours in length. Compared to the RH134 course, which is roughly 32 hours in length, you can see that we did a lot to pare down the content. However, even though I firmly believe that the Red Hat training courses are well worth the money and they are taught by excellent instructors, you could still pass the RHCSA exam by using this course along with some rigorous self-study. We made sure that we covered every exam objective and demonstrated how to perform the tasks as they are listed by the RHCSA exam objectives. However, you could also use this course along with the official Red Hat training and preparation for your exam. Either way, I wish you the best of luck on your exam. You will find that it is one of the most rigorous and well-respected certifications in the industry. The first step in creating logical volumes is to first convert any disk or partitions into physical volumes. We have a new blank disk and another disk that has an empty partition on it. We will show you how to create physical volumes out of both. First, we will create a physical volume out of our disk that has a partition on it. We have a partition on /dev/sdb that we need to modify. The file system ID on this partition is set to the default of 83. We need to change this to the hex code for an LVM partition. Press the T key to change its type, then press Enter. Next, press the L key to bring up the list of hex codes. The one for Linux LVM is 8E, so we need to change our partition to this. And now our partition is ready to be converted to a physical volume. Press the W key to write our changes, and press Enter. Now let's verify our partition. We create physical volumes with the pvcreate command. Just give it the device that you want to convert and press Enter. Now we have a new physical volume. Next, we are going to convert our blank disk that doesn't have a partition on it. Again, just run the pvcreate command with the device name. And that's all there is to it when it comes to creating physical volumes. We can check on our physical volumes with the pvs command. And at the bottom, you can see our two brand new physical volumes. You can view more details with the pvdisplay command. Now, we need to lump these physical volumes together into a volume group. This is done with the vgcreate command. The first option is the name that we are giving to our new volume group. Then we tell vgcreate what devices we are adding to this volume group. And now we have a new volume group. We can check on our volume groups with the vgs command. As you can see, we have a total volume group size of 2.49 gigs by combining a 500 megabyte disk along with a 2 gigabyte disk. And just like with pvdisplay, we have a vgdisplay command for volume groups. And here we can see that our physical extents are broken up into 4 megabyte chunks. A quick tip that could help you out on the exam: if you can't remember the exact names of the commands that you need to run for a particular portion of the LVM creation, just type in the first 2 characters of the command, then press Tab twice. For instance, to see all of the commands that you could run for physical volumes, type in PV, then press Tab twice. In the following video, we will create a logical volume and extend our home directory. Now that we have a brand new volume group set up, we are going to create a new logical volume. We create new logical volumes with the lvcreate command. We will create our new logical volume with a size of 800 megabytes, and we will name it lv_new. And we need to tell lvcreate what volume group that the logical volume will be built on. And we can run lvs to verify our logical volume. Now we can put a file system on our logical volume just as we would a normal partition. Let's create a directory to mount our new logical volume. And then we will add an entry to our etc tab file so that it will be brought up at boot time. Now we will mount our new volume and create a test file there. To grow the logical volume, therefore giving us more storage space to work with, we use the lvresize command. We can increase the size of a logical volume while it is still mounted. Let's increase the size of our logical volume to 900 megabytes. We just give the lvresize command the size that we want to resize our logical volume to. Next, we need to resize our file system. Remember, all we did was increase the size of the container, not the file system itself. We use resize to fs to resize our file system. Next, we can run lvs to verify the size of our logical volume. And we can see that our new logical volume has now grown to 900 megabytes. Now let's shrink the size of our logical volume back down to 800 megabytes. When we shrink a file system, we should first make sure that we have a backup, as any data that is in the area that gets reduced is lost. The next thing we will need to do is unmount the file system. Now we run the file system checker on our logical volume. Next, we will need to shrink our file system with the resize to fs command. Now we can shrink our logical volume. We get a warning reminding us that this could be potentially dangerous, so in the real world, make sure you have a good backup. Again, we can run lvs to verify the size of our logical volume. And we're back down to 800 megabytes. Finally, we can remount our logical volume. Now we can use the df command to show how much disk space we have free on our partition. We will use this with the -h option to show us the output in human-readable format. And we can see that we are right around our 800 megabytes. Some of this data is always going to be taken up by the LVM metadata itself. The LVM metadata is what stores the information about the mount points and extents of our logical volume. We could have used the lvextend and lvreduce commands to complete these tasks, but for the sake of simplicity, we just used the lvresize command. Now that we have a partition set up, we need to get a file system on it. A partition by itself is just a container that we use to hold data, but a file system is the method that an operating system uses to store data within a partition. Red Hat Enterprise Linux supports a variety of file systems. Take a look at the man page for FS to get an idea of the various types of file systems supported by RHEL. We create file systems on a partition with MKFS, short for Make File System. There are a couple of ways that we can call MKFS to create a file system. We can use the -t option to specify the type, such as ext4. ext4, or the fourth extended file system, is the default file system for RHEL 6. The other option would be to run MKFS, then a dot, then the file system type. Then you specify the partition that you wish to create the file system on. In our case, this will be /dev sdb1. Then press enter. And MKFS has finished creating our file system on the partition. If you notice at the bottom of the command's output, we see a message about tune2fs. Tune2fs helps us control how many times a file system can be mounted before a file system check needs to run on it. We will discuss the file system checks momentarily. We can list the parameters of our ext4 file system by running tune2fs /l dev sdb1. The output of the command shows us the UUID, short for the universally unique identifier for the device, when the file system was first created, the last time the file system was written to, how many times it was mounted, and the mount count. Again, the mount count is the maximum number of times a file system can be mounted before a file system check is performed on the drive. A file system check scans for any damage to the file system and attempts to repair any damage. You can run a file system check with the following. However, a file system check should never be run on a mounted file system. Severe damage to data can occur if a file system check is used on a mounted disk. We have not mounted our new partition, so it is safe for us to run a file system check on it. We will demonstrate this. We just run the file system check command with the name of the device we want to scan. Since it is a brand new disk, it came back clean. Take a look at the man pages for the commands discussed in this video. Before we dive into the creation of partitions, we need to briefly discuss some of the different types of disk that we can create partitions on. All system devices are located in the /dev directory, and this is where we will find the hard disk that the kernel has detected on our system. There are quite a few items in here, but the ones that we are concerned with at the moment are the SD devices. As you can see, we have SDA, SDA1, SDA2, and SDB devices. The SDA device is our first SCSI hard disk. This can be read as S for SCSI or SATA, D for disk, and the letter A, which represents the first disk detected. The SDA items that we see here with a 1 and 2 represent the partitions that are configured on this disk. SDA1 is the first partition, and SDA2 is the second partition. The SDB device is our second hard disk, denoted by the letter B. We don't have any partition numbers on here, as we have not created any partitions on it yet. Your system may have HD instead of SD, where H stands for a regular IDE drive. Another option would be VD, where V stands for virtual disk in a LibVirt virtualization environment. Regardless of what type of disk you have, the first letter will tell you what type of disk it is, followed by D for disk, then a letter indicating which disk it is, such as an A for the first disk, B for the second disk, and so on. And if there is a partition on the disk, that will be represented by a number indicating which partition it is. Now let's create a new partition on our blank/dev/sdb disk. We do this with the fdisk command. Then we tell fdisk which disk we will be working on. Fdisk is an interactive partition creation tool, meaning that it is menu-driven. As displayed here, we can press the M key to bring up our menu. But for now, we are going to press the P key. The P key displays the partition table of a disk, and here we see that we do not have one. Now to create a new partition, we press the N key. Next, we get prompted asking us if we are going to be creating a primary or an extended partition. We don't have any partitions on this disk, so we are going to create a primary partition. Press the P key for primary partition. Then we are asked for a partition number. This is the first partition that we are building, so we will use 1. Next, we are asked for the starting cylinder of our partition. We will just accept the default of 1 by pressing Enter. Next, we are asked for the location of the last cylinder. We can press Enter for it to take the whole disk, or we can enter a size in kilobytes, megabytes, or gigabytes, preceded by a plus sign. This is a 1 gigabyte disk, and we only wish to use half of it, so we will enter in plus 500 M for 500 megabytes, then press Enter. Now we can press P again to see our new partition table. Here we have our new /dev/sdb1 partition, our start and end cylinders, our blocks indicating our 500 megabyte partition size, and the last two fields indicate our partition type. To see what types of different file systems we can use on our system, press the L key. Our default file system ID was 83 for the Linux file system, which for RHEL 6 generally refers to the ext4 file system. That will work for now, as we will just leave it at that. We will discuss file systems in more detail in the following video. We haven't actually finished creating our partition yet. In order to do that, we need to write our changes to the disk. To do this, we press the W key, then press Enter. Fdisk has now written our new partition table for our /dev/sdb disk. We can verify this by listing our partitions in our /dev/sdb disk by running the fdisk command with the -L option on the disk itself. And here we see our new partition table. If for some reason you do not see your new partition table, you could reboot the system, or better yet, run the part probe command. This command tells the kernel to reread the partition tables of all of the disks on the system. Take a look at the man page for the fdisk command to see some of the other things you can do with it. You can add more partitions to a disk, delete partitions, and change file system types. Another method of creating partitions on hard disk is by using parted instead of fdisk. Both tools do the same thing, they just have different ways of doing it. You can look up the parted command's man pages if you wish to give that utility a try. You can use either method on the RHCSA exam, so just use whichever tool you are most comfortable with. Oftentimes, a user will need to elevate their current login to that of root in order to perform some system administrative task. There are a few ways of doing this by using su or sudo. Su is mostly used when you want to log into a session as another user. Most of the time, this other user is the root account. From a regular user account, we run su. When we run su, which is an abbreviation for switch user, by itself without a username, the system assumes that we wish to log in as the root user. So let's log in as the root user. Press enter, then enter the root password. Notice how the prompt changes from a $sign to a pound sign to reflect the change? However, if the root user has applications in /root/bin, then by just using su by itself, we will not be able to run any of those commands without specifying the full path to /root/bin. Here's why. If you look at the end of the path environment variable, we are using the bin folder from the user account we just logged in from. If we want to use the full environment of the root user, we need to use su with the dash option. Now let's look at our path environment variable again. See how we are now using the /root/bin directory in our path? This is because the dash option makes the shell a login shell. Review the earlier video about accessing terminals for a refresher on the differences between a login shell and a non-login shell. Most of the time, when you want to switch to the root user, you would do this with su-. There are going to be other times when you, as the root user, would want to grant a particular user or a group of users the ability to run system administrative commands without them using the root account. An inexperienced user with full root privileges could wreak havoc on a server if they were to make a mistake while working with important system files. This way, they can run singular commands and you don't have to give out the root password. We do this by allowing users to run the sudo command. Users are granted the ability to use sudo by having their usernames or groups added to the /etc/sudoers file. We edit this file by using the visudo command. We use visudo instead of editing the file directly since it has built-in error checking to make sure that we don't make any mistakes to the sudoers file. Having a broken sudoers file on our system could cause some serious problems. Let's take a look at the more commonly used directives in this file. The first line that we will look at is the one that allows root to run all commands on this system. You could add a user to this line to allow someone else to have full control on the system. This is generally frowned upon, but there are instances where this might be necessary. Below that, we have an example of allowing a particular group of users to have full access to the system. Below the next directive, we have some examples that use groups to run only certain commands that generally require root privileges. This will be the safer option rather than granting full access to the system, but your needs may vary. For now, we will add our K-Armstrong user to the directive that grants full privileges as an example. Here, we are granting the K-Armstrong user the ability to run all commands on this system. Now, we save the file. Have a look at the video where we discuss Vim if you need some help on editing a file with Vim. And let's log back in as K-Armstrong. Now before, only root could read the /etc/shadow file, but by preceding our command with sudo, we should be able to do the same. As an example, as our K-Armstrong user, we're going to try to read the shadow file, and we can't do it. However, if we precede our command with sudo, we should be able to do so. And we're going to put in our password, and there we go. Notice that after the command has run, we are still on our own account. We were able to read the shadow file without logging in as root. LUKS, or Linux Unified Key Setup, is a partition encryption system. Encrypted file systems are extremely useful in ensuring that the data stored on a user's laptop or removable device, such as a USB key, will be safe in the event that it is lost or stolen. The RHCSA exam objectives specify the ability to create a LUKS encrypted partition and to have it prompt for a password at boot, so that is the example that we are demonstrating here. Do not attempt to encrypt a file system that already has data on it, as you will lose all of the data on that partition. If you wish to encrypt a partition, be sure to back up all data on that partition beforehand. We have already created a new partition that contains no data to show you how this is done. We will be using a brand new /dev/sdb1 disk. To encrypt our partition, we run the crypt setup command. We are warned that we will lose any data that may be on this device. Since this is a new partition, we will continue on and type in yes. We then enter a passphrase for LUKS. And we see that the command has completed. Next, we can open our new encrypted partition with crypt setup and the LUKS open option. The last part of the command, the word safe, is there to give a name to the partition after we open it. We can verify that our new device was opened by checking in the /dev/mapper directory for our encrypted partition named safe. Next, we can create a file system inside our new encrypted partition. Now, let's create a new directory to mount our encrypted partition to. Now, we will mount our encrypted partition to this directory. Next, we need to relabel our SC Linux security context on this new directory with the restorecon command. In order for our encrypted partition to be brought up at boot, we need to edit the /etc/crypt tab file and add an entry for our partition. The first field is the name that we give our device, just like what we did when we opened our device. When the system boots, it will show up as /dev/mapper/safe. The next field is our encrypted device, and the final field is for our password to decrypt our partition. By entering in none, we are forcing the user to enter in the password to decrypt the partition. We could enter in a directory that contains a key file instead. Read the man page for the crypt tab file for more information on how to do that. We also need to modify our /etc/fs tab file to add an entry for this partition to be brought up at boot time. Now we are going to reboot our system, and we should get prompted for a password so that the system can open our encrypted partition. And here we see that we are getting prompted for the password. So we enter in the password and press enter, and the boot process should continue. Now let's verify that we have our safe partition mounted. And there it is. We can check the status of our encrypted partitions with the crypt setup status command. And then give it the name of the device. Take a look at the man pages for both crypt tab and the crypt setup command to learn more about setting up encrypted partitions. We can take the standard read, write, and execute permissions on a file or directory further with the use of ACLs. ACL is an acronym for Access Control List. It is a way for us to further define who can have what rights to a file or a folder. We can use ACLs to deny a member of a group to read a certain file even though the group itself may have full access to the file, or grant another user access to a particular folder even if that user doesn't own that folder and that user isn't a member of the group that has rights to that folder. We need to mount the partition that is going to have ACLs on it with the ACL option. Let's edit the /etc/fstab file to grant this to our /home directory. Now we remount the home partition. And let's check our mounts to verify that we have the ACL option on our /home partition. And we can see that we are ready to set up ACLs on this partition. Now let's log in as K Armstrong and create a directory in K Armstrong's home folder that will contain a file that we want G. Freeman to have access to. Now let's log in as G. Freeman and see if he can read the notes file. As expected, G. Freeman is denied when he attempts to read the file. Let's take a look as to why G. Freeman can't read the file. We will check the file and folder permissions with the getf_acl command. The getf_acl command shows us the basic file and folder permissions and the extended access control list permissions. The output of the command shows that only K Armstrong has full access to the home directory, which is what we expect by default. Remember in a previous video where we stated that in order for a user to access a directory, they need to have the execute bit set to traverse that directory. With the file that we are trying to let G. Freeman read, we need to traverse two directories, the home directory for K Armstrong as well as the review directory. If we look at the permissions for the review directory, the output shows us that others can read and execute the review directory. So how can we grant G. Freeman access to that file? We can use setf_acl to grant the execute bit to K Armstrong's home directory, so that G. Freeman can at least get through that directory. We will not need to set the read bit since we don't want G. Freeman to read anything else in K Armstrong's home directory. Once we can execute the home directory for K Armstrong, we will then be able to traverse the review directory. What we are doing here is we are setting the file access control list for G. Freeman to have execute bit on K Armstrong's home directory. This M right here is just saying that we are modifying the ACL. Now let's take another look at the permissions. We see that only G. Freeman has the execute bit on the K Armstrong home directory outside of the K Armstrong user. Now that the permissions are set up for us to traverse the two directories, we should be able to read the file now. And we see that we can. Just to check that only G. Freeman and K. Armstrong can read this file, log in as Avance and attempt to view it. We can also grant G. Freeman the ability to write to this file with ACL permissions. To remove an ACL entry for a file or a directory, use the -X option without any permission specified. Now let's test it out to see if G. Freeman can read the notes file. File compression is important for system administrators as it is a common means for backing up data and distributing multiple files and folders in a single archive. Compression, or archiving, is important for the distribution of files over a network as it requires less bandwidth to send and receive the files than if they were their normal full size. The most commonly used method for archiving files and folders is with tar. Tar is often used in conjunction with other compression tools such as gzip and bzip2. Let's go ahead and start working with tar. The first thing we will do is run an ls within our compress.me directory. Now say that we want to email the contents of this directory to someone else in our department. We can email files, but we can't email folders. So instead of sending an email with multiple files as attachments, where we have to attach each file to our email, we would rather just email one file that contained all of these other files. Let's start packing these files into a single tar file, also known as a tarball. We start tar with the C and F options, which means that we are going to create a tarball, and the V option means that we want verbose information as to what the command is doing. Here we are specifying the name of the tarball. And now the directory that we are going to add to the tarball. Now run an ls on our new tarball. Well, the tarball size is larger than the files added up individually. That's where compression comes in handy. We can compress our tarball using gzip compression with the following command. Now let's do an ls on our directory. And we can see that we now have a stuff.tar.gz file in there. The .gz extension was automatically added by the gzip command. If we do an ls-lh on our stuff.tar.gz file, we can see that the file size has been significantly reduced. We went from 20 kilobytes down to 3.7 kilobytes. We could have also performed all of the above in one step by invoking gzip compression with the tar command like so. Note the addition of the Z option. That's what invokes the gzip compression. Also, it is common to find tarballs named something like this. This is the same thing as stuff.tar.gz, just with a different extension. We can list the contents of our tar file with tar-tf stuff.tar.gz to see the contents of the file. To use bzip2 compression instead of gzip, just replace the z option with a j and add bz2 to the end of the archive name. And here's our bz2 tarball. If you notice, it's essentially the same size as the gzip tarball. Now, we'll copy our tarball to the root user's desktop directory. Now, we will extract our tarball on the desktop. The X option is what extracts our tarball. And here we have all of our files. We could do the same thing with the bzip2 tarball by replacing the z with a j. So in other words, the command would look like this. And we would end up with the same results. One of the oldest methods of transferring files on the Internet is through the File Transfer Protocol, or FTP. Red Hat Enterprise Linux uses the very secure FTP daemon as the default FTP server software. To set up an FTP server, we will first need to install the vsftpd application. Once we get the package installed, we can take a look at the default configuration file for the FTP server located at etc vsftpd vsftpd.conf. Here, we can see that by default, this server allows anonymous access, which means that anyone can access this FTP server without logging in to download files. By default, we are allowing users that are configured on the local system to use their local accounts to log in. We will demonstrate this shortly. Also by default, we are allowing write commands for the FTP service, meaning that people can create files and folders on the FTP server. Below this, we see some more directives relating to the anonymous users. The first one allows an anonymous user to upload files to the FTP server. This directive will only work if the above directive for allowing write commands on the FTP server is set. We will leave this directive commented out as we will not be allowing anonymous users to upload to our server. The next directive is allowing anonymous users to create directories on the FTP server. We won't allow this, but this is where you should configure that should you need to. Now let's go ahead and quit our FTP configuration file. Now we will set up our FTP server to start at boot time and start the FTP service. Next, we will need to open up the port for FTP in our firewall, which is port 21 with the TCP protocol. Now, let's verify our firewall port is open. And here we see that it is. Now, we're going to jump over to our other system and try and access our FTP server. We will use the lftp command to log into our FTP server. Let's list the contents of the user's home directory. When we log in as a regular user, we seem to have access. However, when we try and list the contents of the user's home directory, we are getting a login failed message. Why is that? Let's jump back to the FTP server to see what we can find out. We have already verified that the FTP service is running and the FTP port is open, so why can't our user log in? Let's take a look at the SC Linux audit logs. If we page up in our output, we can see that SC Linux has denied us access to the user's home directory. Remember before when we were discussing SC Linux booleans? Well, here is an instance where we need to set one. So according to the fix, we need to set the boolean to allow FTP access to the home directory. Now let's go back to our other system and try and run the ls command again. We can now list the contents of the directory. Let's upload a file to our remote home directory. We can use the put command to put a file on the FTP server. Then run an ls on the FTP server to verify that we uploaded the file. And we can see that we did indeed upload the sent up file. Now let's take a look at something else. If we do an ls on the root directory, we can see all of the system folders. There are security implications to this, since someone could copy down important system files. In our next video, we will show you how to prevent a user from accessing the rest of the FTP server's file system through the FTP connection. To prevent a user from listing the FTP server's file system contents through an FTP session, we can put the users in what is known as a chroot jail. Chroot is a way to specify a particular directory as a user or system's root directory, preventing them from browsing anything else outside of the specified directory. To do this, we will need to add another directive to our vsftpd.conf file. Let's jump back over to our FTP server. Now, back on our FTP server, let's uncomment the directive to chroot local users to their home directory. We will use the chroot list enable option and set it to yes so that vsftpd will read a list of usernames to put into a chroot jail. Now, we need to create a new file called the chroot list that has a list of usernames that will be dumped into a chroot jail when they log in through FTP. The chroot list is created within the etc vsftpd directory. Let's go ahead and add both the root user and the karmstrong user. Then save the file. Now we need to restart the vsftpd service. And let's go back to our other system and see if we can still see the full file system's contents of the FTP server when we FTP into the server. Now all we see is the user's home directory. Now onto anonymous FTP access. A user can log into the FTP server as an anonymous user with the following. As for a password, the common convention is to enter in your email address, but this is not necessary unless the server enforces it. If we do an ls while logged in as anonymous, all we see is a directory called pub. This is the default directory that an anonymous user sees. This is set up automatically during the FTP service install. Commonly, content that is made publicly available to users will be stored in the pub directory for anonymous users to download. Let's change to the pub directory to see what is in there. And there is a file called getme. We can run the lcd command to change to our desktop directory on our local system. We get confirmation that we did change the directory on our local system. Now we can download the getme file. And we can see that our getme file has in fact been downloaded to the user's desktop. Let's go back to the FTP server to see where this pub directory is located. Back on the FTP server, let's take a look at the /var directory. We can see that we have an FTP directory under var, so let's see what is in there. And there is our pub directory that the anonymous user sees. So when an anonymous user logs in, they actually log into the /var/FTP directory. Let's take a quick look at the SE Linux security context for the /var/FTP directory. An anonymous user would fall into the world or other category of user permissions, and we can see that other has read and execute permissions, and our security context is set to public content T. Keep this in mind if you need to set up the anonymous login to be able to upload content. You will need to make sure that the proper permissions are in place and that your FTP configuration file has the directives set to allow anonymous uploads. Lastly, but certainly not least, make sure that your SE Linux booleans are correctly configured to allow anonymous access if you need to enable anonymous upload. I recommend that you practice this on your own. Look up the man page for the vsftpd.conf file to see some more of the various options and directives that you can use to configure the FTP server. In this video, we are going to take a quick look at some avenues of assistance that are available to you while you study for your exam. While studying for the RHCSA exam, you should always consult the documentation that is on your local system first. This documentation includes the man and info pages and any sort of help or README files available in User Share Doc. Also, be sure to review comments within any script or configuration files. We brought up the local system documentation quite a lot throughout this video series as we wanted to get you in the habit of checking there first in case you needed a reminder on how to perform a command or just needed a bit more information on how some things worked. We also recommend that you keep the official Red Hat Enterprise Linux deployment guide open in a web browser while you study. You can find the full deployment guide for RHEL 6 at the link below. You can also ask for some help on the various forums listed here. If there is a task outlined in the official exam objectives from Red Hat that you need help on figuring out, ask someone on any of these forums to see if they can help you. Do not expect to get an answer to a direct question about the RHCSA exam's content, as that would be a breach of the agreement between any certified Red Hat system administrator and Red Hat. I would recommend starting with the CentOS forums. Since CentOS is a rebuild of Red Hat Enterprise Linux, any method that would work on CentOS will very likely work just the same on RHEL. You could also try the Fedora forums. Just keep in mind that Fedora is constantly in development and contains newer software. It is quite possible that what would work in Fedora would work in RHEL, but there could be some differences in the software between the two distributions, so something might not work the same between the two operating systems. The Linux questions and Linux forums are also great sites to visit. Just be sure to mention the fact that you are working on a RHEL 6 or rebuilt system, since members of these forums use many different versions of the Linux operating system. Sometimes you may find others that are studying for the same exam, and they might have set up an online study group. If you can't find one currently, you could try and start your own and invite other forum members to join you. There are also a few mailing lists that you could subscribe to. Keep in mind that when you post to either a forum or a mailing list, that you describe what it is exactly you are attempting to accomplish, and the version of the operating system that you are trying to work with. Always be cordial and patient. Since these are free resources, no one is obliged to respond. However, with this being the open source community, chances are you will get helpful answers for your questions. If you are familiar with IRC, which is an acronym for Internet Relay Chat, you could log into any of these channels to see if anyone would be willing to assist you. The RHEL channel is specifically for discussions about any versions of Red Hat Enterprise Linux, but keep in mind that this is not an officially supported channel by Red Hat. IRC channels tend to be full of lots of chatter, so be clear and concise when posting your question. Also, remember to be patient. IRC chats often move quickly, but that doesn't mean that you were ignored. Someone has quite likely seen your question, and they may be working up a response for you. These are just some of the ways that you can seek help while you study for the RHCSA exam. Don't forget that you have other resources available to you, such as a local library or bookstore and online search engines. If you know of someone else who has already taken the exam, see if they would help you study. But above all, practice as much as you can. The exam is built on experience, and the more experience that you have with working with RHEL, then you will have a greater chance of success with the exam. Groups are an essential means of organizing users on a system. Groups provide a means to securely grant access for certain users to resources on a system. As you will see with a later video, we can use groups to create a collaborative directory within which they can work together that they all have rights to. Groups are created on the system with the group add command. We will create a new group called research. We run group add and give it the name of our group. Now, with the user mod command, we will add our advanced user to this group. We use the -G option to add advanced to the research group as a supplementary group. On a Red Hat Enterprise Linux system, each user on the system primarily belongs to a group with the same name as the username. So with the user mod -G option, we are setting them up to be in their own private group as well as any supplementary group that we add them to. In order for the new group membership to take effect, the user must either log out of the system then log back in, or run the new group command like so. In Advance's case, she would run new group and then research. Without logging out, the user can run the new group command with the name of the new group that they were just made a member of. Now, let's switch to Advance's account and check what groups that she is a member of. We do this with the groups command. As you can see, we have verified that she is now a member of the research group. We can also add new users to a supplementary group at the same time as their account creation with the user add command. Now, let's check T-Mention's account out. And again, we now have T-Mention in the research group with Avance. We can modify some group attributes with the group mod command. Let's say that the members of the research group wish to have the group name changed to researchers. We can do this with the following. The -N option grants us the ability to assign a new name to the group. We can also change the group ID for the group with group mod. By default, all new users and groups have their IDs start at 500. We want our users to remain in the 500 range, but have our group ID start at 1000. So here's how we change the group ID for our researchers group. Group mod -g 1000 for researchers. We will use the ID command to verify this. ID for the user Avance. As you can see, the researchers group is now at group 1000. The ID command will show you what user ID and group ID that a user is a member of. You could also run the ID command by itself to check what group IDs pertain to your account. A non-root user can be granted the rights to add other users to a group that they are an administrator of. For instance, the root user can set up a particular user to be the administrator of a group. Then that group administrator can add and remove users from that group as they see fit. This would be useful for managers or department heads. Let's walk through such a scenario where the advanced user is to be set up as the group administrator. We use the "A" option with the gpasswd command to allow Avance to be the researcher's group administrator. Now, we will switch to the Avance account and add the K Armstrong user to the researcher's group with Avance acting as group administrator. The "A" option is used to add non-administrative users to a group. Only the root user can use the "A" option. To delete a group, we use the group del command. For our example, we will just say that the researchers group has been disbanded. We can remove the user supplementary group membership with group del space researchers. We can use the same graphical tool that we use to manage users with to also manage groups. Go to System, Administration, Users and Groups. Click on the Groups tab to see the groups currently on the system. We can click on the Add Group button to create a new group, and to also assign it a specific group ID. Let's create a new group called Management with the group ID of 1001. To add members to this group, click on the Users tab, highlight a user, then click the Properties button. We can then click on the Groups tab and select the new group that we created to add this user to that group. To delete a group, click on the Groups tab, highlight the group, and then click the Delete button. One of the RHCSA exam objectives is the ability to set up a directory for group collaboration. In this example, we will create a working directory for the research group. The first thing that we will need to do is to create a new directory for the group. Let's create a research folder under the /home directory. Now, let's grant ownership of the folder to just the research group. We can do this by specifying nobody as the user in our chown command. The next step will be to assign the proper permissions to the directory. We will do this with the chmod command. Let's explain this command. We have zeros set for the user owner since no one single user will have ownership or exclusive rights to the directory, and we grant full rights to the group. We are also denying any permissions to others. But what is this 2 all about here in the front? This is what is known as the SGID bit. The SGID bit, or the Set Group ID bit, is a special flag that forces the process that executes the directory, such as copying, moving, or creating files in the directory, to be owned by the group, and not the user's group that performs the action of creating a file in the directory. Notice the S in place of where the execute bit would normally reside in the group permissions. That is the indicator that we have the SGID bit set. You could do the same thing for a user account by setting a bit called the SUID bit that forces a process to be run as the owner of the file or program. This isn't exactly a safe setup though, as a regular user could run a command as if they were root if the SUID bit were set on a file or an application that is owned by root. Instead of using a 2 in the first octal position of a file's permission for SUID, you would see a 4. Now back to our collaborative directory. We should be able to log in as any user for the research group and create files and folders in the /home/research directory that will be owned by the research group. Let's try it. And here we can see that K. Armstrong has created a folder in the research directory that is owned by the research group. Let's create a file in there. And again, the file that we just created is owned by the K. Armstrong user, but because we did it inside the research folder, it is owned by the research group. Now we will log in as A. Vance, since she is also a member of the research group, and she should have the ability to read and modify the same file. There we go. A. Vance and K. Armstrong can work in the research folder together. Let's make sure that a user that is not a member of the research group cannot access this directory or these files. And just to verify, let's take a look at the groups that T mentioned is a member of. As you can see, he is not a member of the research group. So let's see if he can access any of the files that belong to the research group. And of course, T-Mention is denied access, since he is not a member of the research group. And that's all it takes to set up a collaborative directory. It's just that easy. The default bootloader, Grub, consists of two stages. The first is the small application within the master boot record or the boot sector of the hard disk. The second stage is loaded from the boot partition on your file system. This is the stage that you see when your system boots and you see the Grub menu screen. The first stage of Grub is created during the operating system installation. It exists in the first 446 bytes of the hard disk that contains the boot sector. The first stage is executed by the BIOS, and its purpose is to find the Grub configuration file located at boot grub.conf. Should you ever need to repair a Grub installation, you can do so with the grub install command. The second stage of Grub is located within your boot partition of your file system. If you are using LVM on your system, then the boot file system will be located on a separate partition, since at this point Grub does not support booting from an LVM partition. Let's take a look at our Grub configuration file. At the top, we can see a notice indicating that since we have a boot partition, that Grub was going to refer to our boot hard disk as HD 0,0. If we look below that, we see that our boot disk is our /dev/SDA device. Next, we see a directive for our default boot stanza. The 0 means that we are looking at the very first Grub stanza to boot from. Below this, we see our timeout directive. This value is for the amount of seconds that will pass before the default entry in the grub.conf file gets booted. You can change this value to whatever you want. Let's quickly see what constitutes a Grub stanza. Each stanza begins with the word title. We can see that our first titled stanza is for the CentOS Linux installation, followed by the kernel version number. Below this, we see which hard disk we will boot from. Next, we have our kernel line, showing the file name of the kernel, followed by all of the kernel options that our system will use to boot with. The last line of the stanza is where our initial RAM disk file is located. This is the file that the kernel uses at boot time to load device drivers and initial scripts that are used to start the system up. Below this, we have another stanza containing another kernel version. We will reboot the system so that we can see what else we can do with grub. Press a key to enter the grub menu. Here we are presented with the grub menu. These menu entries are made up from the stanzas that we just saw in the grub.conf file. We can use the arrow keys to select a different kernel to boot from. Just highlight an entry and press the Enter key. We can also edit a kernel entry from the grub menu to modify how the system boots. Let's try this. Press the A key to modify the booting kernel's arguments. Here we can see the full line of kernel arguments that we saw in the grub.conf file for this kernel. Let's take out the arguments for RHGB, which is short for Red Hat Graphical Boot, and the quiet argument. We are doing this so that we can see all of the system messages during the system boot up that the default progress bar hides from view. Then press the Enter key to boot the system. Now we can see all of the system messages from the kernel while our server boots. You can make changes like this permanent by editing the same information in the grub.conf file. Well, what if you don't want anyone else modifying the grub menu before a system boots? You can password protect your grub menu to prevent such modifications. To do this, we use the grub md5 crypt command. Then enter in the password that you want to use to protect your grub menu. Then, take the MD5 hashed password and copy that into our grub.conf file. Enter a new line right above the first title and input the following. Then paste in your encrypted password. Save your file. And now we will reboot our system. We pressed a key to enter our grub menu, but now we are told to press the P key to enter in a password for us to unlock the other features of grub. Press the P key, enter in your grub password, and press enter. And now we can modify the kernel boot arguments. To learn more about grub, look at the info pages for grub itself. Along with the command line tools available to manage LVM volumes, we also have the System Config LVM graphical tool. Many Linux administrators prefer the command line way of doing things, but I must confess that this is one application that can save you some time on the RHCSA exam. System Config LVM isn't installed by default, but you can get it with the yum command. We access this tool from the System Administration Logical Volume Management. After System Config LVM refreshes its view, we are presented with an overview of the first volume group on the system, usually the one that contains the root file system. The top blue bar represents the volume group and the individual logical volumes within that volume group. You can click on these logical volumes and it will highlight the portion of the physical device, represented by the red bar below, that directly maps to the logical volume. Over on the right-hand side, we can see more details about the volume group itself. To find more details on the logical volumes, drill down in the Logical View menu and click on any of the individual logical volumes. On the right-hand side, we can now see more details about the logical volume, such as the size of the logical volume, the mount point for it, and the file system it contains. Beneath the view of the logical volume, we have buttons that will allow us to remove the logical volume, create a snapshot of it, or edit the properties of the logical volume. If we click on the Edit Properties button, we can see where we can change the name of the logical volume, grow or shrink it, or change the file system or the mount point. If we go up to the physical view, we can drill down and see how the disk is partitioned for the logical volumes. With the buttons below, we could remove the disk from the volume group or migrate the extents on this volume group to another physical volume. Below all this, we have our uninitialized entities. Some volumes cannot be initialized, such as /dev/sda, since it has our /boot partition on it. Others we don't want to initialize for LVM, since they are regular partitions that contain data, such as /dev/sdc1, which holds our sales mount point. We do have a new blank disk at /dev/sdd that we can initialize and use though. To set this disk up to be part of a logical volume, we first need to click the Initialize Entity button. We are prompted with a warning reminding us that we will lose any data on the disk. This is a new empty disk, so we click the Yes button. Next, we are advised to have the whole disk set up with a single partition. We will take the advice and click the Yes button. The disk is initialized, and System Config LVM reloads. Our /dev/sdd device now shows up as an unallocated volume. When we highlight the disk, we are given options to create a new volume group, add the volume to an existing volume group, or take the disk out of LVM altogether. We will add this volume group to an existing volume group so that we can increase the size of the logical volume that the home directory sits on. We click the Add to Existing Volume Group button, and we are then prompted with a list of possible volume groups. We will choose the 6200 volume group, which holds our home partition. Then we click the Add button. The volume is added to the appropriate volume group and the application reloads again. Now if we click on the volume group that contains our home directory, we can see that we have some unused space available. We can occupy that unused space by increasing the size of the original logical volume. Expand out the logical view, then click on the logical volume that holds the home directory. Then click on the Edit Properties button. Since we have added a 1 GB volume to this group, we have the option of using the full remaining space available, or by using the slider or by entering a value in the LV size field. We can specify how much more space we want the logical volume to occupy. Let's click on the button for Use Remaining Space. We can see that the slider and the value now occupy the rest of the available space. Click the OK button, and the logical volume gets resized. Back in the overview, we can see that the logical volume now occupies both disk and has expanded out to 2 GB. We can go back to the logical volume and shrink it as well. Let's reduce the size by 200 MB. Drill down to the logical volume and press the Edit Properties button. Let's reduce the size by 200 MB. Then click the OK button. We are prompted by an information box telling us that the logical volume will have to be unmounted for this task to be completed. Press the Yes button. The logical volume is reduced, and the application reloads. A hard link or a symbolic link are essentially shortcuts to a file or directory. To understand the differences between a hard and soft link, it is important to know what an inode is first. An inode, short for index node, is an entry in a file system table that references a file or directory. Some of the data within an inode includes information such as the file or directory's permissions, the location on the file system where the file or directory resides, and more. An inode is referenced by its inode number. We can view a file's inode with the following command. The number to the far left is the file's inode. Now, let's see how this ties into hard and soft links. A hard link is a pointer to a file's inode. The inode for a hard link and the file it references is the same. Let's create a hard link from our vim-test file in the root user's home directory to the desktop folder. We do this with the ln command. Now, let's see what the inode numbers are. And we see that the inodes are the same. Next, we will create a symbolic link. A symbolic link, or soft link, is a file that points to another file, so both files will have a different inode. We create symbolic links with the ln command with the -s option. Be sure to use the full path of the source and target for a symbolic link to be created. For example, now let's compare the inode numbers. As expected, we have different inodes. Now, let's see what happens when we move the vim-test file over to the desktop folder and try to access it from the links. So why did the hard link work and not the soft link? Because the hard link is pointing to the exact inode where the data resides. The soft link was just pointing to the original file, which in turn was pointing to the location of the data. When that file was removed from the root user's home directory, the soft link didn't have anything to reference anymore. Another difference between the two types of links is that hard links cannot be accessed from a different file system. However, a symbolic link can cross file systems. Here is an example. First, let's move our test file back to the root user's home directory. We get an error telling us that we cannot cross disk devices. Now let's try a symbolic link. And we can see that a symbolic link does the trick when you need to reference something across file systems. The best documentation on the system for links are in the info pages. To view this documentation, run the following. We already know that the kernel manages all of the hardware on the system, so what can we use to query the kernel to find detailed information about our hardware? Red Hat Enterprise Linux comes with a variety of tools that we can utilize to parse this information. Knowing particular details about the system's hardware can be helpful in troubleshooting driver issues or hardware failures. Oftentimes, a hardware vendor may need to know the exact make, model, and firmware version of an installed piece of hardware to assist with troubleshooting an issue. The first command we will look at is the dmessage command. The dmessage command prints out the contents of the var log dmessage file. This file contains the details of the system hardware detected by the kernel. The output is rather long, so we will pipe it to the less command. As you can see, this is some rather in-depth information about the hardware the kernel detects during boot up. What if you only want information about certain areas of your system, such as your PCI bus? For that purpose, we have the lspci command. The lspci command will just show the basic information about the devices connected to your PCI bus. If you want to know what kernel modules are loaded for a particular piece of hardware, we can use the -k option. Here, you can see the PCI device itself, and below that the kernel module that has been loaded to work with that particular device. We can also view all of our system's USB device information with the lsusb command. By itself, the lsusb command displays the USB buses on the system and any devices that are connected to it. We can also view our USB buses and devices in a tree mode, showing the hierarchy of how the devices are connected. One other command that we have available to us is the DMI decode command. The DMI decode command lets us look at detailed information about the various components of our system, such as our CPU, the RAM we have installed, the system BIOS, the installed motherboard, and more. The DMI decode command by itself will display everything by default, but we can query for specific hardware devices by specifying its type. We do this with the -t option. Let's look at the details of our CPU. And here we can see some detailed information about our processor, such as the manufacturer, the speed, and some other details. Another command that we can use to find out some details about our processor is the x86 info command. And we are presented with a brief overview of our processor. Take a look at the man pages for the commands presented here to see some of the other information that you can learn about your system's hardware devices. In a later video, we will take a look at the files that these commands parse this information from. It would be pretty difficult to memorize every option for every command. However, Red Hat Enterprise Linux includes some built-in command line tools that will help you in finding more information about the commands you use. Two that we will discuss here are the man and info pages. Nearly every command on the system will have a man or manual page associated with it. We can look up a command's man page with the man command. We just type in man, then the command that we wish to know more about. Just like the less command, we can scroll up and down using the J and K keys. The man pages contain a brief synopsis of what the command does, all of the options associated with it, and sometimes an example on how to use the command. If you have an idea of what it is you're looking for, you can search for a particular word or option in the man pages by using the / key. Let's look for the -L option. We can then jump to the next instance of the -L option with the N key. We can also search backwards with the question mark key, $-L. And just use the P key to go to the previous highlighted instance. Just like in less, you quit the man pages with the Q key. If you are not sure what command you should run for something, but you know of a keyword that could be associated with a particular command, you can use the following command to search through the man pages on a system to find a man page related to what you are looking for. Apropos is used to search through the manual page names and descriptions and returns man page listings that could be related to what you are looking for. Let's try an example. Let's say we want to see what man pages are available for SE Linux. To find out what man page could point us to the command that we would use to set an SE Linux boolean on an object. We will go over SE Linux in a bit more detail in later videos. And then just press enter. And here we go. We should read the man page on the set SE bool command. You may notice the number 8 off to the side of the man page result. That is there because the man pages consist of different sections. The number 8 refers to man pages that are pertinent to system administrative tasks. The number 1 refers to commands available to regular users, such as ls. The number 5 refers to specific file formats and configuration files. These are the main pages that a system administrator would be concerned with. Not all man pages will have different sections. For instance, the ls command doesn't have a section 8 since that command has no special features for system administrators. Another option that many commands have is the --help. This will give you a quick look at how a particular command should be constructed. Let's take a look at the set SEBool command again, this time with --help. Here we are given a brief review on what to use with the command. There is another tool that we can use to get help at the command line, and that tool is the info pages. The info pages are formatted a lot like the man pages, but sometimes the info pages will contain information that is not in the man page. We invoke the info pages like so. Just type in info, space, and then a command that you're looking for information on. Let's take a look at the info pages for the cp command. Just like in the man page, we get a quick synopsis as to what the command is used for. To look around the info pages, use the arrow keys. As you can see, there is a lot of information in the info pages for the cp command. On your own, compare the info pages for the cp command to the man page for the cp command. Just note that there isn't an info page for every command, but most often you will find one for most common commands that you could use. To quit the info pages, just press the Q key. Another objective of the RHCSA exam is the ability to set up and configure a default web server. Red Hat Enterprise Linux uses the Apache web server to serve up web pages. The Apache daemon is named HTTPD. The first thing we will need to do is install the HTTPD package. We could do a group install of the web server group, however, that will pull in a bunch of dependencies that you will not need on the exam. It is best to just install HTTPD by itself for the RHCSA exam, as your exam time is limited. After we get our web server package installed, we will take a look at the configuration file for our web server. This is located at etc httpd conf httpd.conf. This is a very large configuration file, but there are a few main directives that we are concerned with. The first is the document root directive. The document root directive tells the HTTP daemon that the main location for the web page files are located at var www html. The next main directive is the directory directive. This should match the same location as our document root directory. So let's test out the basic default setup of our web server. Go ahead and start the HTTPD service. Don't forget to enable it to start up at boot time. And let's go ahead and open up our firewall port for TCP port 80, which is the default port for web services. Now let's open a web browser and navigate to HTTP localhost. And we should be able to see the default Apache test page. So there we go, we have a working basic web server. Now let's create our own test page in the default web directory at /var/www/html. When setting up a test page to be viewed from your web server, do not be concerned with trying to develop a page in HTML. You could just create a file with basic text in it and the browser will still display it. Time is of the essence on the RHCSC exam, so don't waste any by trying to display any prowess in web page development. Make sure that your default web pages are titled index.html unless told otherwise during the exam. Now just refresh the page in your browser and you should see your new page. We can also test our website out from the command line using the eLinks terminal web browser. We will need to install eLinks since it isn't installed by default. To use eLinks, just type in eLinks and the page you are trying to see. And here we see our test page. Press the Q key to exit eLinks, then enter to confirm. In our next video, we will see how to serve more than one website from our web server. The Apache web server has got a great feature called Virtual Host that will allow us to serve up more than one website from the same server. In this video, we will configure our server to host more than one website. First thing we need to do is to modify our etc host file so that we can have our website domain names point to our local server. We are doing this for the purpose of this video. Follow the instructions on your exam for your particular setup. Now we will create our two directories that will house our two websites. Before we go further, take a look at the permissions on these two directories. We can see that only root has write access, and all others have read and execute permissions. This is important, as we wouldn't want anyone else to modify our web pages. That is partly how websites get hacked. Also, look at the security context. We have the httpd sys content t context set up, so SE Linux knows that the HTTP daemon is supposed to have access to these resources. If this security context is not set properly, your website will not work. Now let's add our two new websites to our httpd.conf file. The first thing that we need to find is the directive for virtual host. Start with section 3 of this configuration file to find information on virtual host. Scroll down to find the directive that enables virtual host. Uncomment the line for virtual host. This will give us the ability to use the names of our websites so that when a request comes in for a particular website, Apache will know where to go on our server to find that website. Now let's enter in our first virtual host. Now scroll down a little further to find an example of a virtual host website. we will create our virtual host below this section. We start the virtual host container with the following. Next, we tell the virtual host container what site we are trying to access, along with the port number. Next, we will enter in our document root directive, which tells the server where the files for this website are located. If you notice that in the example above, they are using a different directory location for their document root location. However, not only does that directory not exist, but we would have to manually set a security context for that location as well in order for SE Linux to allow the HTTP daemon access to that directory. Since we are staying within the default web directory, we are ensuring that our permissions and security contexts are correct. Next, we need to include our server name. Now, we need to include our log locations. Make sure that you follow the syntax above for the logs to work properly. Finally, we close out our first virtual host container. Now let's go ahead and configure our second virtual host. Now we save and close our file. We can verify the syntax of our httpd.conf file by running the following command. Now let's reload our configuration for the HTTPD service. Next, we need to create the content for our two new websites. Now let's go to our web browser and see if we can view our new sites. And there we go. We have multiple sites from the same web server. In an earlier video, we saw an example of output redirection by sending input to the cat command out to a text file. We are now going to work further with input and output redirection. Let's create another text file to use as an example with the cat command. And again, the input that we are putting into the cat command will be redirected to the in-out file. And the EOF indicates that we are finishing the file. Now, using output redirection, we can append the output of the hostname command to this file using two greater than symbols together. We are running the hostname command, and we are going to append the output of that command to our in-out file. Now, let's take a look at the in-out text file. And we see that the hostname of our system has been appended to the file. If we had only used one greater than sign, then we would have overwritten our file with the hostname command. Let's see that in action. Now let's take a look. And we can see that all of the text in the file was overwritten by the output of the hostname command. We can combine input and output redirection to a single command. We have a file that has some misspelled words in it. Here is how we can use the spell command, which is a spelling checker, to verify the spelling in our file. Here, we are sending the spelling.txt file into our spell command, as indicated by the less than arrow, and redirecting the output of the command to the misspelled.txt file. And here is the listing of our misspelled words. Another use of output redirection is sending standard error output to another file. For instance, let's see what happens when we try and look for a file that we don't have. We end up with the error message displayed below. What if we had a script that ran on the system that was supposed to show the listing of files when a bunch of them don't exist? That could fill up our console in a hurry depending on how many files we're missing. We can redirect the standard error output to another file with the following. The 2 with the greater than sign means that we only want the errors redirected. Let's look at our output.txt file. We can see that the error message was sent to this file instead of our terminal. This is useful for scripts where you would run a command and you wanted a log of the error messages that were created in the event of an error. Another method of input-output redirection is piping commands together. With the pipe character, we can string multiple commands together, creating a single complex command. A very common example of this use is by combining commands with grep. We will cover grep further in a later video, but we are using it to search for a particular word here. We are using cat to display the contents of the etc/sysconfig/network file and sending that output to be the input for the grep command, which is only searching for a line of text that has host in it. And our output is displayed below, showing the host name of our system and excluding the rest of the file. Now, we are going to install a Red Hat Enterprise Linux system using the Kickstart file that was generated from our other computer. We will be performing this from a network location. You can use a Kickstart file from a CD, hard drive, web location, FTP server, NFS server, or even a USB device. The basic syntax between each of these methods is the same. You will just need to modify the location of your Kickstart file itself. In our example, we will install from an NFS server. First, we boot the install media, and then we press the escape key. At the boot prompt, we put in our Kickstart installation instructions. We're specifying Kickstart here. Our Kickstart file is at an NFS server, which is located at this IP address. And the NFS folder that is being shared out is at /serve/NFS, and our Kickstart file itself is ks.cfg. You'll notice that we have a shorter name for our Kickstart file. We just renamed it on our server to save us a little bit of typing. Next, we press enter, and the installation DVD will boot our system. Network Manager is going to give us an IP address on our ETH0 card, is contacting the NFS server. And now the installation will actually begin. As you can see, our partitions and our logical drives are being created along with the file systems, as dictated by our Kickstart file. And again, we are providing no input here. All of this is being read from our Kickstart file itself. Now it is checking our Kickstart file for all the packages and the dependencies that it will need to install them. And the installation process continues. Now all of the packages that were configured in our Kickstart file are being installed in our system. And now our installation has finished, and we can reboot our system. And there we go. We have a brand new Red Hat Enterprise Linux server completely installed with very little input from us. In this video, we are going to take a look at what virtualization is and how it is set up in Red Hat Enterprise Linux 6. Virtualization is a method that allows us to run multiple virtual machines on a single server. Virtualization has brought about the means to cut some cost in data centers by reducing the amount of physical servers needed to run various services. This has saved on hardware cost and energy costs since not as many physical servers are needed and less energy is required to cool server rooms. Each virtual machine is known as a guest system. The server system that runs all of the guest systems is known as the host server. The software that this host server runs is known as a hypervisor. There are a lot of hypervisor software systems on the market today, such as VMware and Microsoft's Hyper-V. There are two main ways that virtualization is done. The first is known as full virtualization. Full virtualization utilizes features from the CPU of the host system, and the guest system is unaware that it is a virtual machine. The guest system is configured as if it is on a bare metal system. The other method is known as paravirtualization. Paravirtualization requires software modifications to the guest system, usually in the form of network and hard disk drivers. Since there are other drivers involved that help the guest communicate better with the host, the guest system is aware that it is a virtual machine. However, with the additional drivers, paravirtualization often provides better performance. Red Hat Enterprise Linux 6 utilizes KVM, or the kernel-based virtual machine, as the hypervisor software stack. KVM is the open-source software platform that offers full virtualization out of the box. Through the use of a set of drivers developed specifically for KVM, known as the VirtIO drivers, KVM can also be used as a paravirtualization hypervisor. In order to run KVM on your host system, your CPU must be either an AMD 64 or Intel 64 class processor. KVM supports both Microsoft Windows and Linux guests from many distributions. On a KVM system, each virtual machine is treated as a single process. There are multiple tools available to manage a guest on a KVM system. The first that we will discuss in a later video is the Virsh command line toolset. There is also a graphical toolset called VirtManager. Both Virsh and VirtManager are front-ends to the libvirt system, which is the set of libraries that KVM uses on a host system. There are a lot of other Virt tools available, but they are not covered on the RHCSA exam. I've listed a few here. Feel free to install these and use them on your own. In order to use KVM on your system, you must first make sure that you have a 64-bit processor as stated earlier, and that your processor has the appropriate CPU flags to support virtualization. Run the command shown here to see if your CPU qualifies. If you get output after you run the command that includes either VMX or SVM, your system is good to go to run KVM. If you don't get any output, then you will need to try another system. To install KVM on your RHEL system, it's easier to just do a full group install to get all of the necessary packages. Once you get the packages installed, make sure to enable the libvirt-d service and have it started prior to working with any guest systems. A KVM guest consists of two main components. First, you have the guest XML file, which contains hardware assignments such as how much RAM the guest will use, how many virtual CPUs it has, where the virtual hard disk image files are located, and lots of other information. The second component is the hard disk image file themselves. These will be formatted in either RAW or pre-allocated formats or the QCal file format. Both image files will end in the .img file extension. We will discuss the differences between these two file formats in a later video. The XML files are located in etc, libvirt, qemu, and then the name of the guest followed by .xml. The hard disk image files are located under var, lib, libvirt images. Be sure to check the security context of these files, as SE Linux does play a role in virtualization. To learn more about virtualization in RHEL 6, I recommend that you look at the official documentation located at the URL listed below, and take a look at the man pages for the commands that we will cover shortly. NetFilter is the standard firewall system for Linux. We control the configuration of NetFilter with the iptables command. You do not have to be a wizard with iptables to pass the RHCSA exam, as you should be able to complete any necessary firewalling tasks with System Config Firewall. However, we are going to look at the basics of iptables to give you an idea of what is going on behind the scenes when you use the System Config Firewall utility. First off, let's take a look at where our current firewall rules are stored, and we will walk through this file discussing how the rules work. Our iptables rules are stored in etc sysconfig iptables. By default, we are just filtering the packets that are going through our system. This is our filter table. The other three tables in NetFilter are the NAT, Mangle, and RAW tables, but we are not too concerned with those for the RHCSA exam. Our iptables rules consist of three chains: the input chain, the forward chain, and the output chain. The input chain is for processing packets that are coming into this system. By default, we are accepting all packets that come into our system to start with. The forward chain is intended for packets that would be routed through this system and not intended to be delivered to it. By default, we are accepting all packets that get forwarded through this system. The output chain processes packets that originate from this system. By default, we are accepting all packets leaving this system. Now on to where we have iptables rules that are doing more processing on the packets that traverse our system. First off, we are appending to our input chain, using the state method, any packets that have a state of established or related. In other words, connections that are already up and running. We will take those packets and jump over to our accept chain, meaning at this point we are letting them in. Next, we are appending to our input chain any packets of the ICMP protocol, such as those sent by ping commands. We will also take those packets and jump over to the accept chain, letting those packets through as well. Next, we are appending to our input chain any packets that are intended for our loopback interface. We will take these packets, and by jumping to the accept chain, letting those packets through as well. See how this works? iptables rules can almost be read as sentences, describing what happens to packets that meet certain criteria. This next rule is more in line with the types of rules that you would modify for the RHCSA exam, that is opening ports for services. This rule is defined as we are going to append to our input chain any packets that have a state of new that matches the protocol, TCP, and that are destined for port 22, we will accept. This rule allows us to use the secure shell services to access this system. Next, we are rejecting any other packets, therefore blocking any other connections to this system. Not only are we rejecting them, we are rejecting them with the ICMP host prohibited message. Finally, we are rejecting any packets that are attempting to get forwarded through our system. We are not running a router, so this rule is acceptable. These IP tables rules are processed from top to bottom. If a packet meets a certain rule, the other rules following are not checked and the packet is dealt with according to how the rule is configured. For example, any packets coming into the system that are of the ICMP protocol, we accept, and the following rules do not need to be checked. We could modify this file, even though at the top it instructs us not to. The reason for that is if we modify this file, then open it up in System Config Firewall, all of our changes that we made by hand would be lost. So if you intend to alter your firewall by editing this file, make sure that System Config Firewall is not used again on the system to change any firewall rules. If that is the case, the safest bet would be to uninstall System Config Firewall. Let's add a rule to allow port 80, used for web traffic, to come in. The easiest way is to copy a line that is similar to what you want to do. Since we want TCP traffic on port 80 to come in, let's copy our rule for the SSH service that is also using TCP traffic to a certain port. Next, paste it below our current rule for SSH. Now we just change the port to 80. Then we save, then close the file. Now, even though our new rule is in the etc sysconfig iptables file, the port still isn't open in our firewall. We will need to restart our firewall for the new changes to take effect. We will do this with the service command. Now, to check to see if our rule is in place, we will run our first iptables command, which will list for us all of our current rules that are loaded into memory. And we can see that our firewall now has the port for HTTP or port 80 open. Now we are going to take a look at the iptables command itself and some of the basic tasks that we can accomplish with it. In a previous video, we demonstrated how to view the current firewall rules with the iptables-l command. If you are testing something, such as a new server install, and you believe that your firewall rules are blocking something that you need opened, you could flush out your rules with iptables-F. Just be sure to restart your iptables service so that you have your firewall back up and running properly after you have finished your troubleshooting. To modify firewall rules with iptables, we just run the iptables command, followed by options that specify what we want to do with the packets as they come in. If you remember from our previous video, our firewall instructions in the etc sysconfig iptables file were appending new rules to each chain. However, if we use iptables to add new rules outside of this script file, it is best to insert new rules rather than append them. The reason for this is that our new rule would get appended to the very end of our input chain, which would put the new rule below our existing rule that rejects all other traffic that doesn't match any other rules before it. In this case, our new rule would never get checked since the rule before it rejects any packets that doesn't match the previous rules. By inserting our new rules, they will be put in the proper table above the final reject rule. Let's open port 21 for FTP traffic in our firewall. We are using the -I option to insert and not append our new rule to make sure it gets checked before the final reject rule. Now let's check to see if our port is open. And here we see that our new rule is now in place. We will simulate the system restarting by restarting our iptable service. And let's take a look at our rules. Our FTP port is no longer open. That is because when we use IP tables, we are only modifying the rules that are on the running system. As soon as we restart, our rules get flushed, and the only rules that get used are the ones that are read from our etc sysconfig IP tables file. In order to make the rules stick, we will need to reopen our port. And then save the new rule with the service command for IP tables. Now we're going to check our rules out again. And here we see that our FTP port is open again. Then again, we restart the system. And let's verify that the rules stuck this time. Great, our port is still open. Now let's say that we are no longer running an FTP server on this system, so we need to close the port for FTP. We can do this by deleting the rule for port 21 like so. Then we make sure that the port is no longer open. Which looks good, so we'll save the new configuration. All we did was run the same command as before, except that we used the -d option to delete the rule as opposed to the -i option, which inserted the rule. I highly recommend that you read through the IP tables man pages to round out your understanding of how IP tables works. Do not overburden yourself with every option. Just be familiar with what you could do with IP tables at the basic level. Kernel modules are the drivers that your hardware needs for communications with your system's kernel. They also allow for the kernel to work with your particular file systems. These modules are loaded by the kernel dynamically, meaning that they are not loaded unless they are actually needed. To view the currently loaded kernel modules on your system, run the lsmod command. The output can be rather long, so we will pipe it to the ls command. The output is read from left to right, with the name of the module first, then the amount of memory the module is using. The next column is for the amount of processes and/or other modules that are using this particular module, and a list of the names of the other modules that are using this particular module. For instance, we can see that the CD-ROM module is dependent on the srmod module. Well, what is the purpose of the srmod kernel module? We can find out with the modinfo command. Just type in modinfo, then the name of the module we want to know about. According to the output, it is a SCSI CD-ROM driver. Well, let's say that we only needed the CD-ROM driver from when we did our system install. However, while the system is up and running, we don't need the CD-ROM anymore since we will be performing any updates or new software installs over the network. We wish to save some system resources, so we decide to remove the CD-ROM driver for the time being. We can remove a kernel module with the modprobe command and the -r option. The modprobe command is used to load kernel modules and any dependent kernel modules. We use the -r option to remove kernel modules and their dependencies. We are using the -v option for verbose output. Next, we tell the modprobe command which modules we wish to unload. And if we run the lsmod command again, we can see that we no longer have the CD-ROM drivers loaded. Well, now we need the CD-ROM driver loaded again since we need to install some software that we only have on a disk. We don't want to reboot the system, which will reload the CD-ROM driver automatically, so let's do this with the modprobe command. And just enter in the name of the driver or module we want loaded into the kernel. And if we check the output of our lsmod command, we can see that the srmod module is loaded along with the CD-ROM driver. To see what kernel modules you have on your system, run the following command. We are using the output of the uname-r command instead of typing out the full kernel name here. It is a lot quicker just typing in one command that you can easily remember rather than trying to type out the full kernel version. Here we can see our subdirectories for architecture, cryptography, device drivers, file system drivers, and so on. Take a look around on your system to see what is installed. It isn't very often that you will need to work directly with kernel modules, but it is beneficial to know how to load and unload modules in the event that you have a buggy driver that is causing instability to your system. The RHCSA exam assumes that you already know how to perform a basic Red Hat Enterprise Linux installation from CD or DVD. However, one of the exam objectives for the RHCSA certification is the ability to perform an automated installation with Kickstart. Kickstart installations are performed using files that contain instructions on how the system should be set up. A Kickstart file automatically gets created by the Anaconda installer at the end of a RHEL installation. This file is saved in the root user's home directory at /root and is called anaconda-ks.cfg. You can create a Kickstart file by hand or with the system config Kickstart utility in Applications, System Tools, and Kickstart. This application is not installed by default with a RHEL system. However, it is quite easy to install it after you get your system up and running. We will take a look at our Kickstart file to view its contents. In our Kickstart file, we can see that the installation was performed from a CD-ROM device, that the keyboard and the language was set to English US, that our network was enabled, and device ETA0 was set up with DHCP with no IP version 6. The root user was created and its password was encrypted. The firewall service was started with the SSH port opened. We are using shadow passwords for our authentication. SE Linux was set to enforcing mode. Time zone was set to American New York for the Eastern Coast. And we have our bootloader installed to the master boot record. Below this section is our information for our hard drive and logical volume layout. You will notice that these directives are commented out. The reason for this is in case we want to use the same Kickstart file again on another system that may not have the same exact hard drive layout. The installation repository was set to Red Hat Enterprise Linux, which was actually on our CD-ROM device. The Packages section lists all of the software that we will have installed on our system. The lines that begin with an @ symbol indicate a package group that is installed. These lines are for individual packages that get installed. The lines with a dash before them means that these packages will be excluded from the install. Let's go back to the section about our hard drive information. We're actually going to uncomment these lines, as we will be using this Kickstart file to install another RHEL system with the exact same hardware setup. We will be performing this task in a later video. Save our file. The system config Kickstart utility can actually be used to modify an existing Kickstart configuration file. As you can see, the fields have been pre-populated with the information that exists in our Kickstart file, along with the partition information that we just uncommented. Note that if you do not include a directive for installing a graphical desktop environment, then the first boot service will not run after this installation has finished. In this event, you will need to manually add a user to the system, since by default, a Kickstart file only creates the root user. We can easily add a new user into our Kickstart file with the user directive. The simplest place to put this directive is right below where the root user gets created. We do this by putting in user, name for the actual username, and the user password. And then we save this file, and we will be able to use this kickstart file to set up a brand new RHEL system with the user for Kenny and the password pass123. For further information about the Kickstart file, you can visit fedoraproject.org/wiki/anaconda/kickstart to find a full listing of all different types of options and directives that you can put in your Kickstart file. You can also visit the web page for the Red Hat Enterprise Linux 6 installation manual that also has a section on Kickstart options in Chapter 32.4. In this video, we are going to discuss the Linux kernel, which is the core of Red Hat Enterprise Linux. Understanding the basics of the Linux kernel is the key to understanding how Linux works as a whole. The Linux kernel was started by Linus Torvalds in April of 1991 while he was still a student at the University of Helsinki in Finland. In October of the same year, Linus posted a message to the Minix news group on Usenet that he was starting a free operating system based on his kernel. After that, many people joined him in the effort. 3 years later, version 1.0 of the Linux kernel was released. In 1996, version 2.0 was released, and in 2003, version 2.6.0 was released. RHEL 6 is using the kernel from this branch with a multitude of patches and updates. As we already stated, the Linux kernel is the heart of the operating system. Since the kernel is the heart of the operating system, it is responsible for these tasks. First off, the kernel is responsible for the system startup, which we will elaborate on more in a later video. The kernel is also responsible for all of the system's process scheduling and priorities. All of the network functionality originates from the kernel. The system's memory management is coordinated by the kernel. And the system security is handled by the Linux kernel through the NetFilter firewall system, SE-Linux, and file and folder permissions. The Linux kernel's version numbering scheme is broken down into first the major kernel version, a dot, then the minor version, a dot, then the patch version. Red Hat takes the version numbering further by including a dash, then the build number, followed by an EL number representing the version of Enterprise Linux that the kernel is for, a dot, and finally the CPU architecture. You can see what version of the kernel that you are currently using by running the uname-r command. Also, remember that when you go to update your system's kernel that you install a new one and not upgrade it, as an upgrade will overwrite your currently installed kernel. We discussed this issue in more depth in our video about updating the system kernel. The Linux kernel is a monolithic kernel. What that means is that the operating system is running in the kernel space. The Linux kernel loads device drivers and file system drivers from what are known as kernel modules, and these modules are loaded dynamically. That means that the only modules that are loaded are the ones that are needed for your particular hardware and system setup. You can see what kernel modules you have on your system by listing the contents of the lib modules directory. All of the kernels that you have installed on your system are going to be located in the /boot directory. The kernel names begin with VM-linux since the kernels are contained in a compressed image file that gets decompressed during the system boot process. When the system boots up, the kernel creates the /proc, /sys, and /dev directories. The /proc directory is where you will find the running system processes and any kernel parameters that you can modify. The /sys directory is where you will find your detected system devices and details about their device drivers. The /dev directory is where the access points for your devices are stored. This is what the file system uses when working with your system disk. In the following videos, we will take a look at some of the tools that we can use for working with the Linux kernel. The RHCSA exam expects the candidate to be able to create new physical volumes, assign physical volumes to volume groups, and be able to extend unencrypted logical volumes. We are going to briefly discuss LVM before we begin working with logical volumes. LVM is short for Logical Volume Manager. It was first developed by Hewlett-Packard for the HP UX operating system. LVM is the default volume management system in Red Hat Enterprise Linux. LVM uses a collection of disks. A single volume can span multiple disks, and not all disks need to be the same size. That's one of the strengths of LVM. Each disk is referred to as a physical volume, and physical volumes are collected into volume groups. A volume group can then be split into logical volumes. and logical volumes are what contain the file systems. Here is a diagram illustrating the different layers that make up LVM. At the bottom, you have the physical volume, which is just a converted physical disk, such as in this case /dev/SDA1 and a 30 gig disk over here of /dev/SDB3. These physical volumes are then grouped together in a volume group. This one here named volume group 01 for a total of 40 gigs, adding the 30 gigs from here and the 10 gigs from here. We can then split this volume group into two separate logical volumes, each one containing 20 gigabytes, logical volume 01 and logical volume 02. You can then create a file system on these logical volumes and then mount them to particular directories, such as this logical volume getting mounted to the /var directory and this logical volume getting mounted to the /home directory. LVM allows for online resizing, which reduces system downtime. Physical volumes and logical volumes are broken up into chunks of data, called extents. Logical volumes can be grown or shrunk by either increasing or decreasing the extents used, or by increasing or decreasing the amount of disk space used. And you can specify either megabytes, gigabytes, or other sizes for how big or how small you wish the logical volume to be. LVM provides the ability to create volume backups through what are known as LVM snapshots. A backup utility can read the data from the snapshot, negating the need for the live file system to be halted while the backup is run. This way, you don't have to worry about any extra system downtime. A couple of things to note about LVM is that the /boot partition cannot be a logical volume, since Grub cannot read LVM volumes at this time. Volume groups are located at the /dev/mapper directory, and that there are a plethora of command line tools and a great GUI tool known as systemconfig LVM that makes management of logical volumes easy. We will be demonstrating these commands when we create our logical volumes in the remaining videos. One of the really great features of LVM is the ability to take snapshots of a logical volume. A snapshot is a block device that is an exact copy of a particular logical volume frozen at the point in time that the snapshot was created. Snapshots are often used in conjunction with backup solutions, so that data can be backed up without being concerned with taking the file system offline. The first thing we will do is copy some data over to our new logical volume. Next, we will create a directory that we can mount our snapshot to. Next, we will create the snapshot of our LV-new logical volume with the following command. We use the lvcreate command, which is the same command that we use to create a logical volume, but with the -s option, which indicates we are creating a snapshot logical volume. We are giving the snapshot a size of 100 megabytes. Your LVM snapshot doesn't have to be the same size as the logical volume that you are taking a snapshot of. The man page for the lvcreate command suggests creating a snapshot logical volume with the size of roughly 15 to 20% of your original logical volume. We are giving this snapshot a name of LVM snapshot, and finally we tell the lvcreate command what logical volume we are taking a snapshot of. And here we can see the new logical volume, which is a snapshot of our LV-new logical volume. Say that another administrator removed the RPM file that we had saved in root's home directory, and he also deleted the copy from the /extra directory. Yet we still need that RPM for an install we have to perform. We can go to our latest snapshot of the logical volume that the extra directory sits on and attempt to recover it. To do this, we mount our snapshot like we would with any other disk. We will mount it to our /mount/snapshot directory. And we can see the data that we copied over to our /extra directory earlier. Now we can copy the RPM file back over to the /extra directory. And our lost RPM file is recovered. To remove a snapshot, we will need to unmount it. Then we delete our snapshot logical volume with the lv-remove command. And the LVM snapshot logical volume is now gone. Now, before we use our new file system, we will need to discuss how to mount file systems. To use a file system, we will need to have it mounted, which is a way of saying that the disk is brought in to be used with the operating system. When we mount a file system, we need to have a directory mapped to it since we save our files in directories. Let's take a look at how this is done. First, we will create a new directory to mount our file system to. Now, we need to map this directory to our /dev/sdb1 device. To do this, we run the mount command. Then we need to tell it what type of file system we have. Next, we will need to tell the mount command what device we are mounting. Finally, we need to tell the system what directory this device will be mounted to. We will use our new test directory. Then press Enter. Now, we should have our new disk with a brand new clean file system mounted to our new directory. Let's run an ls on it. Notice the lost plus found directory? This directory is created on each file system automatically. The purpose of this directory is to be the storage location for any files that are recovered by the file system check utility after it has been used on a damaged file system. This feature is a nice safety measure to rescue files that may otherwise have been lost. Let's copy our etc host file to the new directory. We can view a list of our currently mounted file systems with the mount command. And here we can see that our /dev/sdb1 device is mounted to our new directory. To take a file system offline, say in the event that we need to run a file system check on it, we use the umount command. We can unmount our new test directory with the umount command, then the name of the directory. And our new file system is unmounted. We can verify this with the mount command. And we no longer see our /dev/sdb1 device. However, the test directory still exists. Remember, we only mounted our new file system to the test directory. Let's copy a file over to the test directory. And we see that our file is in the test directory. Watch what happens when we mount our new file system back to the test directory. The file that we just copied is no longer visible, but our lost and found directory, along with a copy of our host file, is there. The other files still exist, but the file system has been mounted over the /test directory. In order for the new file system to be brought up automatically when the system boots, we will need to add an entry for it into our file system table file, located at etc fs tab. As you can see at the top of the file, there is a list of man pages that you can look at to find further information on the directives used in this file. On the far left, we have our devices, listed either by UUID number or by the device item as listed in the /dev directory. The bottom 4 items are temporary file systems that the system creates at boot time. When the system is shut down, these bottom devices no longer exist. The next column is the directory that the file system will be mounted to. The next column is the file system type. Then we have the mount options. The next field is for the file system dump command, and the final field is for the file system check command to determine the order in which a file system gets checked when the system boots. Let's add a new entry for our new disk. First, we enter in our device. Next, we enter in our mount point. Next, we specify our file system. We will just use the default mount options. Finally, we will allow the dump command to work with the file system, and we will allow the file system checker utility to check this system should it need to. Now we save the file and we reboot the system. Our system has come back up, so we run the mount command to verify that our new file system is there. And we check our files. As well as knowing the networking tools created by Red Hat, it is beneficial to know some of the more commonplace Linux command line tools for viewing and adjusting network settings. Note that if Network Manager is running, it would be best to stop that service, otherwise they will interfere with the commands we will use here. We used ifconfig in a previous video, but now we are going to look at it a bit more. ifconfig is the old IP configuration tool that has been used in Linux systems for years. ifconfig by itself will display the current interfaces that are up and running. ifconfig-a will display all of the interfaces on a system, whether they are up or down. We can also assign an IP to an interface with the ifconfig command like so. We assign a new IP address to the ETH1 interface with the subnet mask listed above. Now let's use the ifconfig command to take a look at ETH1. And we can verify that our IP address that we assigned is now there. Keep in mind that any IP address configurations made with this command will not survive a reboot. If you need for any changes that you have made to be permanent, you will need to modify the network scripts that we will discuss in a following video to store your IP settings. The ifdown command does just what it says. It shuts an interface down. By default, our ETH1 interface is brought up when the system boots, but for now, let's just shut it down. This is done with the ifdown command and an ETH1. And if we do an ifconfig, we no longer see ETH1 in the output. We could make this a permanent change by running ifdown ETH1 boot. That would keep the interface from coming back up on system reboot. To bring an interface back up, we can use the ifup command. Let's bring our ETH1 interface back up. Just like with the ifdown command, we could use ifup, then the device name, and then boot to have the device come back up automatically at reboot. We can use the route command. to view our current routing table. We can also add static routes with the route command. Since our configuration here shows that we do not have a default gateway, let's use the route command to add one. And we will make sure it uses our ETH0 device. Now let's take a look at our routing table again. And there we go. We now see that we have a default gateway pointing to the IP address that we just set up, and it is using ETH0. Now we're going to take a look at the IP command. IP is a newer command line tool to work with network interfaces. It is meant to be a replacement for the old ifconfig command along with the route command. We can do any of the previous commands we just saw with the IP command just by changing some options. To view our currently configured IP addresses for our interfaces, we run the following command: IP address show. And here we can see our local loopback, the IP address associated with that, our ETH0 interface, along with the IP address associated with that, and our ETH1 interface, and the address associated with that. Instead of running the route command, we can use IP route to view our current routing table. And just like we saw before, here is our default gateway via the 192.168.75.2 address through the ETH0 device. We can also view current interface statistics such as drop packets or connection errors with the following: IP-S and then link. This is useful in helping to determine if we have a faulty cable or network card by looking at the amount of errors or drop packets. Read the man page on the IP command to learn more about it. You won't need to know all of the options for the RHCSA exam, but you should know the ones discussed in this video. The final command that we will look at is the dhclient command. The dhclient command is used to get an automatic IP assignment from a DHCP server on your network. Let's use dhclient to get a DHCP IP address on our ETH1 interface. We just run dhclient and then the name of the interface. And let's see what IP address we ended up with. We quickly went through a lot of networking commands in this video. I would suggest reading the man pages on each one and practicing them on your system, especially the IP command, since it is the preferred command on Linux systems nowadays. Before we dive into configuring network settings on our Red Hat Enterprise Linux 6 system, we are going to first quickly go over the basics of the different types of network interfaces you would encounter. We are going to run the old standby ifconfig command to take a look at our network interfaces. We will cover more network command line tools in a later video. This command displays our network interfaces, the IP addresses and subnet mask for each interface, the state of the interface, telling us if it is up or down, and some other useful information. The default network interface is LO, or the loopback interface, whose IP is 127.0.0.1. As long as networking is properly installed on a RHEL system, this interface will exist. The next interface is our ETH0 device. This is our Ethernet interface, and the first Ethernet interface is always notated as ETH0. We do have more than one Ethernet interface, as we can see with ETH1, but if we had more than that, then we would have ETH2, ETH3, and so on. Another network connection that you could encounter is a wireless connection, denoted by WLAN0 for the first wireless card and WLAN1 and so on for each additional card. You will probably not see this very often on a server system, however you could run into it on a laptop or a desktop that has RHEL installed and is being used as a workstation. On Red Hat Enterprise Linux 6 systems that have virtualization installed, you may see the VMnet 0 interface set up as well. This is a NATed interface for virtual machines that a RHEL 6 system would host. We will cover virtualization in Red Hat Enterprise Linux in later videos. Another network interface that you may see on a Red Hat Enterprise Linux system is the PPP or point-to-point protocol interface. Any of these network interfaces will be configured in script files located in etc sysconfig network scripts. Let's take a look at these files. As you can see, there are quite a few files in here. For now, we are just going to concern ourselves with the ones that have our networking devices currently set up. Let's take a look at our local interface first, which is configured in the ifconfig-lo file. The first directive is for the device, which actually gives us the name of the device that we see in the output of commands such as ifconfig. Here we have our IP address and our subnet mask. We want this device to be started up when the system boots, and an alias for the device. Now let's take a look at our ETH0 device. Again, we have a device name, where this one is for ETH0, and we also have an nm control directive. This is asking if the Network Manager service is handling this device. Our ETH device is being handled by Network Manager. We will go over Network Manager in a later video. Our device will be available when the system boots. It is an Ethernet device. And we have a boot proto directive. This is for the boot protocol for the interface. Our device is set to none, since Network Manager is handling the device. But other options would be DHCP for automatic IP configuration, or static for static IP configurations. This line says that networking services will not start for this interface if there is no IPv4 network available on ETH0. Below this, we have our IP address, our MAC address, and our default gateway, along with our DNS IP. Most network scripts will have similar settings. Now we are going to take a tour through the file system locations of where network scripts are stored and briefly discuss the main ones. Let's jump into the etc sysconfig directory, which is where Red Hat-based distributions save the majority of the network scripts. The first script we will discuss is a simple one, the etc sysconfig network script. Basically, this script just tells a system that networking is enabled and the hostname of the system. The next script we will look at is the etc sysconfig IP table script. We will discuss IP tables and the Linux firewall in later videos, but in brief, this is the file that stores all of the firewall rules for the system. As we discussed in an earlier video, the script files for the network interfaces are stored in the etc sysconfig network scripts directory. Not only does this directory contain all of the configuration files for our individual interfaces, but this directory also contains the scripts that commands such as ifup and ifdown use to manipulate the interfaces. The etc resolve.conf file is the original location for where DNS servers were configured on a Linux system. Even though Network Manager contains the same information in the ifconfig scripts, it is also stored here since many applications use this script file. The etc host file is the local host file. This file contains the hostname of the system and resolves it back to its local loopback IPv4 and IPv6 addresses. You can also add other systems to this file if you do not run an internal DNS server and you wish to resolve their hostnames to IP addresses. The drawback to this is you would have to have the same file on each system on your LAN in order for everyone to resolve the same information. It is much easier to have a DNS server as a central location for all hostname requests to be sent to. That is a lot of network script files. Now you can see why it is much easier to use the tools such as Network Manager and System Config Network to modify the majority of your system network settings. To learn more about the sysconfig script files and options that you can use in them, look at the documentation here. Since Red Hat Enterprise Linux is primarily a network operating system, it is very important to possess basic network troubleshooting skills. Let's walk through an example where a user is trying to get to Red Hat's homepage. For some reason, we are unable to get to the home page for Red Hat. And we are not able to access the website at linux.com either. Let's check the status of our networking service. Well, we are not using Network Manager, but we are using the regular network service, and our ETH0 device is active. Let's verify that we have an IP address. And we see that we do have an IP address configured on our ETH0 interface. Let's see if we can ping the website for redhat.com. The ping command lets us send ICMP packets, which are packets that will let us know if a connection is up, to the destination we specify. And we are not able to ping the website. Could it be that we cannot resolve the website's fully qualified domain name to its IP? Let's check our DNS settings in the etc resolve.conf file. And we do see that we have a DNS server there at 192.168.75.2. Let's make sure that we can communicate with that server. And we can. So let's make sure that our DNS server can resolve the domain name of redhat.com to its IP address. We will use the dig command, which is part of the bind utils package. Dig lets us query a DNS server for various types of DNS records for a particular domain. And we can see that our DNS server can in fact resolve the redhat.com domain name. So we know our network service is running, we have an IP address, and we can resolve the website for redhat.com, but we can't get to it. However, our DNS server is on the same subnet as our system here. Let's make sure that we can get outside of our local subnet. We will try the traceroute command next. Traceroute lets us check our routing to a particular destination and shows us all of the network hops along the way. Well, we didn't get very far, did we? And there is that message again stating that the network is unreachable, which is what our ping command told us earlier. Let's have a look at our routing table. We have a route here for our local subnet, which makes sense since we can talk to our local DNS server. And we have an automatically generated IP address for our ETH0 device, which gets created on an Ethernet interface whether it has a connection or not. But we don't see a default route here. Let's see if that is the cause of our problem by adding a default route. And let's double check our routing table. There, now we have a default gateway. Let's try and ping the website again. Now it responds to ping. Let's check with our web browser. And now we can get to the site again. However, we only added our default route in memory, so while the system is running, we will be able to get to the internet. We need to check our network script files to make the change permanent. Well, our gateway is configured here. So let's check the configuration script for our ETH0 interface. Look at that. The directive for our gateway is empty. Let's enter our gateway IP address. Now let's restart the network service, and we should be able to still access the website. and we can still get to the web page. We took a long route to solve this problem, but we did that with the intent of showing you some of the various networking tools that you can use to troubleshoot your system's connectivity. Introduced with Red Hat Enterprise Linux 6 is the new network connection utility called Network Manager. It replaces the older application known as System Config Network. However, you can still install and use that instead of Network Manager. Network Manager makes it easy to connect to various networking services. It can handle standard wired network connections, wireless connections, and it makes it simple to connect to a variety of VPN services, such as OpenVPN. It can even handle mobile broadband connections such as 3G. The Network Manager applet generally shows up on the top right-hand side of the panel. By right-clicking on the applet, here we can enable Disable Networking, enable Disable Notifications, show current connection information, and edit our connections that Network Manager will handle. By clicking on Connection Information, it'll show you the basic details of your current network connection, such as your MAC address, your IP address, and so on. Again, by right-clicking and going to Edit Connections, this is where you manage your network connections with Network Manager. Here, we can edit our current wired Ethernet connection, our system ETH0 connection, by first highlighting the connection name and then clicking the Edit button. This is where we can set the connection to be connected automatically anytime that Network Manager starts, configure further security settings, and here we can actually set up our IP information for our particular connection, either through DHCP connection or by manually entering in a static IP. To do this, you just highlight Manual, click Add, and enter in your static IP information. Enter in your subnet mask and your gateway. You can then enter in your individual DNS servers. For multiple DNS servers, just put a comma between each one. Network Manager will actually assist you with what you need to know for each particular field just by putting your mouse cursor over the field and a tooltip will display. To actually change this connection, you'll need the root password. And we have now changed our IP for this connection. By clicking on the Wireless tab, we can enter in a wireless connection. Click the Add button. Give it a meaningful name. Generally, giving it the same name as the SSID will help you identify which network you are connecting to. You can enter in your SSID information, the type of wireless security that your wireless connection will use. For instance, we shall use WPA. You could put in your password. And if you're going to set it to be automatic with DHCP, or again, using a manual IP setting for your connection. As stated earlier, you can set up a mobile broadband connection, work with any type of VPN connection, or connect directly to a DSL connection. The Network Manager applet makes it easy to connect to any type of connection. To get a list of current network connections that are available or configured with Network Manager, left-click on the Network Manager applet to display a list of those that are available. On our current system here, the only one we have set up is just our ETH0 connection under our wired connection. However, with a wireless connection, you will see multiple listings through here with different SSIDs. NFS, short for Network File Services, is a way to share out files over a network. Red Hat Enterprise Linux 6 supports NFS versions 2, 3, and 4, with NFS version 4 being the default. You can mount a remote NFS share on your system as if it was a local disk and access files and folders from it. If you know the IP or host name of the NFS server, you can use the show mount command to see what shares are available on it. The -E option shows us the exports, which is what a shared NFS directory is called, on the server specified by the IP listed. And here we can see that the path to the share is at /serve/NFS. This is on the NFS server itself. The star character indicates that everybody has access to this share. Once we have located the share that we are supposed to have access to, we can mount it to a local directory with the mount command. Let's first create a location to mount the NFS share to. Now, let's mount the remote share with the following command. We run the mount command, telling it that the file system type we are accessing is NFS. Then we put in either the IP or the hostname of the NFS server, then a colon, followed by the share path that we found in the output of our show mount command. Next, we tell it what local directory to mount the share to. And we can verify that the NFS share has been mounted by running the mount command. Now we should be able to access the share, and if the permissions are properly set on it, we can also create and delete files on it. To unmount the NFS share, just use the umount command. We can also set up an NFS share to be mounted when the system boots. Here is how we set that up. We use the _netdev option rather than defaults here. The netdev option tells the mount command to wait for the network services to come up prior to mounting the share. Otherwise, the system could get hung up trying to mount a resource it can't access if the network is not yet available. And since this is a remote file system, we will not be running a file system check on it. Now, when the system reboots, the NFS share will automatically get mounted. In a later video, we will see another way of automatically mounting an NFS share. The RHCSA exam expects that you know how to set up an NTP server. NTP is an acronym for Network Time Protocol. The NTP service is a way to keep a system's time in sync with that of upstream or higher stratum time servers. Keeping correct time is important for system logs, authentication services, and for making sure that all systems on a network have the same timestamps. The easiest way to get started with configuring an NTP server is to first go to System Administration, Date and Time. The first thing we should do is select the checkbox for Synchronized Date and Time over the network. Here, we are given a default listing of NTP servers that we can use as our upstream time providers. Click the OK button, and the NTP service will be started. Now, our system is set up as an NTP client. Now, to configure this system to be an NTP server for other systems on your network, we will need to first modify the NTP configuration file. This file is located at etcntp.conf. scroll down to the line that allows hosts on the network to communicate with our NTP service. Then uncomment the line that begins with the word restrict. Next, enter in the IP range of your network. Leave the other options as they are, then save and close the file. Next, verify that the NTP-D service will start at boot time. Finally, make sure that we have our TCP port 123 opened up in our firewall so that other systems can communicate with our NTP service. To configure your other systems to use your new NTP server, you will need to open up the date and time utility on those systems. We're going to show you the one on the local system so you can see how this is done. On the other systems on your network, click the Add button and then enter in the hostname or IP address of your new NTP server. Then click the OK button. That's all there is to it to configure an NTP server. This is one of the easiest tasks you could complete on the RHCSA exam. Along with the great command line tools that we have available to us for managing software on a RHEL system, Red Hat has also included the Package Kit application for the graphical environment. To access Package Kit, go to System, Administration, and then Add and Remove Software. On the left-hand side, we can use the search bar to search for any available software. To see what packages are available for text editors, we will enter Text Editor. Then press the Find button. On the right-hand side, we see all of the available text editors that our currently configured repositories contain. All of the packages are listed in alphabetical order. The items that are shaded are packages that we do not have installed, and if we scroll down, we can see that gedit, which has a check mark box next to it and is highlighted, indicates that we have this package installed. To learn more about a particular package, just click on it and a summary of the software displays below, along with more detailed information about the package itself is displayed to the right. We will install the Emacs text editor. Just put a check mark next to Emacs. We see that the box icon is now highlighted and has a plus sign over it, indicating that we are about to add this package to our system. To install it, press the Apply button. And here we see an example of dependencies that will need to be installed along with our Emacs package for Emacs to work properly. Click Install, and the package gets downloaded and installed. The list of packages has been updated, and if we scroll down, we can now see that Emacs has been installed. To remove a package, just uncheck it and press the Apply button. We are prompted with a list of the software that we are about to remove, and once we have verified the list, we click the Remove button. Again, the list of software gets updated, and if we scroll down, we should now see that Emacs has been shaded, proving that the package has been removed. To browse all available software that we could install, click on All Packages to see what is available. Let's install the SC Linux Sandbox utilities. Scroll down to it, put a check mark next to it, and click the Apply button. Again, we are prompted with a list of the packages which are dependencies for the Policy Core Utils Sandbox package. Click the Install. If we attempted to install this package with the RPM command, we would have to hunt down each one of these packages and install it in turn for the Policy Core Utils-Sandbox software to function properly. Since Package Kit uses Yum, all of our dependency resolution is handled for us. We can also search for and install software based on a particular purpose. For instance, on this system, we can drill down in databases and see that we have software for installing a MySQL database server available to us. On the right-hand side, we can see all of the packages that are intended for that purpose, and we can then select from those and install them based on our needs. Your system may have more categories available, such as servers, virtualization, etc., but your configuration may vary. We can see our Yum repositories that are configured for our system by going to System and Software Sources. Here, we can just put a check mark next to any repository that we wish to use or uncheck those that we do not wish to use. You can learn more about PackageKit by clicking on the Help button on the bottom left. Password management is another essential skill for a system administrator. Password controls that are enforced on any system is a good way to help maintain system security by locking out users that no longer need access to the system, as well as to keep current users safe by having them change their passwords on a periodic basis. Going back to our user add command, we do have the option of setting a password for a user when we create the account with the -P option. Here, we are creating a brand new user, known as new user, with the password of test123. By default, if user add is used without the -P option, the account is disabled until a password is set. Any regular user on a Red Hat Enterprise Linux system can change their own password. This is done by the passwd command. However, only root can change the password for everyone on a system. Since we're logged in as the root user, let's change the password for the K Armstrong account. Just use passwd space K Armstrong. Then we'll enter in a new password. And the password has now been updated for the K Armstrong user. We can lock a user's account with the passwd command as well. The account will still exist on the system, and none of the user's files will be removed. However, the user will not be able to log into the system. To lock a user's account, we use the -L option. And we can see that the account for K Armstrong has now been logged. To unlock the user's account, use the -U option. And the account has now been unlocked. As an extra administrative measure, we can set password aging on a user's account with the change command. By default, there is no expiration setting for a user's password on a Red Hat Enterprise Linux system, but with the change command, we can put such a policy in place. Here is the command that we would use to set a password's age to a maximum of 90 days. We enter in change, -M, 90, and then the username. With the -M option, we set the password for the K Armstrong account to be good for only 90 days. Before the 90 days have passed, the K Armstrong user will need to change their password to keep the account current. Change can be useful if you have a temporary user that will require access to a system until a certain date. To set an expiration date on a user's password, we can do the following. The -E option will set the K Armstrong password to expire on May 25, 2012. We can check the password age policy on a particular user with the -L option. And here we can see all of the policies that have been set up for the user account for K Armstrong. Only the root user can set an expiration date on a password, but a regular user can check their own password aging with the change-L command. Also, the change-L command is a good way to check to see why a particular user may not be able to log in, even if they are entering their password properly. If the password has expired, then the password must be changed by the user. An administrator could extend the password expiration by one more day to give the user a chance to change their password. To keep a user from being surprised that their password is about to expire, we can set a number of days prior to the password's expiration for a user to receive warnings that their password is about to expire. This is done with the -W option. and let's use the change-l command to take a look at the new password settings. 2 days prior to the expiration date of the password, the K. Armstrong user will get warnings that their password will soon expire. The final topic that we wanted to go over with regards to the system startup involves the different ways that we can shut a system down. We already know that we can use the desktop environment to shut down our system. But there are a few ways of doing this from the command line as well. We have already seen that we can reboot a system with the reboot command. And now that we know the different run levels, we could even reboot our system by invoking run level 6. For shutting down the system from the command line, we have a couple of ways of doing this. We could invoke run level 0. The problem with that command is that no one is warned that the system is about to be shut off if anyone else were logged in, so someone could lose data that they haven't saved to disk yet. The better option would be to use the shutdown command. The shutdown command lets you reboot the system, shut it down, schedule a system shutdown, and you can send a message to other users logged into the system that the server is about to shut down. This gives them a chance to save any changes for their work, and if a user needs more time, you can cancel a scheduled shutdown. To schedule a reboot of your system, enter in the following. The -R option indicates that we wish to reboot our system, and the +5 option states that we will have the system reboot in 5 minutes after the command is executed. And we can use the -C option to cancel a scheduled shutdown or reboot. And as we can see from our other terminal, the shutdown has been canceled. To schedule the system to shut down at a specific time and send a notification to all logged in users, we can do the following. And we can see in the other terminal that we got the message telling us that our system will be shut off at 11 p.m. The -H option indicates that we want our system to halt at the time specified, using the 24-hour time format. 5 minutes prior to the scheduled shutdown, no new user logins will be permitted. Again, we can use the -C option to cancel the scheduled shutdown. If you want to shut a system down immediately, you can use the word now in place of a time. This will bring the system down as soon as we press enter. And that sums up the different ways you can power off your RHEL system. Red Hat Enterprise Linux supports a variety of hardware. You can visit www.redhat.com/rel/compare to get a full listing of the platforms that RHEL can run on. For the purpose of this course, you can install Red Hat Enterprise Linux or a rebuild distribution on any 32-bit or 64-bit hardware with at least 512 megabytes of RAM, while 1 gigabyte of RAM is recommended for a minimum. If you do not have any spare hardware to run Red Hat Enterprise Linux 6, then a virtual machine is a common choice for candidates to practice on. There are various technologies available that you can use to run a Red Hat Enterprise Linux 6 virtual machine on your host computer. Here are some examples. VirtualBox works on all major platforms and is easy to install and configure. You can learn more about VirtualBox at virtualbox.org. VMware Player works on both Linux and Windows and is also easy to use. Learn more about VMware Player at vmware.com/products/player. Parallels Desktop is another option for Apple Mac users. It's a proprietary application that you can learn more about at parallels.com/products/desktop. If you are running a Linux system, you can use Virt Manager. Virt Manager works with the native virtualization system known as KVM built into the Linux kernel. We will discuss virtualization with Virt Manager on Red Hat Enterprise Linux 6 in a later video. One of the great features of using a virtual machine is that you can take a snapshot of it, practice on it, and then roll back to its previous state so that you can try the same commands over again. You can find various tutorials on the internet on how to utilize any of these virtualization tools to practice with, as they are beyond the scope of this course. The important thing to remember is work with whatever you are comfortable with, since the goal is to be proficient in Red Hat Enterprise Linux, not any particular hardware system. We can manage the amount of hard disk space that a user or a group can use with disk quotas. To set up a quota for a user, we first must make sure that we are doing this on a home directory that is mounted on a separate partition. We have a system here that has its home directory mounted on a separate disk. The first thing that we will need to do is edit the /etc/fstab file to add the user quota directive to our mount options on the home directory. Next, we remount the home partition. Now we check to make sure that our home directory has been mounted with the user quota option. And we can see that it has. Next, we will need to create a quota table file with the quota check command for our home directory. The -C option creates our new quota table files. The U option creates an aquota.user file, and the M option tells QuotaCheck to not try and remount our file system in read-only mode. Now, do an ls on our home directory. And here we see our aquota.user file. Now, we have our home directory set up for quotas, but we don't have any quotas set up on any users yet. We can view a user's quota table with the addQuota command. The U option specifies the username we wish to work on. And here we are presented with the quota table for the user K. Armstrong. Let's take a moment to go over this file. The alignment of our fields are a bit off considering that the file system here is quite long. The first field is obviously the file system that we have the quota set up on. The next field is the amount of blocks that are in use by the user. This field should not be edited. Next, we have the maximum amount of blocks that a user may take up on a file system before a warning is issued to the user. This number is known as the soft limit. Next, we have the maximum amount of blocks that a user may take up on a file system. This is the hard limit and cannot be exceeded. The next field is for the amount of inodes a user has on a file system. The inodes refer to the amount of entries in a directory. This value should not be edited. As before with the soft and hard limits for blocks, these next two fields refer to the soft and hard limits for the amount of inodes a user can have on a partition. A 0 in the place of any of the soft and hard limits means that there is no restriction set. The easiest way to modify the quota limits for a user is with the setQuota command. Let's set a quota for the K. Armstrong user. Here, we are setting the quota on K. Armstrong to have 30,000 blocks, or roughly 30 megabytes of space as a soft limit, and 35,000 blocks, or roughly 35 megabytes, for a hard limit in his home directory. The two zeros at the end means that we are not limiting the amount of files that the user can have, we are only limiting the amount of space he can use. Next, let's turn on quotas for the home directory. Now, let's log in as K. Armstrong to test our new quota. As the K Armstrong user, we are going to create a test file of a specific size to test our quota settings. We will use the dd command, which is short for disk dump, to dump a bunch of zeros as data into a brand new file. We are using 1 kilobyte block sizes, and we are creating 25,000 of them to have a 25 megabyte file. Now run add quota to see what our quota usage is. We can see that we have used up 25,000 extra blocks, and we have increased our inode count by 1 since we just added a new file. Now let's see what happens when we go over our limit. We will create another test file that will cause us to exceed the limit. Here we see that we got a message that our quota was exceeded. We can also use the add quota command to copy quota settings from one user to another. Rather than manually editing quota settings for G. Freeman, we will just copy the quota settings for K. Armstrong over to G. Freeman. The P option sets the K. Armstrong quota entry as the prototype to use for the G. Freeman account. Now, if we check on G. Freeman's quota settings, we can see that the quota settings for K. Armstrong have been copied to G. Freeman. Now we are going to set up a quota for a group directory. We have our /sales directory mounted on a separate partition. The first thing that we will need to do to set up group quotas on a particular directory is to edit our /etc/fs tab file and add the group quota mount option to it. Next, we remount our sales partition. Now, we check to make sure that our partition has been mounted with the group quota option. And we can see that it has. Next, we create our aquota.group file with the quota check command. The -C option, just like before, creates our quota check file, and the G option creates the aquota.group file for us. And once again, the M option prevents our partition from being remounted in read-only mode. Now let's make sure that we have our aquota.group file. And there it is. Now, to set a quota on the group, we run the setQuota command with the -G option, followed by the group name. Just as we did with our user quotas, we are setting a limit only on the amount of blocks and not on the inodes, as we will allow them to have as many files as they want as long as they don't go over the hard maximum of 35 megabytes. And we can use the add quota command with the -G option followed by the group name to view their quota settings. Now, we need to turn on quotas for the /sales directory with the quota on command. Next, we will log in as G. Freeman and try to create a file that is larger than the quota limit, again using the dd command that we demonstrated in a previous video. we should get a warning letting us know that we have gone over the quota limit. And there is our warning. Let's take a look at our quota usage. Looking here, we see that we did in fact get up to 35 megabytes of usage, but the quota prevented us from going beyond that. To see the quota reports for all group quotas, we can run the rep quota command with the -G and A options. We can also use rep quota to see all user quotas. We have already seen before how to monitor and view our SE Linux messages using the SE Alert tool. In this video, we will see how we can monitor system events by watching the standard system logs. Using the tail command is the most common way of viewing system log files. By itself, tail will show us the last 10 lines of a file. We can increase the amount of lines viewed by using the -N option followed by the number of lines that we wish to see. If you are troubleshooting an issue, or you just want to see what is going on with your system in real time, we can follow the log files by using the -F option of the tail command. Each time a new entry is entered into a log file by the system, we will see it in our terminal when it occurs. Here is an example where we modify our network connections. And we can see in our var log messages output that we have modified our network configuration. To cancel the tail command, just press Ctrl+C. We can also view in real time when someone elevates their privileges to root. In one terminal, we will follow the var log secure file. And in another terminal, we will switch from our regular user to the root user. And we can see in the other terminal that a session was opened for the user root by the K Armstrong user. You can use just about any text processing command on your system log files. Administrators often use grep when they are searching for specific lines within their logs. less and cat are often used on log files as well. If you have problems with a system application or service, start your troubleshooting by investigating var log messages. And if you are running SE Linux, check your audit logs as well. Chances are the logs will contain the clues you need to resolve your problems. The RHCSA exam does not expect you to be an expert in using regular expressions, but it does assume that you know some basic usage of regular expressions. A regular expression is generally a pattern that describes a particular string. The most commonly used tool that is used in conjunction with regular expressions is grep. We introduced grep in a previous video where we searched for a particular string of text within a file. By combining grep with regular expressions, we can use it to search for lines of text in a file that can match a variety of patterns. We will demonstrate the most basic usage of grep by looking for a particular line of text in the /etc/passwd file. We will be searching for any lines that have root in it. We have two entries displayed below. But what if we only wanted the line that had root at the beginning of it? That's where regular expressions come into play. Here's an example. We are still instructing grep to look for root in the etc passwd file, but we have included the caret character in front of root. The caret is a regular expression stating that we are looking for anything that begins with root. We enclose the expression in single quotes so that bash interprets our expression literally. Now we have our line that just has root at the beginning of it. We can also use grep to search for words that match a particular letter case. For instance, we have a file, fruits.txt, that has apples written out in a mixture of upper and lowercase letters. Now, we will use grep to only search for those lines that begin with either a capital or lowercase a, and where the rest of the letters are lowercase. And we will also print out the line numbers that each instance appears on. The N option specifies that we want to know the line numbers of our result, and we enclose our two A's that we are searching for within brackets. Now we have the results we are looking for, and we know what lines they appear on in our file. We can also use grep to search for strings that appear at the end of a line. We do this with the $sign at the end of our search term. Here is an example. Here, we are searching for any account on the system that doesn't have a login shell in our /etc/passwd file. Now, let's use the same search again, but this time tell grep that we are looking for any line that doesn't end in /bin/no-login. We can do this with the -v option for grep. And here we have the accounts that do not have /sbin/no-login as their shell entry in the /etc/passwd file. Another example of using regular expressions with a command is by altering files with sed, or the string editor. In an earlier video, we have a file called spelling.txt that has some misspelled words in it. We will now use sed to replace one of the misspelled words with a correctly spelled word. Just to review, here's our spelling.txt file. Now, we are going to set up our command that is going to replace the word spelling for us. Here, we have sed set up to swap the first word, which is our misspelled word, with the correctly spelled word in our spelling.txt file. And the output indicates that our misspelled word has been replaced. However, if we look at our spelling.txt file, we can see that our original file wasn't altered. The reason for this is that sed is not set up to change the source file. We can, however, use output redirection to send the corrected output to a new file. Now we have a file with the corrected spelling. If you wish to know more about regular expressions, you can use the man pages to find more information. Just do man 7 for section 7 of the man pages for regex. And here you will find plenty of details on regular expressions. Using the rpm command is one of the older ways of installing and removing packages on a RHEL system. The rpm command is a great way to install individual packages, but you can run into issues when trying to install multiple packages. These problems generally arise when your system does not have the appropriate dependent packages already installed for a particular application to run. Then you would have to search for that dependency and attempt to install that. Oftentimes, that package may require another package that you do not have installed, so you attempt to install that, and so on. The yum command has eased us of the dependency problems, but the rpm command is still relevant and very useful on a RHEL system. The first task that we will demonstrate with the RPM command is installing software with it. We have downloaded an RPM package from our local FTP server, and we will install it with RPM. We used the -I option to install RPM packages. We get a message about a GPG key, but did the software install? We can check by querying our RPM database to see if the package was installed. Here, we are using the -Q option, which queries the database, the -A option, which searches through all packages, and then we pipe the output of the RPM command to grep for LFTP. And from our output, we can see that the package did install. To remove packages with RPM, we use the -E option, and we don't have to specify the full package name. Again, we can query the RPM database to see if the package has been removed. And we no longer see LFTP listed. Let's reinstall LFTP, but using the more common options that administrators utilize with the RPM command. With this command, we are using the -U option to upgrade LFTP if it is installed, or if it is not already installed, to go ahead and install it. The -V option means we want verbose output, and the -H option gives us hash marks that act as a progress bar updating us on the installation process. Now that output looks better. Let's check to make sure it was installed. And there we go. LFTP was in fact installed. Two of the more useful options for the administrator is the ability to query RPM files for what documentation and configuration files that get installed with a given package. To see what documentation was installed with the LFTP command, we use our query option along with the -D option to search for the documentation itself. Here, we see all of the documentation and their locations that came with the LFTP command. To locate the configuration files for LFTP that RPM installed, use the -C option along with the query option. And we can see that the lone configuration file is at /etc/lftp.conf. As with the yum command, we can also view information about an installed RPM package with the -I option. And we get the same output that we would get if we ran the yum info command for LFTP. Despite the age of the RPM command, it is still constantly being updated and improved. As with the other commands we cover, I recommend reading through the man page for the RPM command so that you can see the many options that are available for it. In this video, we are going to discuss RPM packages, the default software installation system used by Red Hat-based Linux distributions. In a later video, we will discuss installing software with the RPM command, but for now, we're just going to briefly discuss what an RPM package consists of. RPM is short for Red Hat Package Manager. All RPM files end in a .rpm extension. RPM files are used in installing software, documentation, and source code. RPM files are also the preferred Linux installation files according to the Linux standard base. There are two different types of RPM files: regular RPM files, which contain the compiled code, and source RPMs, which contain the source code for a particular application. The same RPM command is used to install either type of RPM file. RPM package names are constructed like this: first the name, then the version number, then the release number, then the architecture.rpm. Here is an example using the OpenSSH package. First we have the name, next we have the version number, next we have the release number, and then finally the architecture. The architecture comes in three different types. We have i386 for 32-bit systems, x86_64 for 64-bit systems, and files marked as no-arc, which means that they are platform-independent software and can be installed either on 32-bit or 64-bit systems. An RPM package contains the following items: the spec file, which is a file that ends in the .spec file extension, which contains the information necessary to create the RPM package. There's also the application or libraries that are to be installed, any documentation, such as man pages or info pages, that come with the package, and any configuration files that come with the application. Package installation is tracked and stored in the RPM database, which is located at var lib rpm. So whenever you query for a particular RPM, or you're doing a yum info, which we will discuss in later videos, you are actually checking the RPM database. In the next video, we will start installing software with the yum command. In this video, we are going to discuss the various run levels on a Linux system and the differences between each one. A run level dictates what processes are going to be running on a system. This includes items such as particular networking services and what type of environment the user will be working in, whether a graphical environment or just a command line terminal. There are a total of 8 different run levels. We will discuss each one in this video. You can only have one run level active at a time. You cannot have multiple run levels active at the same time. So you can't have run level 2 for one user and run level 5 for another user. And here are the different run levels. Run level 0 means that the system is shut down. Run level 1 is for the single user mode, and that single user is the root user. It is mostly used for making repairs to a system. There is no network access within run level 1. This is also the mode where you can reset the root user's password in case you forget it. If that sounds like a security nightmare to you, we will show you how to lock that down. Run level 2 is a multi-user mode, meaning that more than one person can be on the system at the same time. It is a text-based mode, so there is no graphical desktop. The one thing that Run Level 2 does not have is access to NFS shares, but other networking resources can be available. Run Level 3 is a full multi-user mode with NFS access. All networking services are available in Run Level 3. Run Level 3 also is a text-only environment. Run Level 4 isn't used, but can be customized according to the administrator. You will most likely never use this run level. Run Level 5 is the run level that provides a full graphical desktop along with all networking services enabled. And finally, Run Level 6 is the reboot run level. Don't make this the default run level, otherwise your system will just constantly reboot. So how do we use these different run levels? Here we can see that we have a graphical desktop environment, so we must be in Run Level 5. We can verify this with the run level command. And we can, in fact, see that we are in Run Level 5. To change to another run level, we can use the telinit command. You have to be root to use this command. Just enter in telinit and the corresponding number for the run level you wish to switch to. Then press enter. And now we are in Run Level 3, the multi-user mode with networking. Now let's switch to Run Level 2. Let's first verify that we are in Run Level 2. And let's check our NFS service. And we can see that it is not running, but we do have web access. As we stated before, the etc init tab file is where the system's default run level is configured. And we can see that our system here is configured to automatically boot into Run Level 5. If you want your system to boot into Run Level 3 by default, just change the value here. Now we will save the file and reboot our system, and when it comes back up, it will default to run level 3. We will use the Telnet 6 to reboot our system. In our next video, we will show you how you can boot into different run levels without modifying this file, which is helpful for troubleshooting. Now that we know what the different run levels are and how we can change to a different run level while logged into the system as the root user, we will now show you how to boot into a different run level. Here at the grub menu, we press the A key to append an argument to our kernel boot line. Next, we will enter a 1 at the end of our line, which means that we wish to boot into run level 1. That's all there is to it. Next, press the Enter key, and our system will boot into single user mode. All we need to do to boot into another run level is to just append the number for that run level at the end of the kernel's boot arguments. And now we are in single user mode with a root prompt. In single user mode, we can change the root password in the event that we forget it. Just type in the passwd command and press enter. Then enter in a new password for the root user. Now we have a new root user password. If you would rather not have the single user mode automatically log into the root account, you can force single user mode to prompt for a password by modifying the etc sysconfig init file. Now scroll down to the bottom of the file and change the sbin su shell to sbin su login as indicated by the comments above this line. We get an error message stating that vim can't write to the root user's vim info file. That's okay since we are in single user mode, but the change to the file did take effect. And as stated, the root user will be prompted for a password the next time single user mode is run. Let's reboot our system into run level 3. Again, just press the A key, then append the number 3 to the end of the kernel boot line. So how does the system know what services to run in a particular run level? We have already used the check config tool to enable and disable services for a particular run level, so where is that information located on the system? In a moment we will find out. We have already learned that all of our service script files are located in etc init.d. And we have also learned that our etc init rc.conf file starts the scripts for a particular run level. And this file, in turn, starts the service script files for the designated run level within etc rc.d. Within this directory are the parent directories for our individual run levels. Let's take a look at the scripts for run level 5, which is located in the etc rc.d rc5.d directory. As you can see, we have symbolic links that reference the original service script locations. For instance, we have a script file for the oddjob D that links back to the original oddjob D script in etc init.d. But what is the letter and the number for before the service name? Looking through this directory, we have the letter K and S before the service name. The K is for kill and the S is for start. The number following the letter indicates in what order a service should be started or killed. Services prefixed with a lower number get started or killed before those with a higher number. So our oddjob daemon is stopped early on in the process of entering run level 5. So what sets its priority? The check config command. Let's use an example. As you can see, the check config output confirms that the oddjob service is disabled in run level 5. So let's see what happens when we enable it. And now we see that the oddjob script link has been changed to start with an S, indicating that it will start in run level 5, towards the end of the run level 5 startup process. So now we know what check config is doing in the background to enable and disable our services for specific run levels during the system startup. Take a quick look at the directory for run level 0, the system halt run level. We can see that all service script links are stopped, except for the 2 scripts that actually halt the system. Take a look around these directories on your own and compare what you see to the check config list command to get a good feel for what your system does to start services when your server boots. Another tool that we have at our disposal for scheduling jobs is the at command. The at command is meant to run one-time jobs at specific times. The at service is what checks our at queue for any jobs that may be configured in there. Let's create a script file that will install the MySQL client tools on our system. We will then use the at command to run this script for us at a later time. Since this is a script file, we need to make the script executable so that the at command can run it. Now, let's set up the at daemon to run this script in 2 minutes. We do this with the at command. We run the at command, followed by the -f option, which specifies a file that is to be run, in this case, our MySQL install script, and we want this script to be run 2 minutes from now. And we can see that the job has been submitted. We can take a look at the jobs that are queued to run by using the @queue command. And here we can see the job that we have submitted. But what if we want to cancel that job from running? We can do so with the @remove command. Just enter the @remove command, followed by the job number displayed from the @queue command above for the job we wish to remove. And we can verify that the job has been removed by running the @queue command again. Let's schedule this job to run again. And let's double check the queue. Where is the @queue located? Let's take a look at var spool at. Here we can see a script file located in here. Let's see what it contains. And we can see that this script contains the contents of our scheduled command. We can also schedule a job to run at a specific time. For instance, you can schedule a script to run at 12 noon with the following. We could even tell it to run this command tomorrow by tacking the word tomorrow onto the end of the command. Let's take a look at our @queue. It looks like our queue is clear and we have new mail. To see the system mail message, type in the mail command. Here we have a message from root entitled Output from your job. To read the message, enter in the message number, in this case, number 1. Then press Enter. And the message contains the output from the script that the command had executed. To quit the mail application, just press the Q key. Be sure to take a look at the man pages for the command to see your scheduling options. We can schedule tasks on our system using both the cron and at daemons. Cron is used to schedule recurring jobs, while at is used to schedule a task to run at a particular time. We use cron tables, or cron tabs, to schedule our jobs. The cron d daemon is the service that reads those cron tables and performs the task configured. Let's first verify that we have our cron service configured to run at system startup. Now, to configure a cron job, we must first understand the syntax of a cron job. The first field of our cron tab is for the particular minute within the hour that you wish to start the job. The next field is for the hour of the day in 24-hour format with 0 meaning 12 midnight. The next field is for the day of the month. Then we have the month of the year. You could use either 1 through 12 for the month or use the first 3 letters of the month name. Next, we have the day of the week that the job should run on. 0 or 7 would be Sunday, 1 would be Monday, and so on. Since Sunday can be represented by 2 numbers, I recommend using the first 3 letters of the day instead. You can use a star character in place of any of these fields to represent any day of the month itself, minute, or day of the week. We will demonstrate this shortly. To set up a cron job, we use the cron tab command. When we run cron tab by itself, we are creating a cron tab for the currently logged in user, so in our case, the root user. We can specify a user to create a cron job for with the -u option, then specify the username. The -e option means that we are going to edit our own user cron tab. The first thing we will do is to create a cron job that will create a file called Here I Am in the root user's home directory in 3 minutes after we submit the job. Let's get the system's date so we can use that as a basis for our scheduling. We will format the output of the date command to just show us the time. Okay, so now we have our time. Let's create our job. Now we will enter in the details of our cron job. Now we save the cron tab file. Let's quickly review our file. We are starting at the minute specified, which is 3 minutes later than our current time, our current hour, the day of the month, and we are using the star character here to represent any month, and we're using the star character here to represent any day of the week. And then finally, the command that we wish cron to execute for us. And if we check the default location for our cron jobs at var spool cron, we should see our cron job there. And there it is. In a few moments, we should be able to see our new file. There are also default system cron jobs that run on a periodic basis. We have jobs that run hourly, daily, weekly, and monthly. All of these jobs are stored within the etc directory. Let's take a look at the jobs that run daily. All daily jobs are stored in the etc cron.daily directory. And here we see the default system jobs that run every day. These are just script files that are placed in this directory. The cron service runs these scripts automatically on a daily basis. Any script that is placed in this directory will get run once a day. The same goes for the weekly, hourly, and monthly cron jobs. Just drop a script in the cron.weekly directory and that particular script will get run once a week, and so on. Let's take a quick look to see if we have our new file. And there it is. Be sure to review the man pages for cron tab for more details on how to edit a cron tab file. If you forget the syntax for a cron tab, just view the etc cron tab file that we showed you at the beginning of the video as a reminder. The Secure Shell, or SSH protocol, includes a group of useful utilities for securely communicating with remote systems. Red Hat Enterprise Linux provides the open SSH packages, which includes both SSH server and client applications. We will demonstrate the SSH and SCP commands in this video. We will start with the SSH daemon, which is the SSH server daemon that allows remote SSH connections to communicate with the system. If this service is not running, then we will not be able to SSH into this system. SSH is the most commonly used tool by technicians for administering remote RHEL systems. SSH allows us to open up a secure remote shell on another system. All of our command traffic back and forth from the client to the server system is encrypted. In the old days, administrators would have used Telnet to maintain remote systems. The problem with Telnet is that all traffic was passed in clear text, meaning that anyone on the network could sniff out that traffic and find login credentials and other important information. The SSH utility is a far superior replacement for Telnet since all of the communications between the systems is now encrypted, preventing others from reading our network traffic. To remote into another system with the SSH command, run the following. We run the SSH command, followed by the username for the account that we wish to log in as, then the @ symbol, and finally the IP or hostname of the system we are attempting to access. If we haven't logged into this system remotely before, we are presented with the Remote Systems Secure Fingerprint. This is to help us make sure that when we try and log into the same system again at this IP or hostname, that we are in fact accessing the correct system. If the fingerprint doesn't match the one that we already have, it could mean that the other system has been compromised and we are attempting to access an illegitimate remote system. Type in yes to confirm, then press enter. We are then prompted for the root user's password from the remote system. Type in the password, then press enter. We are now logged into the remote system and we can run commands on it as if we were sitting right in front of it. While we are on this system, let's take a look at the SSH daemon configuration file. This is the configuration file that controls how the SSH server operates. For instance, if we scroll down, we can see the directive that allows root to remote into the system through SSH. If we were to change this to disallow root logins, then to perform system administrative tasks, we would first need to log in as a normal user, then elevate our privileges to root either through the sudo or su commands. Take a look at this file further to see some of the options available to the SSH daemon. To log out of an SSH session, just type exit, then press enter. Now we are back in our local system. We can also copy files from one system to another through an encrypted connection using the SCP command. SCP is short for secure copy. Here is an example. To copy our vim-test file in our local root user's home directory to the root user's home directory on the remote system, we run the following. We run SCP, then we tell it the name of the file that we wish to copy, then we provide the account that we will be logging into the remote system as, followed by the @ symbol, then the IP or hostname of the system, then a colon, and finally the path to where we wish to copy the file. Then we enter in the remote root user's password. And our file is copied over. Take a look at the man page for the SSH command to find out more about it. One other thing that we should look at with file context is the difference between moving and copying files on an SE Linux enabled system. First off, let's take a look at the security context and inode number for the Anaconda file in root's home directory. Now, let's move that file to Kenny's home directory. Remember that we said that a file will inherit the security context of the parent directory? Let's see what the security context is for Kenny's home directory. We can see that the directory security context is user home dir t. Now let's take a look at the Anaconda file's security context now that it is in Kenny's home directory. We can see that the security context on the file did not inherit the one for the regular user's home directory. It instead still has the context for the root user's home directory. Why is that? If we take a look at the inode number for the Anaconda file and compare that to what it was when it was in the root user's home directory, we can see that it is the same. Remember that an inode contains metadata such as the permissions and location of a file, as well as a file or a directory's SE Linux security context. Since moving a file is just a way to tell the file system that the same file is in a new location, the security context and inode number stay the same. Let's move the file back. Now let's copy the file over instead of moving it. Then take a look at the inode information. Now we see that we have a new inode number that is different from the original. That's because when we copy a file, we are in fact creating another file based off of the original, which in turn will have a new inode number. Let's take a look at the security context. And since the copy process creates a new copy of the original file in Kenny's home directory, the security context gets inherited from the directory it was created in. An example of why this is important is if you have a web server that needs to be able to display web pages. A web page has a particular security context that SE Linux checks to see if it can be viewed by others. If you moved a file from one directory to the default web server directory, then you will not have the appropriate security context. In this case, the website will not be visible from a web browser. But if you copy the web page from another directory to the web server directory, and it has the correct security context, then the page will be viewable from a web browser. We will demonstrate this in our video for setting up a basic web server. For now, just be aware that it is best to copy a file from one location to another, then remove the original file, rather than moving files on a system that uses SE Linux. As we stated in a previous video, SE Linux booleans offer a means of allowing or disallowing a process extra capabilities. This helps to give an SE Linux policy a bit more flexibility as if you were tuning the policy itself. To see a complete list of SE Linux booleans on your system at the command line, run the following command. We run the semanage command, telling it to list all of our booleans, then pipe that output to the less command. And here we can see all of the booleans on the system, if they are on or off, and a description of what the boolean does. We can also view this information from the System Config SE Linux application. Just click on the Boolean category, and here we see the same listings. The check mark dictates if the Boolean is turned on or off. You can also search for specific booleans with the get SEBool command. For instance, let's say we just wanted to see the booleans relating to an FTP server. We can do this with the following. Here we are telling the get SEBool command that we want to get all of the booleans, then grep for those that have FTP in the results. Now let's say that we want to configure SELinux to allow a user to FTP to their home directory. To change the boolean for our FTP home dirs option, we use the set SEBool command. So to set this boolean, we use in place of on, we could use a1 or true. The converse is also true if we want to turn something off. We could just use the terms off, 0, or false. However, if we restart our system, then this boolean will be turned off again. To make the policy stick, we need to use the -p option, like so. You would not use the -p option if you just wanted to test something. However, if you need this to be a permanent change, then you will need to use the -p option. Keep this in mind when you take the exam if you need to set a boolean on a service and that configuration needs to survive a reboot. We will be working more with booleans when we set up our FTP. For the RHCSA exam, you do not need to know all of the ins and outs of SELinux in great detail. You will, however, be responsible for having SELinux enabled and properly configured for the completion of your exam. You should not need to modify any of the default policies that are built into the system, but you will need to know how to troubleshoot an SELinux related issue and configure services to properly work with SELinux. SELinux is short for Security Enhanced Linux. It was developed by the NSA, the National Security Agency, and they released it as open source in December of 2000. Red Hat first introduced SELinux in their Red Hat Enterprise Linux 4 distribution. SELinux is a mandatory access control system, which means that the operating system restricts the ability of a thread or process to access or use a resource on the system referred to as a target. SELinux performs its protection of this system through kernel modules and user space tools. And these kernel modules are known as Linux security modules. SELinux has multiple types of policies, but the one in use by RHEL is the targeted policy. A targeted policy restricts a target's access to resources. Examples of targets are memory locations, TCP/UDP ports, directories or files, and others. There are 3 modes for SELinux. The first is the enforcing mode, which is the system default. In this mode, SELinux is on and checking policies when a system resource is requested. You will need to have SELinux in this mode with all policies properly working to pass the exam. And in permissive mode, no policies on the system are enforced, but they are checked. If there is a policy violation that occurs on the system, you will get a warning, but you will be able to carry on as if SELinux wasn't even on the system. This is best used for troubleshooting to see if SELinux is preventing something from working properly. Once the issue is resolved, SELinux will need to be back in enforcing mode. Finally, disabled mode. In this mode, no SELinux policies are enforced or checked. If you disable SELinux on a system that has it enabled, then the file system will need to be relabeled at the next system boot, which can take a long time. Do not use this mode during the exam, as it will cost you time. If you need to troubleshoot, switch back and forth between enforcing and permissive modes. SELinux is essentially a system that reads and checks labels, and another term for these labels are security context. The old Unix adage of everything on a system is a file comes into play here, since every file on the system has a security context. That includes running processes and even network ports. SELinux is a type enforcement system. Basically what that means is that an SELinux policy's rules dictate what processes are allowed access to certain types of files. SE Linux messages, such as allowing or denying access to a process, are cached on the system. This cache is known as the Access Vector Cache, or AVC. SE Linux messages can be found in var log messages, but the most important location for SE Linux messages is located at var log audit.log. This is where you need to check if you believe that you have an SE Linux related error or problem. When you get what is known as an AVC denial message, this is where you will find it. With the following videos in this section, we will see these concepts in action. Before we dive into the world of modifying context and setting booleans for SE Linux on a RHEL system, we need to get some tools set up to make SE Linux management easier. There are two packages that I recommend you install when it comes to working with and troubleshooting SE Linux. The Policy Core Utils GUI tool is a collection of front-end tools that we can use to monitor alerts and errors and to help with the overall configuration of SE Linux on a RHEL system. The name for the main application is System Config SE Linux. The SE Troubleshoot package helps us to parse the SE Linux audit files to resolve any issues that may arise with SE Linux. Once we have the packages installed, we can access System Config SE Linux by going to System, Administration, and SE Linux Management. The application takes a few moments to load since it has to parse a good deal of system information. The main categories on the left that we are concerned with are status, boolean, and file labeling. The other categories are outside the scope of the RHCSA exam. With the status category, we can set our SE Linux modes. With the system default enforcing mode, we can switch between the three different types of SE Linux modes. Keep in mind that if you switch to disabled, that you will need to check the box to relabel the file system on the next reboot. However, avoid this when you are taking the exam. Your system needs to be in an enforcing mode by the time you complete the exam. We can also change our current enforcing mode by switching back and forth between enforcing and permissive. I want to switch gears for a moment and show you how this can be done from the command line. We can use the get_enforce command to see our current SE Linux mode. If we want to temporarily switch to another mode of enforcement, we can use the set_enforce command. For instance, we can change from enforcing mode by using set_enforce permissive. However, we can also use a Boolean value to change our modes. Using a 0 is the same as saying permissive, and using a 1 is the same as saying enforcing. During system startup, the etc SE Linux config file is checked to see what mode SE Linux should be in. Here, we can see the same information that is displayed in our System Config SE Linux tool. We could also modify this file to change our modes, and they will be active the next time the system boots. Back in System Config SE Linux, the next category is Boolean, which allows us to enable or disable some things that a process can do or access. We will go over this a bit further in a later video. Next, we have the file labeling category. This is where we can see the default file labeling security context for a file or a directory. We will discuss security context further in the next video. To find any man pages that have information relating to SE Linux, run the following command. Here, we can see the various man pages that are available to us that contain information about services and commands that we can use SE Linux with. We have demonstrated how to start, stop, and restart services a few times already in this video series, but now we are going to take a deeper look at service management. Services, or daemons as they are often called, are programs that run on our system and perform specific functions. We can see all of the services that we have on our system in etc init.d. Each one of these services is actually a script file that runs the associated application. Let's take a look at the service script for @d. Here, we can see the program that gets run by the script, the @d program located in /user/sbin. We also see the name of the program, which is what we use with the service command we will see shortly. And we can see where the configuration file for the service is located. If you notice, most service names end in a D, which means daemon. If we scroll down, we can see the commands that we can run with this daemon, such as start, stop, restart, reload, which will reread the daemon's configuration file, force reload, status, which tells us if the service is running or not, and conditional restart. Let's try out the status option on this service. And we can see that the service is running. Specifying the full path to the service script is the traditional way of working with services from the command line, but Red Hat has created the shorthand method by using the service command. This is the method that we have been using throughout the video series. It requires less typing than using the full path to the service script. As we have seen in other videos, we can start and stop services with the service command. And we can also restart services with the service command. And if we made a change to the @d configuration file, and we wanted the @d daemon to reread the configuration file so that it can act on our changes without restarting the service, we can use the reload option. We use the service command to work with services during the system runtime. However, in order to configure whether a service is running or not when the system boots, we use the check config command. To set up the @d service to not start when the system boots, we run check config @d off. To have the service start when the system boots, we use the on option. To see a list of the services on our system, and if they will start or not when the system boots, we run the check config command with the -- list option. On the left, we see the name of the service, then a listing of numbers, followed by the word off or on. The numbers represent run levels, which we will discuss in a later video. Basically, what you're looking at is whether a service will start at boot or not within a particular run level. For instance, when the system boots into run levels 3, 4, and 5, the service will start, but not the others. By default, when you run the check config command, you are enabling or disabling a service in run levels 3, 4, and 5. We can specify what run levels a service may start in with the -- level option. For example, to only allow the @d service to start up automatically in run levels 3 and 5, we run Again, don't stress about the run levels right now. We will go over them in detail in a later video. For now, just focus on the fact that check config is used to make sure that a service does or does not start when the system boots. On your exam, you will likely be asked to make sure that a particular service will be running when the system reboots. If the service isn't running when the system starts, then you will likely not get credit for any work you did for that service. As we stated before, every file and process has a default security context. We are going to discuss what a security context looks like and how to view and modify them. Usually, a file will inherit a directory's security context. A good example of this is the /etc directory. We can view the etc directory's security context with the following. The -z option is what gives us the SE Linux security context on a file or a directory. Here is our security context for the etc directory. A security context is broken down into three components. First, we have the user component, which refers to the type of user that is logged in, then the role component, which indicates the purpose of this file, process, or user. Then we have the type component, which is the most important field since SE Linux is a type enforcement system. As we can see, the security context type for our etc directory is etc_t. As we said before, most items inherit the context of the parent directory. Let's take a look at a file within the etc directory that demonstrates this. We can see that our etc services file has the same security context as our etc directory. However, there are some files in the etc directory that will have their own special security context due to the roles they perform. For example, let's take a look at the etc shadow file. As seen here, the shadow file has its own security context, specific to the shadow file. This makes sense considering that it holds the encrypted passwords for the users on the system. We can also view the security context for a running process. We add in the same Z option to view the security context for our PS command, which we will see more of in a later video. Notice the contexts that say unconfined? These are processes that are not protected by SE Linux since there is no policy written for them. Anything marked as unconfined T falls into that category. We do see that the Getty processes have their own security context. Now, we are going to break the SSH service on our system so that we can see why security contexts need to be properly configured and what we need to do to fix them. First, we will stop the SSH service. Next, we will see what the security context is for our SSH service configuration file. Here we can see that the type for the configuration file is that of etc. We will use the chcon command to change our security context on our file. We are using the -- reference option, which tells chcon to make the security context of our sshd_config file match that of our Anaconda file. So now let's take a look at the security context for our sshd_config file. And we can see that it is now switched to admin_home_t. So let's see what happens when a file context on a configuration file that a service depends on is not what the service expects it to be. And we see that our attempt to start the service has failed. Along with that, we see that we have an access vector cache, or ABC, denial message at the top. In the following video, we will see how to use the ABC message to troubleshoot and fix our issue. Continuing on from our previous video, we are now going to troubleshoot our ABC denial message that popped up when we tried to start our SSH service. Let's click on our ABC denial message. Here we can see what the problem is that SE Linux is reporting, that we can't properly read the etc ssh sshd config file. Below this, we are told that SELinux denied access to the SSH daemon because our sshd config file may be mislabeled. Let's click on Show Full Report to see what else it tells us. We see the same summary and detailed information as above, but below that we see a possible fix to the problem. According to this, the fix is to run the restore con command, which is a tool that restores file and directory security context, and we are told to run the restore con command on the hidden SSH file in root's home directory. Below this, under additional information, we can see the details of what happened. Our source context shows us that the SSHD type was trying to access the target context, here, which refers to the root user's home directory. The target object itself is the SSHD config file. I want to quickly show you that we can see the same message with the SEAlert command from the shell. The SEAlert command lets us parse the same audit.log file that the SELinux security alert window shows us. And as we can see, it is the exact same information that the window shows us. Back in our graphical window, we see that we have a button that will restore the file context for us. Let's try that first to see if it fixes our problem. Now let's delete out the message since we attempted to resolve it. And let's try and start the SSH service again. Well, it appears that we still have a problem. Let's take a look at the alert message. It appears that there is still an issue with the SSHD config file. Yet we are told that the fix would be to restore the context on our hidden SSH file in the root user's home directory. We tried that and we still have a problem. Now I don't want you to think that the SEAlert tool won't fix any of your SELinux issues for you. It will actually do a great job of correcting many issues you may come across. The SEAlert tool is helpful with pointing us in the direction of what the possible root cause of our error is. If we take a look at the details again, we see that the target object, which is our SSHD config file, has a target context that looks odd. We see that the config file is under the etc directory, yet the target context shows a label for the admin home directory. Let's use the restore con command to attempt to relabel that file, since the labeling doesn't look like it is correct. Now let's check the file context. And now we see that we have the type field of our context set to etc. Let's see if that fixed the problem. And there we go, the service started, and we have no alerts. What if you knew what the security context was supposed to be? Don't worry, you are not expected to memorize security context, but here is how you can manually set it if you knew what the appropriate context should be. First, let's change the context back to admin home T. Okay, if we knew that the context was supposed to be etc_t, we can manually set it with the chcon command. The -T option tells Chacon what security context we want to set on our SSHD config file. However, the Chacon command is only a temporary fix. Using the Chacon command to change a security context will survive a reboot, but it will not survive a file system relabel. In order to make the security context change permanent, you will need to use the semanage command. Then we need to run the restorecon command to restore the file's default security context. Now, in the event that the file system gets relabeled, our security context on the SSHD config file will remain. Take a look at the man pages for the commands used in this video to learn more about them. We already know that we can use the service command to stop processes, but we also have tools that we can use to stop applications and processes that we cannot control with the service command. We can stop a process with the kill command. Here is an example where we will be working with our FTP service. Let's first get the PID of the process. Now we can use that PID to stop the process with the kill command. Just type in kill, then the PID of the process. When we kill a process, we are in fact sending a signal to the process. When you use kill by itself, you are sending a termination signal to the process. This termination signal is also represented by the number 15, so the command above would be the same as running You can specify a particular signal to send to the process with the -S option. The termination signal is meant to send a clean shutdown notification to the process. If for some reason the process doesn't shut down cleanly and it gets hung up, we may need to send a hard kill or signal 9 to the process. Using signal 9 is the same as just plain pulling a plug on a process, so only do this when absolutely necessary. We can also use the kill command to send a signal to a process that will tell the process to reread the configuration file. The signal that performs this action is signal 1, or the SIG-hub signal. This time, we will use the pgrep command to get the PID of the HTTPD service. pgrep is basically grep for processes. With this command, we are searching for the HTTPD process that is owned by the root user. Now we have HTTPD's PID. Now let's tell the HTTP process to reread its configuration file. Of course, this would be easier with the following command. But I just wanted to show you what was going on behind the scenes when we reload a service. Take a look at the man page number 7 for signal to see a list of all of the signals that you could pass to the kill command. Just do a search on standard signals. And here is a listing of all of the signals that you can pass to a particular process using the kill command. We can also send signals to processes without hunting down what their associated PID is. We can send signals to a process by passing the name of the process to the kill all command. This command also sends signal 15, the termination signal, by default. And just like the kill command, you can specify a signal with the -S option. We can also use the pkill command. which is a kill command that looks for patterns to stop a process by its name. As with the other kill commands, you can specify signals with the -s option of the pkill command. As you can see, we have plenty of options for stopping and sending signals to processes. Just remember to only use the signal 9 when you absolutely cannot get a process to stop, as it is not a clean shutdown of an application or service. Now we are going to talk about another type of partition that we use on a Red Hat Enterprise Linux system, and that is the swap partition. The swap partition is meant to augment the system's existing RAM by providing another location for temporary memory to be used by preserving a portion of a hard disk to act as temporary RAM. This swap partition swaps memory for applications that are not accessed as often out of RAM and stores it in the swap partition. There is a performance hit on the system when this happens, but it mainly affects the application that is being swapped out of the disk and back into RAM. Traditionally, the size of the swap partition was anywhere between 1.5 to 2 times the amount of installed RAM. For example, if you have a system with 4 GB of RAM, then you would build a swap partition that is between 6 and 8 GB of RAM. This isn't as necessary as it once was, since most systems now come with quite a bit of RAM. Your configuration may vary depending on how much system RAM you have installed. We already have a swap partition on this system, so we are going to use our remaining 500 megabytes on our /dev/SDB device to add to our current swap total. To see how much swap space you have, as well as how much RAM you have, run the free command. We will run ours with the -m option to see how much memory space we have in megabytes. We can see that we have a total of around 2 gigabytes for our swap space. Now we are going to prepare a new swap partition. Again, we will be using our /dev/SDB device. Press N for a new partition. We will make it another primary partition, so press P. This will be our second partition on this disk, so press 2. We will use the default starting cylinder and the default ending cylinder since we only have about 500 megabytes left on this disk. Now we check our partition table, press P. Now if you look at our ID and system type for the file system, we see that it is set to 83 for the default Linux file system. We will need to change this to swap. Press L to see the list of different types of file systems we can configure. If we scroll through this, we see that 82 is the Linux swap type. So press T for type, then press 2 since we are working on the second partition, and enter in 82 for the Linux swap type. Then press Enter. Now press the P key to verify, and we can see that we have our new partition set to Linux swap. So press the W key to write our new changes. And as we see at the bottom, we are being warned that we need to either reboot our system or run the partprobe command for the kernel to see our new partition table. Now we are going to use the make swap command to make our swap file system, and we will give it a label at the same time. This is how we do it. We use the -L option to give our partition a label, which we will use to identify our new swap device in our /etc/fstab file. Next, we enable our new swap partition with the swap on command. Instead of using the device name, we are referencing the new swap device by its label. Now, if we run our free command again, we can see the addition of our new swap space. As you can see, we have an additional 500 megabytes of swap space. In order for our new swap space to be active at boot time, we will need to edit the /etc/fstab file and add a new entry for our swap partition. We reference our new swap partition with the label that we gave it instead of the device name. We are using the swap location to mount this device. We have the swap file system. We are using the default mount options. And we are not ever going to check this file system in the event of errors, since this is meant to be a temporary storage location for files when the system is running. Syslog is the core service that records and monitors system logs on a system. In Red Hat Enterprise Linux 6, the original syslog daemon has been replaced with the rsyslog daemon. It is a drop-in replacement for the original syslog service with some enhancements such as the ability to write log messages straight to a MySQL or PostgreSQL database, and by sending encrypted system messages to a remote syslog server. You won't have to worry about any of the advanced features for rsyslog on the RHCSA exam, but you will need to understand its basic configuration. The default configuration file for the rsyslog daemon is located in the etc directory. We will first take a look at the rules section. At first glance, you can see that this is the file that dictates where certain system messages get sent. For instance, you can see that most messages, besides mail messages, get sent to var log messages. And a little bit below that, we see that cron messages get sent to var log cron. Any messages marked as emergency get sent to everybody, as indicated by the star character. The rules are broken down into two sections. You first have the facility, such as cron, followed by a dot, and then finally the priority, here represented by a star, and for the emergency represented by the word emerge. So in the rules for cron, the facility is cron, then a dot, followed by the priority, which is represented by the star character. The star means that any priority messages gets logged to the cron log located at var log cron. In the emergency rule, any facility, represented by the star character, that has a priority of emergency gets sent to everybody. Some of the other priorities that we can log are critical messages, information messages, warnings, errors, and others. As an example, if we want to receive critical priority messages from the kernel facility to be sent to var log messages, we can modify our kernel rule like so. Once we make changes to our rsyslog.conf file, we can reload the configuration file to the service rather than restart the service. Now, anytime there is a critical kernel message, we will have an entry for it in var log messages. We can also set up our syslog service to send copies of our logs to a remote server. This is beneficial in a case where you can have a single location that collects logs for various systems on your network. You can save yourself some time by reading the various system logs at one server rather than logging into each individual server to view the logs. Another benefit is that in the event a system gets compromised, you can have another location that will store the logs from that system. If an intruder attempts to modify a system log on the compromised server, you will have a good copy of the logs on another system. Scroll down to the bottom of the file to find the section that contains the directives for sending the logs to a remote system. This directive is the line that actually sends the syslog messages to a remote host. The first part, with the star, indicates that we want all facility and all priority messages. You can change this if you only want specific facilities or certain priorities. Next, we see two @ signs. The two @ signs mean that we want the syslog communications to occur over TCP. If there is only one @ sign, that means the communications will occur over UDP. Next, you enter in either the hostname or IP of the remote system, followed by a colon, and finally the port number. By default, syslog uses port 514, but you can change this to whatever you want. Just be sure to have the port you specify opened on the remote host in its firewall. With this configuration, we are sending all log messages to our remote host at 192.168.75.132 on TCP port 514. And don't forget to reload your syslog configuration file. You can view the system documentation on the rsyslog daemon by using a web browser and viewing the following. In our next video, we are going to examine some of our system logs. In this video, we are going to discuss the various system logs that you will work with on your RHEL server. The systems logs are some of the most important components of a technician's toolkit. Understanding what the logs will tell you and where these logs are located is a necessary skill for the RHEL administrator. All system logs are located within the var log directory. You will often find that other services will have their own logs and subdirectories beneath var log. Constant monitoring of your system's logs is important to keep your system safe, secure, and running. And as a security measure, only the root user can read any of the system's logs. The primary log file that you will work with is located at var log messages. The var log messages file contains all of the standard system log notifications from various processes on your system. All running system software and any boot issues not directly related to the kernel are reported in var log messages. The var log dmessage log is the file that receives messages from the kernel during a system's boot process. You will also find information about hardware that is connected to a system. This includes information about your system's BIOS, your CPU, any PCI devices you may have installed, and so on. You can use the dmessage log to monitor when a hot swappable device, such as a USB drive, is connected to your RHEL server. The var log secure file receives messages for anything that is related to system security. Some examples include messages from TCP wrappers, which is a security feature for allowing and disallowing access to some network resources. System logins are monitored in var log secure, and other important security facilities. If at any time you believe that there has been an unauthorized intrusion on your system, check your var log secure file first. Look for any mysterious login attempts from IP addresses that you don't recognize, and you can check for any users that escalate their privileges to root. Only those users that you have authorized to do this should have this capability. Anyone else escalating to root would be a security breach. We have discussed the audit log file before in our SE Linux videos, but it is worth quickly repeating here. The var log audit.log is the log file that contains all of your messages from the SE Linux subsystem. The most useful entries in this log file are the AVC or Access Vector Cache messages, which notify you when an SE Linux policy check has been performed on a process. If you suspect that SE Linux is blocking access to a process or service, check here to see if there is an ABC message for your issue. You can also use this log file in conjunction with the var log secure file to correlate any attempted security intrusions. You will also find on your system that other services will have their own log files. Some examples are the var log yum.log file, which contains messages relating to software installations, and the var log boot.log file, which contains some extra system boot up messages. An example of a service that will have its own subdirectory under var log is the HTTPD daemon. Here, you will find log files for the various websites and virtual hosts that you could have configured on your system. There are various tools that we can use to monitor our system's log files. We can use tail-f to follow a log file as new messages are added to it so that we can monitor events as they occur in real time. There is also the dmessage utility that can be used to read the var log dmessage.log file for any kernel messages. And as always, keep an eye on your SE Linux messages with the SE Alert and AU Report utilities for any SE Linux ABC events. In the following videos, we will see how these log files are set up and how we can monitor some of them. Red Hat Enterprise Linux comes with a built-in host-based firewall built on IP tables. We will look at IP tables in a later video, but for now we are going to look at the system config firewall tool that we can use to configure our firewall. If you are new to the concepts of network firewalls, I recommend pausing here and doing some side research on the purpose and some basic examples of firewalls, as this series assumes a medium amount of knowledge in this area. To use the firewall utility, go to System, Administration, Firewall. As you can see, we get a warning telling us that this tool is primarily for a basic firewall, and that if we need more advanced firewall rules set up, that we will need to modify a file, the etc iptables file, by hand. If we have modified this file manually, then opened up systemconfig firewall, then all of our manual modifications would be overwritten. You should not need a complex firewall configuration for the RHCSA exam, but this is important for the RHCE exam. In any case, just keep in mind that this utility will overwrite any manual changes you make to your iptables file. Alright, now on to using the application. The toolbar at the top provides a wizard button, which will guide you through setting up a very basic firewall for a desktop, the apply button, which is grayed out until you make a change to the firewall's configuration, the reload button, which reloads all of the rules currently configured, the enable button, which is grayed out if the firewall is currently enabled, then finally the disable button, which disables the firewall. On the left, we have a list of various categories for common types of firewall rules, and in the right-hand pane, we can change our firewall configuration based on what category we have selected from the left. We will start with trusted services. This is where we configure the most common ports that we would use on a RHEL system. Just look for the service name and check or uncheck the box next to it to open or close the appropriate port. Next we have the other ports. This is where you can add custom services that are not defined under trusted services. For instance, let's say that we had a VNC server running on port 5951. We would click the Add button, select User Defined, enter in our port of 5951, and enter in TCP for the protocol. Click the OK button, and now we have our new port opened. We don't have a service name here, since this port is not defined in the etc services file. The etc services file is the list of predefined services, along with their port numbers and protocols associated with them. Take a look at the etc services file at some point to familiarize yourself with it. Next, we have our trusted interfaces category. The next category is for IP masquerading. This is for a system configuration that is acting as a router and you wish to forward packets. As it stands right now, the RHCSA exam does not expect you to set up a RHEL system to act as a router. The next category, port forwarding, ties into IP masquerading. Again, not necessary for the RHCSA exam. Next is the ICMP filter. By default, the firewall on a RHEL system will respond to ICMP requests from tools such as ping. We can put a check next to request types that we wish to reject here. And finally, we have custom rules. This is where you can create custom iptables rules to be used in your firewall. There is also a terminal interface for the firewall utility known as systemconfig firewall TUI. It is grouped into the same categories as the GUI tool. However, just remember that anything modified with this utility will overwrite any manual changes you would have made to the etc sysconfig iptables file. To make configuring a RHEL system's network settings easier than modifying scripts and running commands in the shell, Red Hat has developed the systemconfig network tool. Network Manager has replaced the systemconfig network tool as the default network configuration utility in a RHEL install, but it is still available for use. In order for us to use the systemconfig network tool, what we will need to do is disable the Network Manager. The first thing we will do is stop the Network Manager service. Next, we will prevent the Network Manager service starting at boot time. If these commands are unfamiliar to you right now, don't worry, as we will be covering these in more depth in later videos. We should now see that our Network Manager icon is no longer in our panel. And now we can run our systemconfig network utility. And press Enter. The instructions on how to use this utility are displayed in the bottom. Let's take a look at our ETH0 device. Press Enter for device configuration, then arrow down to our ETH0 device, and then press Enter. And here we see the same information that is in our ifconfig-eth0 file. Here we can change the device's name, We can set up DHCP instead of using static IP assignments, along with our primary and secondary DNS for this particular interface. Let's change this so that we are using DHCP. Just arrow down to Use DHCP and press the spacebar. As you can see, our static IP information has now been disabled. Tab down to the OK button and press the spacebar. Now tab over to Save and press the spacebar again. Now let's arrow down to have a look at our DNS settings and press the Enter key. Here we can set our host name for our system, change our DNS provider IPs, and enter in a DNS search path so that we don't have to enter in the fully qualified domain name for systems that we want to communicate with on our LAN. We are going to leave these settings as they are, so tab down to cancel and press the spacebar. Tab down to the Save and Quit button and press Enter. And that is how we use System Config Network to modify our system's network setup. It is important to understand how the Linux boot process works. If you have a good grasp on what occurs when your Red Hat Enterprise Linux system starts up, then you will be better equipped to troubleshoot any system startup issues. We are going to briefly run through the system's boot sequence before we dive into the details of each stage. The first stage in the RHEL boot process is the system's BIOS initialization. Next, the BIOS calls up the bootloader for the system. After the bootloader is brought up, the first kernel image is then loaded into memory. Next, the kernel mounts the necessary file systems and starts activating the appropriate system services. And in a final stage of the system startup, the user is presented with a login screen. The BIOS, which is an acronym for Basic Input-Output System, is a small program that is installed on the system's motherboard and is responsible for initializing the basic peripherals such as the keyboard, mouse, monitor, and the system clock. The BIOS is also responsible for searching for the boot device that gets the operating system started. Once the BIOS detects the boot device, it executes the program that it finds there, known as the bootloader. The default bootloader program for Red Hat Enterprise Linux is Grub, the Grand Unified Bootloader. After Grub starts, it searches its configuration file for the kernel that is listed as its default boot image. Grub then hands control of the system boot up over to this kernel. After the Linux kernel gets control of the boot process from Grub, it then detects the hardware that is installed on the system and loads its RAM file system from the system boot partition. This RAM file system contains device drivers and other important script and binary utilities that aid in the system boot process. The RAM file system file name begins with initramfs, then the kernel version number, followed by .img. The kernel then loads the root file system in read-only mode and then executes the init process. Init is short for the initial process, whose process identifier is always 1. After the init process is started, it runs the necessary script files in the /etc/init directory. Next, the etc init tab file is read to determine the default system run level. Once the default run level is determined, the scripts relating to this run level are then read and executed. Finally, the system displays a login screen for the user and the system is ready for use. In the following videos, we are going to look at each of these stages of the boot process in more detail. Well, it looks like we have a broken system here. It appears that we can't mount our root file system. We can't even boot into run level 1 to try and fix this. Reinstalling the system is not an option, since there is important data that we may need on this system. So what do we do? Thankfully, Red Hat has included a great set of tools on their install disk called the Rescue environment. We will pop the install disk into our drive and boot into the selection menu. To boot the Rescue environment, arrow down to the menu item for Rescue Installed System and press Enter. And now we boot into the Rescue environment. Just choose your typical options, and when we get to the Rescue Method page, choose the local CD and press Enter. Next, you will be presented with a question asking if we wish to start networking services for this system. We will choose Yes, since we may need to recover some files. Press Enter. Now we enter in our network information. Press the space bar to select the ETH0 device, then enter in an IP for your network or just use DHCP. We will go with DHCP for our example. Highlight the OK button and press Enter. Now on this screen, we are asked if we want to mount our file systems in read-only or read-write mode. We will go with the read-write mode so that if we find the problem, we can fix it and save the fix to disk. Highlight Continue and press Enter. This screen tells us that our system was successfully mounted and that it is mounted to the /mount/sysimage directory. Now, in order for us to have our changes saved to our system that we are trying to work on, we will need to first root the mount sysimage directory. Press Enter. Tab down to OK and press Enter. Now we are in a shell environment, so we can start working with the disabled system. So the error that we got when we were trying to boot our system was that the root file system could not be found. Let's take a look at the etcfs tab file. Before we do this, let's go ahead and root our root file system. And remember, it was mounted at mount sysimage. We will use the vim command for its syntax highlighting to help us locate any issues in case there is a typo. Now let's navigate to the line for our root file system. If we look at our option for default, we can see that it is not green like the others. In fact, the term should be defaults, not default. So obviously, we will need to fix that. Go ahead and make your change. Then save the file. Since we have a network connection, we can back up some data to another server, just in case we have further problems with this system. Let's copy over the important info file in the root user's home directory to a remote system. And let's copy over the var log secure file so that we can review it to try and find out who may have altered our fs tab file. Okay. Now that we have some data backed up, we can leave our rescue environment and see if our problem has been fixed. First, we need to exit our rescue shell. Then we can reboot the system. And there we go. Our system is back up and running, and we have some files safely copied over to another system. The rescue environment is a very handy tool for repairing systems that you cannot boot into. You may not need this on the RHCSA exam, but it is an exam requirement to know how to use the rescue environment. Another objective for the RHCSA exam is understanding the proper way of updating the Linux kernel on a RHEL system. Reasons for installing a new kernel on your system would include bug fixes and security updates that would apply to your setup, along with new features in the kernel that you would find useful. You can get your current kernel version by running the following command. This command will give you both the kernel version and release number. When you update the kernel on your system, you are actually going to install a new one. The reason why we install a new kernel instead of upgrading is that an upgrade would overwrite the existing kernel. That may not sound like a bad thing, but there are a few reasons why that may not be a good idea for your system. The first is that if you have specialized software that requires a particular kernel version, you don't want to lose the kernel that it works with. You may only want to use the new kernel to try things out, and eventually the specialized software vendor may support the new kernel. The biggest reason why you don't want to overwrite your existing kernel is in the event the new kernel will not boot your system. If you overwrite your existing kernel, you will no longer have the previous kernel installed that did boot your system. To illustrate the kernel's role in the boot process, we are going to take a look at our /boot/grub/grub.conf file. This file is what Grub, the Grand Unified Bootloader, uses to determine what kernel version to boot the system with. We will discuss the Red Hat Enterprise Linux boot process in more detail in later videos. The grub.conf file is broken down into different stanzas, each one for a different kernel version. As you can see here, our default is set to 0, meaning that the very first stanza is the default kernel that we boot with. If you take a look here, you can see that our current kernel version is listed. Yum is smart enough to install a new kernel rather than upgrade it, but if you're going to use the rpm command, use the -i option to install the new kernel and not the -u option to upgrade it. Let's use Yum on our system here to update our kernel. Notice that Yum is going to install the new kernel rather than update it. And now the new kernel will be downloaded and installed. Now let's take another look at our grub.conf file. As you can see, we now have another kernel version installed. When Yum installed the new kernel, it also updated our grub.conf file for us. And when we reboot, we will be booting with the new version of the kernel. In this video, we will discuss Upstart, the new default system startup service. It was originally developed for the popular Ubuntu Linux distribution. Red Hat uses Upstart in RHEL 6 as the replacement for the old System V init system. The System V init system started every service that was needed in a sequential order. So if a single service took a long time to start, then the whole boot process waited on that one service to fire up. Upstart, on the other hand, looks at services and tasks as events, and only starts services as they are needed and starts the events in parallel, leading to a much faster and more efficient boot process. Init is the first process started by the kernel during the system's boot up. All other processes descend from the init process. If we look back at the output of the pstree command, we can see the hierarchy of the processes, with init being the main parent process. sbin init is the location for the init program. This is typically not started by users on a system, as the kernel handles the communications with this process. All of the main configuration files for init in the Upstart system are contained within the etc init directory. There are some other scripts involved, but we will look at those momentarily. The main script that gets called first during the system startup is the etc init rcs.conf file. This script then executes the etc rc.d rc.sysinit script. After the rc.sysinit script completes, the rc.conf script then reads in the default run level for the system from the etc init tab file. Once the default run level is determined, rcs.conf then switches the system to that run level. The etc rc.d rc.sysinit script file is a bit of a workhorse. This script sets our system's hostname, starts up networking services, mounts and checks file systems, and it runs Plymouth. Plymouth provides the progress bar we see during the system boot up sequence. The rc.sysinit script also sets our SC Linux enforcement mode, and it assists with sending the appropriate kernel messages to the var log dmessage log file. The etc init tab file has been demoted with the introduction of Upstart. The etc init tab file used to be the file that set up our main system features, such as our terminals that were started and if the Ctrl-Alt-Delete keys would restart the system. All of this functionality has been moved to other script files within the etc init directory. The only thing the init tab file does now is dictate what the system's default run level is supposed to be. The etc init.rc.conf file gets called up by the etc init.rcs.conf file and uses the default run level that is picked up from the etc init tab file. The rc.conf file then uses that run level number to determine which run level scripts to start from the etc rc.d rcx.d directory, where x is the system run level from the etc init tab file. Some of the other scripts that are used during the system boot-up sequence are the etc sysconfig init script, which has some directives in it for setting the colors for the Plymouth progress bar and if the single user mode requires a password or not. We will discuss the single user mode in our run levels video. We also have the etc init tty.conf file, which sets up our virtual terminals that we can access with the Ctrl-Alt F1 through F6 keys. You may also find other minor startup scripts in the etc init directory, along with some startup scripts for some system services. This was a bit of a whirlwind tour through the Upstart system boot-up sequence. If you want to find some more information on Upstart, I recommend taking a look at the two man pages listed here, the Upstart project page from Ubuntu, and also take a look at these script files yourself. You can learn a lot about your system's boot-up sequence by just looking through the configuration and script files. We got a report that Alex is unable to log into the system. Every time she tries to log in, she gets an authentication failure message. She states that she knows her password is correct, so let's see what is going on. And we have confirmed the authentication failure message. Let's log in as root and take a look at Alex's account. We will take a peek at the etc passwd file to see if there's anything odd about Alex's account. Everything looks fine here. Let's look at the etc shadow file. Here we go. There is an exclamation mark at the beginning of Alex's encrypted password. It looks like her account is locked or disabled. Let's verify this with the system config users utility. Highlight Alex's account and press the Properties button. And click on the Account Info tab. There it is. Her password is locked. Let's uncheck that, then press the OK button. Now let's see if Alex can log in. Well, she passed the authentication check, but now she is getting an odd error stating that a file in her home directory could not get updated. Let's close the error message. Alex is not having a good day. We are getting another error relating to Alex's home directory. This one says that her required folders could not be created for her desktop. Let's have her log out. Let's take another look at Alex's account. We can see that Alex does have a home directory located at home Vance. So why is she having trouble with it when she logs in? Let's verify the permissions on her home directory. We found the problem. Vance is not the owner of her own home directory. Let's fix that. Now let's have her try again. That's much better. No errors, and Alex is now logged in properly. To summarize this example, if you are having issues with a user's account, check their password age and make sure that their account has not been locked. Also, be sure to verify any file and folder permissions for any content that they are supposed to have access to. Those are the main issues that pop up the vast majority of the time when it comes to troubleshooting a user's account. Along with using local user accounts, a Red Hat Enterprise Linux 6 system also provides a secure means of connecting to an LDAP server. LDAP, an acronym for Lightweight Directory Access Protocol, is a system designed for centralized resource management and authentication. This is one of those instances where using the graphical tool is much easier than setting something up via the command line. To set up LDAP authentication for users on a Red Hat Enterprise Linux 6 system, go to System, Administration, and Authentication. Under User Account Configuration, change the drop-down menu to LDAP. In the LDAP search base DN, you will enter something like this. In the LDAP server text box, enter in the hostname or IP of your LDAP server. All of this information is something that would be provided to you should you need to configure a server to authenticate against LDAP. Under Authentication Configuration, you will need to know if you are authenticating with a Kerberos server or an LDAP server. For Kerberos, just enter in the information that is given to you, such as your realm, KDCs, and the admin servers. If you need to authenticate to an LDAP server, click on the drop-down and choose LDAP. Notice by default that you have to use either LDAP-S for part of your LDAP server address or check the box for Use TLS to encrypt connections. If you check this box, you will need to click on the button for Download CA certificates. Then enter in the server address that has a certificate file in the PEM format. And once you do that, click the OK button. We're just going to use LDAP-S for our example. Once you have all of your pertinent information entered, just press the Apply button. Users that you have configured in LDAP can now authenticate on this system. To undo any of these modifications, just go back to System, Administration, Authentication, and click on the Revert button. You will get a warning stating that you will lose your configuration changes, which is fine since that is what we want to do. Click the Revert button, click the Apply button, and your system reverts back to only authenticating local accounts. Along with the command line methods of managing services, we also have a few other tools that we can use. The first utility that we will look at is System Config Services. It isn't installed by default, but you can easily install it with Yum. Once you have System Config Services installed, you can access it by going to System, Administration, and then Services. On the left-hand side, we have a listing of all of our services and their startup settings. The green circle means that the service is set to start at boot time and run levels 2 through 5. Again, we will go into details about the different run levels in a later video. The red circle indicates that the service is not set to start at all when the system boots. The services that have a control panel icon next to them indicates that they are set to start automatically within different run levels. To view those settings, highlight one of the services, then click the Customize button. Here we can see that the Avahi daemon service is set to start and run levels 3, 4, and 5. To enable or disable a service, just highlight it and click the Enable or Disable buttons. Just as with the service command, we can stop, start, and restart currently running services. Just highlight a service and click the Stop button. And if we look to the right, we can see that the SSHD service is stopped, along with some other information about the service. There is another program that we can use to manage services called ntsysv that we can run from the command line. ntsysv is a text interface utility that lets us enable or disable services at boot time, just as the check config command does. We can use the arrow keys to scroll down to view our services, and we can use the spacebar to enable or disable a service. There is one drawback to the ntsysv utility. It will only modify a service's startup capability in the current run level that you are running the command from. For instance, we are in the graphical desktop environment, which is run level 5. So if we disable the cron-d service when in run level 5, the ntsysv utility will only modify the service for that run level. Here is an example. Let's take a look at the listing of our cron-d service. Now, let's go back to ntsysv and disable the service there. Now, let's look at our check config output for cron-d again. And we can see that only run level 5 is affected. However you modify your services, just be sure to remember that whatever services you are required to have running when the system boots, that you have them properly set up to do so in order for you to get credit for them on the RHCSA exam. As a systems administrator, it is important to know what processes are currently using your system's resources. You can also help ensure system security by verifying that only valid applications and services are running on your system. There are numerous ways to view what processes are running on your RHEL 6 system. The first we're going to look at is PS-Tree, which not only shows you what processes are running, but also the parent processes that started each one. PS-Tree displays a snapshot of this information in an inverted tree, with the parent processes towards the top. Here we see init, which is the very first process that begins on a RHEL 6-based system. And with the PS-Tree output, we can see what other subprocesses that init has started on its own. Some subprocesses have their own further subprocesses. For instance, HAL-D starts HAL-D runner, and so forth. There are numerous command line options that we can use with PS-Tree. For instance, PS-Tree-P will show us the same tree information, but also the PID, or process identifier, for each individual process that is running. PS-Tree-A will show us any command line options that were run with a particular process. The next tool that we will discuss is the PS tool. PS comes to Linux from BSD, so you don't have to use dashes with its options like most Linux commands. However, if you're used to using dashes for your command line options, it will work with those as well. PS by itself will only show you the immediate applications that you are running. By running PS-U and then a username as root, we can view the processes that are currently running for a particular user. Running PS with just a lowercase u by itself will show more details about the current processes running under your own user account. To see every process running on the system under any account, including system accounts, as root or any other user, run PS-AUX. Here we can see the processes running as root, and some as RTKit, an RPC user, and so on. This is a good way as a systems administrator to see if any particular user on the system is taking up more resources than they should. The last command line tool that we will demonstrate is top. Unlike PS and PS-Tree, top will continuously update itself, so you can view in real time what is running on your system. You can press the H key while in top to get a quick view of some of the commands that you can use with it. Here is an example where we can change the display colors of top to help identify some of the information that top displays. Pressing the Q key will quit top. In addition to the command line tools, there's also a GUI tool that we can use to view our currently running processes. Go to Applications, System Tools, and open up the System Monitor. Here on the Processes tab, just like top, in real time we can see all the processes that are currently running on the system. Vim is by far the most commonly used text editor on Linux. Vim is an enhancement or an improvement over the original Unix text editor, VI. Many system administrators prefer Vim for its abundance of features and ease of use. Not only that, but other text editors such as Nano might not be available on a RHEL system, but it is very likely that the Vim text editor will be installed and available. Vim does have a bit of a learning curve to overcome for those that are new to this text editor, but once you get past the basics, you will find that you can quickly work with files within it. Vim is installed by default in Red Hat Enterprise Linux 6. Vim is what is known as a bimodal editor. What that means is that Vim defaults to a read-only view that lets you take a look at the file's contents but not modify it. The other mode is the editor mode, where you actually modify and enter text into the editor. We start Vim with the command vim. Notice that with just the vim command, we are greeted with a welcome screen that shows some of the most basic commands that we can use. We can type :help, press enter, to see the help file for Vim, which will give us further information on how to use Vim. It tells us that we can use the J and K keys to navigate around a file, J to go down, K to go up. Let's scroll down to one of these highlighted files. To view one of the highlighted manual files, press the Control key and the close bracket key to jump to that file. Again, using the J and K keys, we can navigate around and read the text. Let's practice some basic commands with Vim. Press the key and the Q key to quit this file and drop down into the editor. We are now in normal mode, which lets us review text. We don't have any text in this window, so let's enter some. To do so, press the I key to enter insert mode. If you will look at the bottom, we can now see that we are in fact in insert mode. To go back to normal mode, just press the escape key. While in normal mode, we can save our files and quit out of Vim. To save the file, press the key, W, then Q, for write the file, then quit. Then enter file name, such as vim-test.txt. Note that if we do not enter a file name, we will get an error message stating that we didn't enter one. To open up our file that we just created for further editing, enter in Vim and then the file name. Our file is now opened up in normal mode. Let's add some text to the end of this line. To do so, while in normal mode, we press the Shift key and the A key. Notice that our cursor has jumped to the end of the line and we are already brought into insert mode. We are now ready to append more text to the end of our line. Press the Escape key to go back to normal mode. Let's move our cursor to the beginning of this line. We will do this by pressing the 0 key. Let's add another line of text beneath the line that we already have. This is done by pressing the O key. Now we are at the start of the line beneath our first line of text and brought into insert mode. Press the Escape key again to go back to normal mode. Press the K key to move up one line. We are going to copy this line of text and paste it below the first line. First, press YY to yank the line and place a copy into the text editor's buffer. Then press the P key to put the copy of the line beneath our current line. Notice that this did not change our mode. We are still in normal mode. Well, what if we did not want that bit of text there? We can undo our last change with the U key. The duplicated line of text is now gone. Let's delete that capital H on the first line. Make sure that the cursor is over the H. Then press the X key. The H is now deleted. Press the U key again to undo that change. Now, let's quit out of Vim without saving our changes. This is done by pressing colon, the Q key, and exclamation mark. These are just some of the basic commands available within Vim. I would suggest that you look over the help manual within Vim to learn more about this powerful editor. There's also a built-in instructional walkthrough for Vim called Vim Tutor. If you are new to Vim, I recommend practicing all of the steps in Vim Tutor to get a good feel for this text editor. The RHCSA exam expects that you know how to configure a server to host virtual machines. In our previous video, we showed you what group packages to install and what services to enable. In our next few videos, we will show you how to manage guests on a host system. We have a RHEL 6 guest installed on our host system here, so we are going to show you how to manage this guest from the virsh command line toolset. Let's start off by running the virsh command to jump into the virtualization shell. We can get a quick listing of the hypervisor's details with the node info command. The output tells us our CPU and RAM information. To view a listing of guests that are currently on the hypervisor, run the following. The output shows us the guest ID, the name of the guest, and its current state. We can see that we have a RHEL 6 VM and it is currently running. We can even shut down a running guest with the following. If you notice, instead of the word guest, we see the word domain. In the virsh terminal, each guest is known as a domain. You will often find either one of those words when working with virtualization, but they are interchangeable terms. Let's take another look at our guest status. And now we can see that our guest is shut off. To start the guest back up, run the following. And we can check our status again. And even though it is booting up, the state says that it is running. Now, if you have a guest that will not shut down and you believe that it has gotten hung up, you can run the following command. This command doesn't delete your guest, but instead just shuts it down. Do not use this unless you absolutely have to, as this command is essentially the same as pulling the plug on this guest, causing it to shut off ungracefully. You could potentially lose data on your guest with this method. If you want to see some extra details on your guest, just run the dom info command followed by the name of the guest. Here we can see the state of the system, the guest assigned RAM and CPU information, and a couple of other interesting facts. The first is the SC Linux security label. As you can see, the guest has a label of svirt_t. This security context is for the actual virtual machine process itself, and each one is unique. The other interesting field is the Auto Start section. The Auto Start field grants the ability for a guest to start up automatically after the host system boots up. Currently, our RHEL 6 guest is not set up to auto start. We can change that with the following command. Now our guest will start up after the host boots up. To turn this feature off, just run the following. To see a complete listing of the commands that you can use in the virsh terminal, just run help. As you can see, there are quite a lot of commands available. To leave the virsh terminal, just type exit. We stated before that KVM runs guest virtual machines as a Linux process. Here's what that looks like. Just be sure to not stop the process directly from here. Use either the guest's built-in shutdown routines or the virsh terminal's shutdown command. In our next video, we will work with Virt Manager to show you how to perform the same task using the graphical tool that we just demonstrated here. We will also install a RHEL guest using this tool. Virt Manager is the graphical front-end tool that we can use to manage our virtual guest machines. With Virt Manager, we can monitor currently running guests, manage our disk image storage, and create new virtual machines. To access Virt Manager, navigate to Applications, System Tools, Virtual Machine Manager. We are greeted with a simple interface displaying our single RHEL 6 guest. We can interact with our RHEL 6 guest by clicking on it, then pressing the Open button. Here we can see the login screen for our RHEL 6 guest. At the top, we have our toolbar with some common functions. First, we will look at the Pause button, which suspends the running guest. If we look back at our Virt Manager window, we can see that the guest is paused. To resume the guest, just press the Pause button again. We can shut down the guest by pressing the Power button icon. Before we do that, let's take a look at some of the options that are available to us by clicking on the down arrow button next to the power icon. Here we see an option where we can reboot the guest, shut down the guest, or force off the guest, which is the same thing as just plain pulling the plug on the guest. We also have a save option, which basically saves our current state of the virtual machine to disk and then shuts it down. For now, we are just going to shut down our guest. And our guest goes through a proper shutdown. Let's click on the Information button. Here we have a quick overview of the guest and some details about our host server. Then we have the Performance category, which will give you some statistics about your guest's memory and CPU usage while the guest is running. Next, we have our Processor category. We can see that this guest is only assigned one virtual processor. We can assign more if we want, but we cannot exceed the total available on the host system. Next, we have the Memory category, which is where we can modify how much RAM the guest gets from the hypervisor. Next, we have the Boot Options category. We can see the Auto Start feature that we set earlier with the virsh command, which in Virt Manager just requires a checkbox. Remember this location should you need to set up a guest to auto start with your host server in case you are asked to do so during your exam. We can also change the device that we boot from and in what order the guest should search those devices when attempting to boot. Next, we have our hard disk image. We see that we have a VirtIO disk, and it is located at var lib libvirt images. Here we have the CD-ROM category. We can configure the CD-ROM device to be connected directly to the host CD-ROM drive, or we can have it mount an ISO image. I just wanted to quickly go over the most important categories, but I encourage you to review the rest of them on your own. Let's go ahead and start our guest back up. In our next video, we will create a virtual guest. Even though KVM supports both Windows and Linux virtual guests, the RHCSA exam only tests your ability on installing Red Hat Linux systems as a virtual guest. Now, let's walk through the steps to set up a brand new guest. To create a new guest, click on the Create New Virtual Machine button on the toolbar. First, we will give our guest a name. Then we can choose how we are going to install the guest. We can choose between an ISO image or a disk in our CD-ROM drive. We can also choose from a few network installation methods or import an existing disk image. We will use an ISO image. We will browse for our local ISO image, which we placed in a directory we created called var ISOs. Click on the ISO that you wish to use, then click the Open button. Now we will click on the drop-down menus to choose our operating system type and version. Click the Forward button. Now we can configure how much RAM the guest will have and how many CPUs we will assign it. We will configure our guest with 2 GB of RAM and 2 CPUs. Click the Forward button. On this page, we can configure our virtual disk file. By default, our disk size would be 8 gigabytes. We will increase this size to 10 gigabytes. Below that, we see an option to allocate the entire disk now. When this is checked, the disk creation will build a disk file the exact size that we specified. For instance, we chose 10 gigabytes for our virtual disk storage. So by allocating the entire disk now, we will create a disk file that is 10 gigabytes in size. This file is created in the raw file format, meaning that all of the disk space is there. This file format is better for performance, as we will explain in a moment. If we uncheck this box, the other option would mean that we will create a much smaller file that will grow to the size we specified. As we install the operating system and software, the disk image file will increase up to the maximum disk size we set. So if you create a 10 gigabyte disk size and your operating system install is only 3 gigabytes, then your disk file size will be 3 gigabytes. It will only increase when you add more data to the disk file. This file format is the QCal format. This will save you disk space, but you will lose out in performance as your disk file grows. In a raw formatted file, the data goes straight to the image disk, but in the QCal formatted file, the data is copied in, and then the disk size expands, and then more data is copied in, and the disk size expands again. The performance hit comes from the hypervisor having to keep a check on the disk file size and increasing it when needed. Now we are presented with a summary screen showing our installation information. Let's click on the Customize Configuration Before Install checkbox. Then click the Finish button. Here we are presented with a view of the virtual machine's details. Click on the Disk category, then click on the Advanced options. We can see that the cache mode is default and our storage format is using a raw formatted file, but let's take a look at our disk bus. As you can see, we have a few options as to what type of disk bus to use. We stated before that a fully virtualized guest is not aware that it is a virtual machine because it is not using any modified drivers. If we click on VirtIO, then we are telling Virt Manager to create our guest using drivers specifically designed to provide better performance for KVM-based hypervisors. Once you install virtualization-based drivers, you go from running a fully virtualized guest to a para-virtualized guest. So the trade-off is that you could get slightly less performance on a guest that doesn't know that it is a virtual machine, or a guest with slightly better performance that is aware that it is a virtual machine. Some vendors may not support virtual machines, so this can be important depending on your environment. For our example, we will use the better performance of the VirtIO disk bus. Then click the Apply button. Now we will continue on with our installation as normal. Just click the Begin Installation button once you have completed your changes. Again, I encourage you to explore the Virt Manager utility further. There are a lot of advanced features there that you will not be responsible for on the exam, but it really is a neat tool. VNC, short for Virtual Network Computing, is a way to share a graphical desktop over the network. The concept is quite similar to the remote desktop utility on Microsoft Windows. In this video, we are going to set up one of our systems to act as a VNC server, and we will access the graphical desktop of this system from a remote client. We will set up this system here to allow remote access to it with VNC. We will first need to install the Tiger VNC server package. This is the service package that we need to allow us to remotely view the graphical desktop of this system. Now, we need to configure our user's display to be accessible from a VNC client. The current desktop that we see is desktop 0, so we will need to tell the VNC server to send out desktop 1 for the K Armstrong user. We do this with the following. Next, we are asked to enter in a password to access this desktop. This password is not the same password you use to log into your system. The VNC password is kept separately from that. You can, however, use the same password you use to log into your system if you want. And the VNC service will create the appropriate configuration files in our user's home directory. Keep in mind that if you want to do this for other users on your system, you will need to repeat these steps for each user account. Just be sure to increment your display number by 1 each time you configure a new display, and enter in a password for each account. Next, make sure that the service is started and configured to run at boot time. When we ran the VNC server command, it started the VNC service for us. Now, we need to edit our etc sysconfig VNC servers file to accept our connection. Uncomment the lines at the bottom of the file and set it up so that we are looking at desktop 1. And be sure to put in the appropriate username. Do the same for the bottom directive, but set it up so that we are listening on port 5901 and remove the local host entry. The local host entry will only allow connections from the local system, and we want to access it remotely on port 5901. We are also removing the no listen TCP option since we want our VNC server to explicitly use TCP. Now enter in the option for the RFB port, which is the port and protocol that VNC uses, for port 5901. Now let's restart the VNC server service. Next, we will need to open the appropriate port in our firewall. Now let's move over to our other system and see if we can access this desktop. First, we will need to install the VNC Viewer application. This is part of the Tiger VNC package. Now let's see if we can access the other system. We do this with the VNC Viewer command. Then we enter in the IP, and then the port number. Enter in the password that we configured earlier, then press enter. And now we are looking at the desktop of the remote system. Make sure that you set this up for a regular user and not the root user. Configuring VNC for the root user is possible, but not a good idea for the sake of your system security. Hello, and welcome to VTC's course on the Red Hat Certified System Administrator exam. My name is Kenny Armstrong. In this course, we will cover the highlights of what you will need to know for the RHCSA exam. If you are new to Linux, I would recommend that you take a look at some of VTC's other Linux training courses. This course assumes that you have an ample amount of experience with Red Hat Enterprise Linux, Fedora, CentOS, or Scientific Linux. The RHCSA exam itself is designed for seasoned Red Hat Linux administrators. With the release of Red Hat Enterprise Linux 6, Red Hat has replaced the Red Hat Certified Technician certification with the RHCSA certification. The new RHCSA certification better reflects the skills that are needed by modern Red Hat Linux system administrators. All of the content in this course is derived from the exam objectives as outlined by Red Hat. You can find them at this page here. I will suggest that you look over this page so that you will have a good understanding of what is expected of your skills as an RHCSA candidate. The video series itself will be modeled after the course outline for the Red Hat System Administration 2 course, RH134, available at this page here. We will be concentrating on using command line tools. The reason for this is that you might not always have a graphical environment available to work with. Also, administrators who are comfortable with the command line can complete tasks quicker than clicking through a GUI application. We will, however, demonstrate the use of graphical tools, but they will not be the focus of this course. The RHCSA exam is a performance-based exam, which means that it is completely hands-on. The exam is performed on a live system. No books or outside notes are permitted. I highly recommend that you practice as much as you can. You will have about 3 hours to complete your exam objectives, so the more you practice, the better equipped you will be to pass the exam. If you plan to continue on and attempt the RHCE exam, you will need to know all of these skills required for the RHCSA as well as those required for an RHCE to pass that exam. This is a Red Hat exam, so you must practice on a Red Hat Enterprise Linux 6 based system. Attempting to study with another distribution of Linux will not help you a whole lot, since Red Hat has standardized on particular system directories and tools that other distributions do not include. You can obtain a copy of RHEL 6 by either purchasing install media or by requesting a 30-day trial copy from Red Hat. You can still use the 30-day trial installation after your trial period is up. However, you will not be able to receive any new updates or install any more software from the official Red Hat repositories. The next option is that you can use one of the rebuild distributions, such as Scientific Linux or CentOS. The rebuilds have their own benefits in that they are virtually identical to Red Hat Enterprise Linux without the Red Hat trademarks such as logos. I myself used a rebuild for the bulk of my study for the Red Hat exams. The organizations that create these rebuilds are using the source RPMs that Red Hat provides for public download at their FTP site. Red Hat Enterprise Linux is built on open source code, and in keeping with the open source tradition, Red Hat provides these source RPMs for anyone to download and build on their own. Scientific Linux and CentOS utilize these RPM files to construct their distributions that contain the same directory structure and tools that are available in Red Hat Enterprise Linux. So feel free to follow along with this course and practice your skills with these distributions as you prepare for the RHCSA exam. More information about the rebuilds can be found at www.centos.org and also at www.scientificlinux.org. The proc file system is a virtual file system that contains information about the running Linux kernel. We can read information about the various running processes, our current CPU stats, memory usage, our disk partitions, and other important system information. We can make changes to some of the data within the proc file system, which will modify how the kernel behaves while the system is running. However, since the proc file system is created when the system boots, the changes we make will not survive a reboot. Shortly, we will see how to make these changes permanent. The proc file system is where commands such as lsusb and lspci get their information from. A lot of the information in the proc file system is easy for us to read, but other locations contain information that is difficult for an administrator to understand. That's where the assistance of commands such as ps, lspci, top, and others come into play. Let's take a look at the proc file system. As you can see, there's quite a good deal of information in this directory. We can see a file in here called CPU info. Let's have a look at that file. And here we can see some information about our processor. We also have a file called meminfo. Let's view this file. And here we can see some very detailed information about the memory usage on our system. An example of a command that uses the information from this file is the free command. As you can see, it is a bit easier getting the main details from the free command than it is to parse through the long output of the meminfo files. Take a look at the proc mounts file and compare that to the output of the mount command. Again, the proc file system contains more details, but the mount command makes it easier to read the information we need. We can also change the way the kernel behaves while the system is running by modifying some entries in the proc file system. For instance, we can set our kernel up to route packets through it, which is a necessary step for setting up a Linux system to act as a network router, by changing a parameter in the proc file system. If we take a look at the IP forward kernel parameter within the proc file system, we can see that the parameter is set to 0, meaning that this feature in the kernel is turned off. We can change this while the system is still running by modifying that parameter. Now, our system is set up to allow packets to be forwarded through it. However, the proc file system is created at boot time, and we only changed a kernel parameter while the kernel was running. So the next time we reboot, this parameter will be turned off again. The etc syscontrol.conf file lets us make modifications to some of the same kernel parameters that are in the proc file system, and these changes will be persistent across reboots. Let's take a look at this file. And if you look at the first option in this file, we can see that it is the setting for allowing packet forwarding. If we change this setting to 1, then when we reboot the system, the IP forward value in the proc file system will be enabled. Should you need to modify other kernel parameters, you could use the sysctl command. To see a complete listing of kernel parameters that you can change, run the sysctl command with the -a option. There are a lot of options, so pipe the output to the less command. If you make any changes to any of these values, make sure to add a line for that option and its value to the etc sysctl.conf file to make it permanent. Take a look at the man page for the sysctl.conf file and the sysctl command to find out more details about this command and its associated file. The yum command is the simplest way to install software packages from the command line. The beauty of yum is that it handles dependency resolution for us. What that means is that if we go to install a package, and that package needs another package, then yum will also install the other package as well, and so on until it gets all of the necessary pieces for a program to run properly. Yum will use pre-configured repositories, usually web or FTP sites, to search for and install software. We can also use yum to install packages that we have downloaded, and it will resolve any dependencies that are needed to complete the installation. If you know the keyword or even part of a package name for something you wish to install, you could run yum and search and package name. Let's try this for the system config LVM utility. Here we see that the package is available for download and install. Let's see if we can gather some more information about the software with yum info. Just type in yum info and then the name of the package. The output tells us that this software is not architecture specific, so the same package will work on both 64 and 32-bit systems. The version and release numbers of the software, the file size of the RPM, that it is available from our local net repository, and some brief information about what the package is or what it does. Alright then, let's install the package. Yum install system config LVM. We are then prompted by Yum if we wish to proceed with the install after we are shown a summary of how much disk space will be used and what, if any, dependencies will be installed. We already have the necessary dependencies for system config LVM installed, so we don't need to install anything extra. We will press Y for yes, then enter, and the install commences. We can also uninstall software with Yum remove, and then the package name. We will remove the system config LVM package that we just installed. Yum prompts us, asking if we are sure that we wish to uninstall the package, and again we press Y for yes. And the software is removed. We can also list the different groups of packages that are available for us to install with Yum group list. Package groups are collections of software for a particular task or setup, such as Welsh language support for the system or the full group of software needed to run a database server. We see that a web server package is available, so let's install that. We do this with the group install option for Yum. And when dealing with groups, enclose the group name in quotation marks. Here we see a good example of dependencies that would need to be installed in order for the software to work properly. Press Y for yes, and then enter. And now we have a web server installed. Well, we are done playing around with the web server, so now let's uninstall it. We can do this with the group remove option for Yum. Then include the group name in quotation marks. We get a summary of the packages that will be removed, and we are prompted to make sure that we wish to actually proceed with the uninstall. Press Y for yes. And the web server has been uninstalled. Just as with most other commands, you can look up the man page for the Yum command to get some more details on the various options that you can use with the command. Now we are going to discuss where Yum goes to look for software to install. The RHCSA exam expects that you know how to configure a Yum repository file on a RHEL system, as you might need to set up Yum on your system to communicate with a local repository. Yum repositories are located in /etc/yum.repos.d. As you can see, we have a few sources that we can install software from. All repository files should end with a .repo extension. A typical RHEL system will only have between 1 and 3 repositories configured, usually just the RHN repositories that Red Hat hosts. We are going to take a look at our local repository that we have set up on our LAN, the local net repository. The first line is a one-word identifier for our repository. No two repositories can have the same repository ID. The next line is the name of the repository. This is what you see displayed in a list of repositories that Yum communicates with when you run the Yum command. The next line is the base URL, or the location either locally or on a network location that contains the repo data file for the repository. The repo data file contains the information about location and groupings of packages that Yum uses to find and install software. Common base URLs will either be HTTP or FTP locations, but sometimes you will find that the base URL will point to a local directory depending on the system's configuration. As you can see, we are pointing ours to a local FTP server. The next line tells us if the repo is enabled or not. A 1 means that we are using this repository, and a 0 means we are not using it. The GPG check line indicates if we are performing a GPG or GNU Privacy Guard check on any packages that we download. Since we are getting our packages from a trusted local source, we have turned this off. A 1 here would indicate that we are performing GPG checks, which is the most common configuration. The next line is for the URL location of the GPG key. We are using the local key on the system to check the integrity of files. Take a look at the man page for yum.conf to learn more about repo files, as there are quite a few options that you can configure. To search for the repository section, hit the / key, then the / key, bracket, repository, and then closing bracket. In the repository options section, you can see an example repository file along with a listing of all the different options that you can find within it and how to configure it.